Hello everyone and thanks for joining my course. My name is Swapnil and I am your instructor throughout this course. Let's talk about who can join this course. So, ethical hackers, pen testers, malware analysts, computer science students, and anyone who wants to learn something new can join this course. So let's talk about skills which are needed to understand this course. So you need only two skills. The first skill is C programming language basics. The second skill is Linux command line basics. You should be comfortable in using Linux terminal commands. So two skills are needed for this course. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, we will look at how a computer system works. If you want to learn assembly, then you should know how a computer system works internally. So basically, a computer system has three components. The first component is input-output devices, which includes keyboard, mouse, and monitor, which handles input-output signals in the computer system. The second component is memory, which stores the input data given by input-output devices. The third important component is CPU, which processes the input data given by input-output devices, which are coming through the memory component. So basically, these three components are connected by buses, which are responsible for transmitting data in these three components. So when any user submits data to the computer, first it goes into memory unit where this data is stored. Then this data is transferred to the CPU for processing. After data processing by the CPU, this data is transferred into memory where it stores the processed data. And then this data is transmitted to the input-output devices, which are received by the user. So this is the mechanism by which a computer system works. So in order to understand assembly language, we have to understand the CPU internal workings inside the computer. So in the next video, we will deep dive into the CPU internal workings. If you have any questions regarding this concept, feel free to ask in the comment section. I will surely help you. That's all for now. I will see you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, we will look at how a CPU works. CPU is used to execute programs. Programs have instructions which acts as input for the CPU. The CPU takes input as an instruction from the programs and processes those instructions, then gives the output to the computer user. Let's understand CPU by a simple example here. Suppose a user has created a simple program which adds two numbers. First, this program needs to be compiled to get the executable program. So the user compiles this program. In this compilation process, first the program is converted into an object file which is nothing but assembly code, which is human readable. Now this assembly gets further converted into machine code using a linking process by the compiler. Now you can see this assembly code is converted into machine code in hexadecimal form, which is stored in binary form in our secondary memory at a particular memory address. Now when the user executes this program, first the program binary instructions are loaded into primary memory at a particular addresses. Then the first instruction is transferred into decoder inside the CPU to decode the instruction. After decoding this first instruction, the decoded binary is moved into the control unit. Then the control unit moves this instruction into ALU for arithmetic and logical operations. Here you can see the instruction is moving number 2 into a register. So in this case, the CPU has small storage units called registers. These registers are used to store data inside the CPU. So this number 2 is stored inside this register. The second instruction will be moved in the same way inside the decoder. Then this instruction is decoded and moved into the control unit. Then this instruction is moved into ALU. Here you can see the instruction is moving the second number into the RBX register. Like the same way, the third instruction will be moved into the decoder from memory where it is decoded. After decoding of this instruction, the decoded instruction is moved into the control unit. Then it is further moved into ALU. Here ALU is used for arithmetic and logical operations inside the CPU. Now this instruction is adding RAX and RBX values and storing the result in the RBX register. So here addition is done by the ALU unit and the result of addition is stored into the RBX register, which will be further received by the computer user with the help of input-output devices. So this is the way a CPU works inside our computer system. Now if you have any questions regarding this concept, let me know in the comment section. I will surely help you. So that's all for now. I will see you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, we will look at CPU registers. Our data is stored in our computer system in different memory units. We store our data permanently in our hard disk drives. Then the computer uses the RAM memory to store temporary working data when the computer is switched on. There is a third location where our data is stored in a computer, and that is inside the CPU. In CPUs, there are very small memory storage units called registers. These registers can store up to 64 bits of data at a time. There are many registers inside the CPU and all of them are divided into three basic categories, which are general purpose registers, segment registers, and instruction pointer register. Registers are named based on the size and working of the register. Let's take an example of this first 64-bit register called RAX. If we make it half of this RAX register, then this will be called EAX register. Further, if we make it half of this 32-bit EX register, then this register is called an AX register. Again, if we divide this 16-bit AX register into two 8-bit parts, then the lower part is called AL and the higher part is called AH register. Like the same way, all the other registers are named accordingly. You can see here there are 16 general purpose registers here. We have to study 64-bit assembly programming, so we have to focus on 64-bit registers here. Let's understand the purpose of each general purpose register here. The first four registers RAX, RBX, RCX, RDX are used for storing general data. Let me give you an example here. Suppose we have a simple program here which adds two numbers and stores the result in the result variable. And after that it performs a simple loop operation in which it prints number 1 to 5. So in this case we can store a variable value into RAX, b into RBX, and automatically the value of result will be stored in RBX register. Now you can see here the I variable is used for loop count in this program to print 1 to 5 numbers. So here the RCX register is used for storing counter variable values, and in this case it will store the value of the I variable which is handling the loop counter in this program. The last register RDX can be used to store any data like these. Let's move to our next registers, which are RSI and RDI. RSI and RDI are used for string operations in a program. In RSI, SI means source index, and in RDI, DI means destination index. Let's understand the use of these registers by taking a simple example here. Suppose I want to move this string into another location in memory. So this RSI is used to point this source string index pointer which we want to move. whereas RDI is used to point the destination pointer location where we want to move the string. Now let's move on to our next registers, which are RSP and RBP. RSP is stack pointer, which always points to the top of the stack in memory, and RBP is the base pointer, which always points to the bottom of the stack in memory. The R8 to R15 registers can be used for general purpose data storage. Programmers can store temporary values, function parameters, and local variables in these registers. The RIP register is used to store the memory address of the next instruction to be executed by the CPU. Let's take a simple example to illustrate the role of the RIP register. In this example, the instruction pointer initially points to the address of the main function here. The CPU executes the instructions sequentially. After each instruction, the RIP register is automatically updated to point to the next instruction's memory address. The RIP register plays a crucial role in keeping track of the next instruction to be executed, allowing the CPU to execute instructions in a sequential manner. Let's jump into segment registers. In segment registers, first we have code segment register, which points to the code segment in memory where the CPU should fetch instruction for execution. Data segment register is typically used for addressing data in memory. Stack segment register points to the segment where the stack is located in memory. The remaining extra segment registers are used for additional data storage. So that's all for now. If you have any questions regarding this concept, let me know in the comment section. I will surely help you. I will see you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, we will look into flags of the CPU. Let's understand what the flag is and how it works in CPU. When a computer user gives any arithmetic and logical operations to the computer, first it goes into RAM memory, which is further transferred into the CPU for processing and execution. After calculation of this user input, CPU gives a status of that operation. This status is given by a register called flag register. So whenever the CPU gets any input of arithmetical and logical operations, this flag register gives the status of that result. Now this is the structure of the flag register, which is 32 bits in size, where each bit is indicating a flag bit 0 or 1. 1 means flag is on and 0 means flag is off. Let's understand some common flags in the flag register one by one. Let's start by carry flag. Suppose the user gives add arithmetic operation of these two numbers, which are 128 plus 128. First, these numbers are converted into machine code, which will be in binary form, and then addition operation is done here. First, this 0 and 0 will be 0, then 0 and 0 will be 0, like the same way up to here. Now in the last addition, this 1 plus 1 will be 0 and carry will be 1 here. So in this case, the carry flag will be set here because there is a carry left in this addition operation. Please remember one important thing here. This add operation is performed on an 8-bit register here. So when there is an overflow in this 8-bit register, there will be a carry. So that's why the carry flag is set here. Let's move on to the parity flag. Let's change the user input to 4 and 5 here. Now when we add these numbers, we get this number in binary. This result will set the parity flag on, because when we add this result of binary numbers, we will get 2, which is an even number. If the result was odd, then the parity flag would be off. Let's move on to the auxiliary flag. Auxiliary flag is set when the first 4 binary digits in arithmetic operations gets a carry. Let's understand it by changing our inputs here. You can see here we have changed both inputs to 8. Now if we add these two binary numbers, we are getting a carry in the 4th part. Due to this carry here, our auxiliary flag will be set. So that's the auxiliary flag. Let's move on to zero flag. Let's change our arithmetic operation from addition to subtraction here between these two input numbers. If we calculate these two numbers, we are getting result as a 0 here. So when the result of any arithmetic and logical operations is 0, then this 0 flag will be set. So this was 0 flag. Let's move on to the sign flag. Let's change the input numbers to -5 and 3 here. And let's add these two numbers here. Now we are getting -2 as a result here. You can see here there is a minus sign in the result. Now in this case, the sign flag will be set due to this minus sign in the result. So whenever there is a sign in the arithmetic and logical operation, the sign flag will be set. So this was sign flag. Let's move on to the overflow flag. Overflow flag will be set when the arithmetic and logical operation result causes an overflow in the register. Let's understand this by a simple example here. An 8-bit register has the capacity of storing 127 signed number in count. But if we try to store more than 127 in this register, it will set an overflow flag to indicate there is an overflow in the register. For this example, let's take two input as 127 and 1 and try to store these two numbers in this 8-bit register here. This register causes an overflow. Because of this, overflow flag will be set here, indicating there is an overflow in the register. So that's the overflow flag working. Let's move on to our next flag, which is the direction flag. Basically, this flag is used to manipulate string movement operations. The direction flag controls the direction in which certain string operations move through the memory. So that's all about flags of the CPU. So that's all for now. If you have any questions regarding this concept, let me know in the comment section. I will surely help you. I will see you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. So in this part, I'm going to show you which operating system I'm going to use in this whole video tutorial series. So in order to follow this course, you have to use the Kali Linux 64-bit operating system. You can see here that I'm already logged into my Kali Linux machine. And let me show you the version of Kali Linux machine using the lsb release command, which I am going to use in this tutorial series. You can see here this Kali Linux version is 2023.3. Now let me show you the kernel version also using the uname command. You can see here the kernel version of this Kali Linux is 6.3.0. So in order to follow this course, you should use the Kali Linux 64-bit operating system. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. So in this part, we will look at memory layout of a program. So we will see how a program stores its data inside our primary memory when it is executed. So basically, this is the basic structure of our program memory layout when it is executed. So you can see here, the program store its data in these memory segments. So the first, you can see here, the first segment is this, which is command line arguments and environment variables. So program stores its command line arguments and environment variables here in this segment. Then we have our stack. So so all the temporary data of our program is stored inside this stack area, and all the dynamic data is stored. All the dynamic data which is needed when the program runs will be stored in heap area. And after that we have our .bss segment. In this segment all the uninitialized data will be stored. And in after that we have our initialized data segment called dot data segment, or you can say dot data section. So in this particular section all the initialized data is stored. In the last we have our dot text section. In dot text section all the executable code instructions of our program is stored. So this was the very basic program memory layout, and let me explain you further with the help of a simple C program. So you can see here on the left side, this is a very simple C program. In this C program you can see we have few variables and we have a main function here. We have main function and we have like two variables here, int a, int b. Then we have main function, and in main function we have only return 0. So let me explain you all these parts with this particular, like with the help of this program. So let me first clear all the sketches. Now moving on to the first line. In this program, in this C program, this first part, you can see this first part, this is int a, means integer a. So this is uninitialized data. So this is uninitialized data, and this uninitialized data will be stored inside this particular area, memory area, which is called .bss. This is called .bss segment, or you can say section. So all the uninitialized data will be stored here. So this int a will be stored here. Now after that we have int b equals to 4, because this b is initialized here with value 4. So this is initialized data. So this initialized data will be stored in this particular memory segment, which is called .data segment. Now remember this, we have declared these two variables globally here outside of main. So these two variables are stored accordingly, like all initialized values will be stored in .bss and initialized data will be stored in .data section. So after that we have our this main function. You can see here, let me change the color so that you understand easy. So this is our main function. After this we have main function. In main function all the arguments of main function, this part will be stored here. All the command line arguments of this main function will be stored in at this place, at this particular memory area. You can see here command line arguments and environment variables. After that all the temporary data of our main function, means all this main function temporary data, all the temporary data of this main function body will be stored inside this stack. All the temporary data of this main function will be stored here, like the input values, like the local variable values. When program is loaded inside the RAM, all the local values will be stored in stack. Now let me clear the screen so that we can move forward. Now in the last, like we have covered this command line arguments, we have covered this stack, we have covered this .bss, then .data. Now the only thing which is left is this text section. Now in this text section all the executable instruction code instructions will be, all the executable code instructions of this main function will be stored inside this .text section. All the executable code instruction, or you can say machine instruction of this main function will be stored in .text section. And all the dynamic data, like all the dynamic data will be stored here in heap when it is needed. When the dynamic data is needed, all the dynamic data will be stored in the heap. So the only like the important parts here, like in like the important memory sections which is important to write assembly programs are this .bss section, this .data section, and this .text section. So we will need to know these three parts to write assembly programs and to understand assembly programs as well. So you have to focus on these three parts, .bss section, .data section, and .text section here, these three parts. So let me explain briefly again. In uninitialized data, all the uninitialized data will be stored. This is uninitialized data, you can see this is not initialized, and this is initialized data. So this initialized data will goes here in initialized .data section. So let me write here very simple. So this data will goes into .bss section. .bs, my writing is very horrible, so let me indicate you. This data will goes here and this data will goes here. So this is very simple part. So these three parts are very important: .bss section, .data section, and .text section. In .text section, all the executable code of our main function will be stored, and in these two parts, all the uninitialized data and initialized data will be stored in .bss and .data section. So that's all for now, and I will meet you in the next part. If you have any problem, confusion regarding this, let me know in the comment section. I will surely help you. So till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you the basic structure of our assembly program. So you can see this is our Kali Linux terminal, and in the right side you can see there is a picture. So this is a picture of our memory layout. So I have opened this memory layout picture here because it will help you to understand the structure of our assembly program. So let's write our assembly program. So I'm using Vim editor here. So Vim space, then the name of our assembly program. In this case, I'm naming it assembly.asm. So .asm is the format for assembly source files. So .asm. Hit enter. Now we are in the Vim editor. Let's press I to input something, to write something in this file. So let's first create our data section first. So this section, let's create this section first, this .data here. So to create any section, we have to use this section keyword. Then space, then we have to mention the section name here. So in this case, which section we want to use, we want to create this .data section. So we have to specify here .data. So we have created our data section here. Like the same way, if we want to create this .bss section, then the same way we can create our .bss section using this section keyword, section space then .bss. So we have created two sections. Like the same way we can create our text section also. Text section means this section. So we have created these three sections. After that, we have to create our entry point. We have to create our entry point in our assembly program. So to create our entry point, we have to use this global keyword. we have to use this global keyword. Global space, global means we are specifying which is the, like, what is the entry point for our assembly program. Like in the C program, when we write C program, we should write the main function. We always write main function. In main function we write all the program code. Like the same way, the main function for this assembly program will be our start label. This is a start label. This is called a label. You can say just like the function name here, but in assembly this is called label. So we have to specify the entry point. So in this case we are just specifying that this start is the entry point for this program. After that we should create this label, you can say this label body, or we should define this start label here. So we are just defining here this label. So we are just like, first we have mentioned that the entry point for our for our assembly program is this is the entry point, and after that we are just defining this particular entry point here. That's it. So using this global keyword, it will tell that, like, it is asking us that what is your entry point for this program. So we should mention the entry point by using this label underscore start. Then we are just defining this particular start label here. So this is just a very basic assembly program, and we have not written anything extra. Like we have not written any single instruction in this program. We have just declared our data sections only. We have declared our memory sections here, like data section, bss section, text section, and in this text section we have defined our entry point, start entry, this start label as an entry point. That's it. So let's close this file. Let's overwrite this file by using wq and then hit enter. Now our assembly program is ready to be compiled. This is our assembly program. Now after this we need to compile this program. How we can compile? We have to use this YASM utility. So in your case, first you have to install this file. So sudo apt install YASM. You have to use this command first in order to install this utility. Then after you can compile it using this command. So YASM space then -f for format. So I want the output in 64-bit format. Then we have to mention our source file assembly.asm, and that's it. Now you can see that we got our object file assembly.o. So this is our object file. So we can link it by using ld command. So ld space, then we have to mention the object file here assembly.o. Then we have to specify the object file name, the output file name. So you can use -o for output. So this is our output file name. Right now we have successfully compiled and linked our assembly program. So this is our assembly program. You can see in green color. So if we use file command to find out which type of file is this, you can see that this is ELF 64-bit executable file. So we have successfully created our assembly program in this particular video, and this is very simple assembly program in which we have created different memory segments. You can see we have created .data segment, .bss segment, .text section, and in .text section we have mentioned our entry point, this start label as an entry point here. That's it. So that's all for now, and if you have any confusion regarding this concept, this particular concept, or regarding this video, the concept of these, like these source code, like if you are like if you have any confusion regarding this, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I'm going to show you the concept of system calls. So before going into assembly programming, we should know how system calls work in our programs. So basically I'm going to give you some examples in which I can prove that system calls are used in every programming language, whether it is assembly programming, whether it is C programming, whether it is Java programming, whether it is Python programming. Everywhere system calls are used to do different tasks by the operating system. So let's begin. So this is my terminal, you can see here. So let's first create a simple C program which prints hello world. Let me go into temp directory, and let's create again a simple temp directory, and let's go into this temp directory. So let's create a simple hello world program in C. So hello world.c, and let's input is like let's write some code in order to print hello world. So hash include stdio.h, then int main, then let's use printf to print hello world, Now let's return 0 here, and that's it. So this is our simple program which prints hello world in C program. So let's write this file, and let's compile this hello world file, hello world, and in output let's name it hello world. Now our file is compiled, and you can see we have our hello world. Now let's run it using hello world. You can see it is giving us hello world message. Now it is printing hello world. Now if we want to know how it is printing, we want to trace all the system calls inside this program, we can use strace utility. So if you don't have like strace utility installed in your system, so first you need to do sudo apt install strace like this and hit enter. It will install strace in your system, in your Kali Linux, but in my case I have already installed it. So strace is used to trace system calls of any binary, any given binary. So in my case I am using strace to find out, like to trace all the system calls inside this hello world binary, So let's use -c option. -c means I want to list all the system calls which are used in this hello world program. So let's give this program name hello world, hit enter. Now you can see it is giving all the different information here. You can see this is the time, this is the seconds, this is the like use sec call, and this is calls. So the important columns here is this calls and this system call. You can see these are different system calls used in this particular hello world program. You can see read, write, close, memory map, memory protect, memory unmap, brk, means you can see this is the whole list. So these are the system calls which are used in this hello world program to print just simple hello world string. Now you can see here it has used this write system call one time. It has used this one time write system call. So in order to print something, system uses this write system call. System uses write system call to print something, and we have printed hello world. So to print hello world, system used this write system call one time. We can go further and we can trace how our program, this hello world program, used this write system call. So we can do that by using strace. Let me clear the screen first. We can use strace. Then we can directly mention the program here and hit enter. You can see, let me maximize the screen. You can see this is the whole output, like this is the output of that command. And you can see here the important part is in the last, it has traced every system call from the startup. You can see execve, this is a system call, this is the system function. It is also like a system call which is used to execute any binary. In our case, we want to execute this hello world binary. This is the hello world binary which it is taking as an input, and it has executed. After that, we have several, we have many system calls which are used. You can see memory map, then access, then open at, something like that. But we want to know where is our write system call. Like this hello world is using a write system call to print something, like to print hello world. So in the last line, you can see here, focus on this line. In this line, you can see this write system call is used to print this hello world. You can see this is the function, like this is the you can see all the arguments for this write system call here. You can see, so write system call is using 3 arguments here. You can see this is the file descriptor, which is 1. 1 means if you want to print something onto the screen, you should mention 1 here, like this is the file descriptor to print something. Now after that, we have our string. It is taking input as in string. After that, it is taking the number of characters, or you can say number of bytes here. So you can see this is total 12 bytes. So here it is 12. So now this program is using write system call. So the first proof of concept is that our hello world, our simple hello world program is using a write system call. So this is a write system call which is used by this hello world program in C. Now this was C, which is using a write system call to print hello world. Now after this, let's create a simple Python file. Let's create Python file. Like in Python, we want to print hello world as well. So let's create that. So let's name it hello world in Python, python.py. It's very big name. Let's choose small small name. hello.py, just simple. So hello.py, this is our Python file. In this Python file, let's print hello world. Let's print hello world. So this is the syntax, a very simple syntax in Python which prints hello world. Let's write and quit. Now our Python file is ready to be executed. We can execute it using this Python command, python then hello.py. You can see it is printing hello world. Now let's find out whether this Python is also using our write system call or not. To do that, again we have to use strace command, strace hyphen, not hyphen, but strace. We can give this executable, like not executable but this script file directly. So we have to mention the Python here, Python command here to execute this particular file, to this to execute this Python file here. So strace space, then this is the Python program which executes this Python script file. So Python space then hello.py, and just hit enter. And this is the like very you can say big, huge output. We can filter this output by using grep filter to know if it is using write system call or not. So let's clear the screen first and let's execute the same command, strace space python then hello.py, and after that let's grep out the result. So let's use write filter, like this write system call filter. So all the write part will be filtered in the output. So let's hit enter, and it is still doing the same thing, and maybe we can find out it manually. It is not working. I think it is creating sub process, that is why it is not working like this. Maybe let's put F like F option here, and let's see. No, let me clear the screen and let's do something else. Let's redirect all the errors and all the output into one place, and let's see. Okay, now we have got what we want. So now I have used -f option. -f means like it means that strace will follow all the child process which is created by this Python file, like which is executed by this Python file while it is executing to print hello world. Right now you can see you can see here that this Python file is also using write system call here. You can see write system call, right? Then this is the file descriptor, like which is used to print something onto the screen. So this is the first argument. Now this is the second input. You can say argument, you can say input for this write system call. So this is the string which we want to print, and this is the third part, which is the number of bytes which we want to print onto the screen. So this is the system call. You can see this hello.py means this Python file is, this is just a simple script. You can see here, this is just a simple script, but this script is also, when we execute this script is also using the write system call to print hello world onto screen. So you can see C was also using the same write system call to print hello world. This Python file is also using this same technique, like it is also using this write system call to print hello world. Now let's use a simple Java file, like let's create a simple Java program for printing hello world, and let's see if that Java file is also using this write system call or not. So let's do that. Let's clear the screen first and let's create a Java like Java program. So hello.java, and let's write some code. So first we need to create a class. So class hello. So this is our class, and after that we have to use public static void main, and in void main we need to supply our string. Then we need to use system dot out dot println. Then in this we have to use hello world, and then let's close our brackets, not bracket but curly braces. So this is just a simple Java program which prints hello world, message. Let's write and quit this, and let's execute this Java program using Java command. So Java hello dot Java. So there is error, expected public static void main. Let's correct that error. What should be there? I think it should be strings, not strings, but maybe okay. So the error was I have not given args here, like argument variable. So args, then let's write and quit, and let's execute this Java file, hello world Java file. You can see this Java file is also printing hello world successfully. Now let's trace all the system calls of this Java file as well, and let's see if this Java file is also using write system call or not. So to do that, we can use the same technique like strace utility, and then we use f option to follow all the child processes created by this Java file, this Java program. So -f, then we have to mention our we have to mention our program to execute this Java files. In this case it is Java, so it's Java space, then we want to execute this hello.java, and then we have to but first we have to redirect all the errors and all the output at one place. So 2 is for redirection, 2 is used for all the error part. 2 is the file descriptor for error, error output. So 2, and then we need to redirect all the errors at one place, which is here 1. Like 1 is a standard, 1 is a file descriptor which is used for standard output. So don't confuse here, it is just we are using this to redirect all the errors and all the general standard output at one place, so that we can filter out our write system call from that output. That's it. Now after that, let's grep out our write system call in this output. So let's find out if write system call is used in this Java file or not. Hit enter. You can see that in the last part, you can see this write system call is used here in this Java file as well. So Java program is also using this write system call to print hello world. So what this concludes? This concludes that in every programming language, whether it is C program, whether it is Java program, whether it is Python program, all the programming languages are using write system call in the end. Ultimately they are using write system call. And let me show you one by one all the outputs of C, Python and Java at once. So let's first use strace space, then let's use f sign, and let's use our first hello world. This is C file, so hello world. Then I want to let's use the same thing, 2. Then I want to redirect all the errors and output at one place, and then I want to grep write system call. You can see this is the C part. This C program is using write system call. Let's do the same thing with our Python file as well. So Python space, then our Python hello world Python file. So hello.py, I think, yes, it is right. Now you can see this Python is also using a write system call. Now in the last we can use our Java program as well. So I am using Java to execute our hello.java. So you can see in these three cases, this is C, it is using write system call. It is Python file which is also using write system call to print hello world, and in Java, this is Java, and Java is also using a write system call to print hello world onto the screen. So finally this is proved that system calls are used by these programming languages. Any programming language, like if you use any programming language to print hello world, ultimately it will use write system call by the operating system. So while like in the next part, when we write hello world program in assembly, we need to use this write system call directly to print hello world. That is why that is why I am explaining you the system call concept, because this is needed for you to understand that like how the system calls are used by different programming languages. So this system call is needed to, like, we should have a clear concept of system calls. So that's all for now. This was the basic concept of system calls before writing hello world in assembly. So in the next part, we will use this write system call directly to print hello world in our assembly program. So if you have any questions regarding this concept, let me know in the comment section. I will surely help you. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how you can write hello world program in assembly. So before writing hello world program in assembly, we need three most important information. Here you can see we need write system call number. The first important part is write system call number. We should know what is write system call number. Then we have to find out all the input parameters for this write system call. And in the last, we have to find out how we can store all the input parameters of this write system call. So these are the three most important parts, like you can say information, which we will need in order to write our hello world assembly program. So let's find out all these informations one by one. So first, write system call. So in order to find write system call number, we have to use this file, header file, which is unistd_64.h, and this file is located inside this particular directory. You can see here user include asm. So let's open our Kali. So this is our Kali Linux, and let's use less command to find out our write system call number. So less user include, then asm, then unistd _64.h, and in this file you can see this is all the list of system calls, and you can see here this is the system call number: read, write, open. These are the name of the system calls, and after system call name, these are the system call numbers. So for read, the system call number is 0. For write, system call number is 1. So this is a huge list of system call numbers. So in this case we want write system call number. So you can see write system call number is 1. So we have found write system call number is 1 here. Let's close it. Let's move on to our next information which we will need in this case. The next information is input parameters for the write system call. How we can find input parameters for the write system call? It's very easy. We have to use man command for this. We have to use man command. Man means manual. In Linux we use manual command like man command to see the full documentation of any system call. So you can see we are using this number 2 space then system call name. So let's do this. Let's do this to find out all the input parameters of this write system call. So let's do that. So let's clear the screen first and let's do man2 then write system call name, which is right here. And you can see, let's minimize this. You can see here that in this output we have to find out the input parameters for write system call. So you can see here clearly, focus on this part. This is the definition of write system call, and you can see in this write system call it is taking 3 inputs. The first input is file descriptor. You can see int fd. This is file descriptor, and the second input is our buffer pointer. You can see constant void buffer. So this is our buffer pointer. This is the second input, and the last input is size in count. So these are the 3 inputs which is taken by this write system call. So now we know that this write system call is taking 3 inputs, and in these 3 inputs the first input is our file descriptor, which will be 1 in this case. Generally if we want to print something onto the screen, then we have to use 1 here. So this will be 1, and the second input parameter will be the buffer pointer, our string buffer pointer. In this case this will be our string buffer pointer, and the third will be the count of bytes which we want to print onto the screen. So these are the 3 input parameters for our write system calls. So let's clear this screen. So we have found the second information. Now let's move on to third part. Now the third part is where to store the input parameters of write system call. So where we want to store these inputs into our assembly program. So it's very easy. Let's move on. So you can see here we can store our write system call input parameters into these registers. You can see RAX, RDI, RSI, RDX and R10. These are the registers in which we can store these input parameters. So you can see here system call number will be stored in RAX register. Like we have to store system call number into RAX register. Remember this. Like the same way, our first input parameter of our write system call will be stored in RDI register. Our second input parameter will be stored in RSI, and the last input parameter will be stored in RDX register. So this is how we will write our hello world program in assembly. So let me show you the the graphical, like not graphical but easy representation to understand this part. You can see here this is our write system call number 1. So this 1 will be stored in this RAX, which is system call number. You can see system call number will be stored in RAX. You can see here system call number 1. After that we have to store the first file descriptor. Like we have to store this write system call first input parameter, which is file descriptor. You can see here, focus on this part, file descriptor. So this is file descriptor which is stored in RDI register, which is first input parameters in our case. So this will be stored in RDI. Next we have to store buffer pointer, our string buffer pointer, into RSI here, and in the last we have to store our count in our RDX register. So we have to use this same concept in order to write our first hello world program in assembly. So that's all for now. If you have any question regarding this concept, please feel free to write in the comment section. I will surely help you. And in the next part, I will take these information and I will show you how we will use this information to print hello world in our assembly program. So that's all for now. See you in the next part. Till then, goodbye. So hello everyone and welcome to the next part of this tutorial. So in our previous part, we have collected these information, right? Like we have collected write system call information, which we will need in order to write our hello world program in assembly. So these are the information which we will need in this case. We have our system call number, which is 1, and all the input parameters. You can see here we have 3 input parameters which should be stored in these registers in our assembly program. So let's implement this in our assembly program practically, and let's print out hello world message on our screen. So let's clear the screen first and let's create our program hello world.asm, and let's input our code here. So first let's let's declare our data section here by using .data section, by using .data here. And after creating data section, what we need to do, we need to define our string here. We need to define our string variable here first. So let's define our string here. So let's name it hello string, and then we have to specify the data type here. So in this case, D and B. D means define, and B means byte. So define bytes. So we are defining bytes here. So then we have to use space here, and then we have to write our string here. So hello world, which we want to print here. So we have to use 0 here, comma and 0. Why 0? Because we want to break the line. After printing hello world, program should break it, like program should create a new line so that it looks better on the screen. So after creating our hello string variable, then we have to move on to create our text section here. So we are creating our text section. In text section, first we have to specify our entry point here. So in this case, we use global keyword here, and then we have to specify the entry point as a start label. Always the entry point will be start, like in the C program its entry point was main. So let's implement our start body. In start body we will write our assembly code, like instruction, all the instruction. So first let me introduce you how you can comment in our assembly program. So in order to comment, if you want to comment something, you can use semicolon here, like this. This is semicolon, and then you can comment out your message here. So I want to comment here like move, not move, but yes, move system call number in RAX register. So first we have to move system call number in our RAX registers. How we can move that? We use move instruction here. So in assembly, this is very common and very useful, we use often move in our assembly programming. So move means move from source to destination, move something from source to destination. So we want to move system call number. You can see we want to move system call number into RAX. So how we can do that? We want to move system call number in RAX. So first we have to define the destination here, where we want to move. So in this case we want to move into RAX. What we want to move? We want to move system call number, which is 1 here. So you can see here we are moving this one. Oh shit, my drawing is not very good. So let's, oh, not that, but yes, it's okay. Now this one, look at this one, this one will move into this RX. So this is a move instruction. The working of this move instruction is to move data from one place to another place, means from source to destination. It moves data from source to destination. In this case the source is our this one is our system call number, this one is our system call number, this is our source, and this RX register is our destination. In this case it's very simple concept, nothing like complicated here. We are just moving this one into RX. Like it looks like this is looking in reverse direction, you know, from right to left direction. Data is moving from right to left. You can see this arrow. So let's clear these sketches and let's move on. So we are just moving, like we have moved this one into RAX, like system call number. Now after that what we have to do, we have to move first input parameter of write syscall. So the first input parameter of write syscall was file descriptor, which is 1 in this case. Let me comment it here. So first input parameter is 1, which is FD, means file descriptor. This is file descriptor. So let's move it. So move, and let's open our slide for our reference, for our help. You can see this file descriptor should be moved in RDI. So we have to move this FD into RDI. So let's move it. So move let's move FD is 1. So this one will be moved into this RDI register. So our second, the first input is moved, and let's move our second parameter. Let's give some space. Move second input. My typing is horrible. Move second input parameter of write syscall. So second parameter is let me tell you here by comment. So second input parameter is hello str, hello string. So our second input parameter is this hello string. Let me use sketch. So this is our second input parameter, hello string. So we have to move this hello string pointer into our next register. And how we can do that? Let me show you. Let's move our second input parameter using move command again. Move, then the destination. First we have to specify the destination where we want to move. So we want to move in our next register, which was RSI. You can see buffer pointer should be moved in RSI register. So let's use RSI register here. So move into RSI, and what we want to move? We want to move this hello str. So we have to write, when we want to move any address of a variable, we have to use square brackets. So in square brackets hello str. So this way we are moving the address of RSI. And right now we don't have to use move instruction here. We have to use something else. So in order to send the address of this hello string into this RSI, we have to use load effective address, LEA. This is this is also an instruction, but it loads the address of a particular location into this RSI register. So we have used LEA. LEA means load effective address. LEA, load effective address. So we are loading the address of this hello string into our RSI. Now after this, the next input parameter should be moved into RDX. The third input parameter should be moved into RDX, which is count. So let's count our string length. So 1 2 3 4 5 6 7 8 9 10 11. So total 11. So we want to print 11 bytes here. So let me comment it. Move third input parameter of write syscall. Now we have to use move here, and we have to move this third input into RDX. You can see here. So we have to specify RDX here, and what we want to move? We want to move the count of this bytes we want to print, which we want to print on the screen. So in this case it is 11. Oh, not here, which is 11 here. Let me decrease the size of font. Okay, so you can see we have moved the third input parameter of write system call, which is the count, the length of this string in bytes. After that, we have to use we have to use a new instruction called syscall. Why this syscall? Because by using this syscall instruction, we are telling the system that please execute this system call. Please execute this system call which we have written here. What we have passed here as a first input, second input, and third input, we are telling this system call number to the system. By using this system call, it means that it will take all these information and execute this system call inside the system. So we have to use syscall in the last, so that the system knows that this system call is to be executed here. So by syscall, we are executing this hello word, not hello word, but this write syscall in the memory, in the operating system. So let me write a comment here. So you execute, not execute, but used to execute the system calls. So syscall is used for executing system calls, and that's it. Our program is complete. Let's write this and let's compile it by using YASM utility, YASM, then -f for format. In this case, I want it into 64-bit format, and let's pass our source file ASM and hit enter. Now we should get our object file here. You can see hello world.o. This is our object file which is generated by this command, like by this YASM. So right now we have our object file. Let's link it using ld command. So ld, then hello word, and then object file.o, and in output we should mention our output file name. So hello world. Right now our hello world binary file is ready to be executed. So we can execute it by using this directly by we can execute this hello world right here. So let's execute this command, hello world, not command but binary file, and you can see it is printing hello world. It is printing hello world, but after hello world you can see there is a segmentation fault. Why there is a segmentation fault? Because we have not, like, the program is not able to exit properly. There is no method, like there is no method in this program to exit normally, safely, you can say. That is why it is like it has this segmentation fault error. We can uh, we can uh, we can like we can implement exit function, like exit system call, to remove this fault here in this program. So how we can do that? Let's open our source file and use exit system call to exit this program normally. So vim hello world.asm, and here in the last line use exit syscall. So we have to use exit system call. So in this case, in exits, like to use exit system call, we should know the exit system call number. How like we don't know right now what is the exit system call number here, and what is the what are the input parameters for this exit system call. So for that, let's use our technique which we have already done in our previous part. So let's use this file user include asm, then un, sorry, not this, but unistd td underscore unis td underscore 64.h, and in this listing we have to find out exit system call. Like it seems like it is very long list, but what we can do here, we can filter out by using grep then exit, and you can see the exit system call is the exit system call number is 60 here. So we have to use this number as the system call number, and after that we have to find out the manual page for this system call to know like how many like input parameters does it take, and what is the definition of this exit system call. So man2 then exit, and you can see this is the documentation of the system call, and you can see clearly here that it is taking only one input parameter, which is just a status, which is just a status, which is in integer form. This is just a number. So it is taking a number as an like input, which shows this the exit status in this case. So we can give this as a 0 here. 0 will be the exit status for that, and we can use this system call. So it is taking only one input. So let's do that. It's very simple. Let's clear the screen first and let's quit. And right now we have both information, system call number for exit and the number of input parameters. So let's implement that vim then hello world.asm, and let's use. So first let's move system call number in RAX register. First we have to move the system call number in RAX register. It's very simple. So we use move, again move command, then RAX, then the system call number. So system call number for exit is 60. We already know, we have found from that particular command, from that particular header file. So 60. Then after we have to move first input parameter, parameter for exit. So in this case we can we can move the first input parameter. Like exit has only one input parameter, and that is return value. So we can move that return value 0 into RDI here. You can see in our write system call, first input parameter was 1, and we have moved this one into RDI. This is the first input parameter. Like the same way we are moving this exit input parameter, which is only 1 here. So first input parameter for exit is moved into RDI. You can see this was the RDI. Here it is also an RDI. So this rule will not change for every system call. So this rule is applied to each system call in the Linux system. So we have moved this 0 into RDI as a return status for this exit system call. And after that, what else is needed? On the only thing which is needed is to execute this system call using syscall keyword or syscall instruction here. So syscall, and then just write and quit. So we have implemented the exit system call after write syscall. So let's write and quit, and let's again compile it using YASM, then -f and ELF64. Then we have to provide the source file, hit enter, and our object file is generated. Like it has overwritten this object file and created new. And after that, what we have to do, we have to use LD command to link our object file and to generate our object file into binary file. So LD, then in the source we have to provide the object file, and in output we have to mention the output. So hello_word. Right now we have our binary file generated. It has overwritten this old file with the new one. So let's execute this and let's see what will be the output. You can see this time there is no segmentation fault at all. It is just printing very clean hello world. There is no problem this time. Why? Because we have used exit system call after write system call. So program is exiting normally. So that's all for now. This was hello world program in our assembly language. And if you have any question regarding this video, let me know in the comment section. I will surely help you. And that's all for now, and I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can define data in our assembly program. So let's start. So first I'm going to show you how we can define bytes. So this is the basic syntax. You can see this is the very basic syntax to define bytes. So in this syntax, you can see this is the first part. In this first part, we have to mention the variable name in the first part. So this is the variable name. Then we have to use a colon here, and then after space we have to use this db, means define byte. So we have to use this db to mention that we are defining bytes. So db, d for define, b for byte. So define bytes. So we are going to define byte. So this is db, then space, then we have to assign data after that. So totally we have three parts here: variable name, and this db means define bytes. This is a kind of data type here, and after that our data, which is to be stored in this variable name. So this is the basic syntax of defining bytes here. So let me show you a simple example of this syntax. So this is our example. You can see in this example, first we have defined our variable name. You can see my string. This is our variable name, and after that we have used this db. This db is for define bytes. So we are defining bytes. That is why we have used this db. And what are the bytes? So we have assigned our data into this my string variable, and the data is test string. You can see this part. So this is our data. So we have assigned test string into my string variable. So these are like the total bytes are 11. So we have assigned 11 bytes to my string. So we have 11 bytes which is stored in my string here in this example. So like the same way we can define a word also. Word means 2 byte. A single byte is a byte and 2 byte is a word. We call it word. So we can define word also by using the same syntax, but there is a single change here. So the syntax is still the same here. First we have to mention our variable name here, then we have to use a single colon, then after that we have to mention this data type here. So data type is define word, dw. This w is for word. So like by using this dw, we are specifying that we are defining a word here, and after that we have to assign the data here. So this is the very basic syntax for defining word, means 2 bytes, 2 byte units. So let me show you a simple example for this. So this is our example, and you can see we have defined, like first we have created our name, like our variable name here, which is number in this case. So this is the variable name, you can see here, number. So number is a variable name. After that we have used this dw to specify that we are defining a word here, and after that we have assigned data. You can see I have assigned 2 data here. The first data is 3, like I have assigned 2 decimal numbers in this case. So first decimal number is 3 and the second decimal number is 4 and 5, means 45. So first 3, like you can see this is the first number. This first number is stored in 2 byte memory space. You can see the space for this number is 2 bytes. In this 2 byte this 3 is stored, and in this 2 byte this 45 is stored, 45 is stored. You can see this comma here, I have used comma. Like you can store further, like you can add other numbers as well, like 3 comma 45 comma something else. So each unit will be of 2 bytes. Each memory unit will be of 2 bytes space. So this is define word, like we have defined word. So this is single word, this is single word. If you count all these data, like if you count the length of this like these 2 data, it will be 4 bytes, because 2 bytes plus 2 bytes, it will be 4 bytes. So don't get confused here. This is single unit, which is word. So we have just assigned 2 data here, like 2 numbers, 2 decimal numbers here, and each decimal number will take 2 byte of memory space. So this 3 is of 2 byte, and this 45 is of, like this 45 will be stored in this 2 byte memory space. It's very simple. Now after that, let's move on and let's define double word. Let's define double word. Double word means 4 bytes now. In previous part we have defined 2 bytes. Now we are going to define 4 bytes at once. How we can define that? This is the basic syntax. It's very easy. First we have to create our variable name here. Then we have to use colon here, single colon, then space, then we have to use this d and d. D and d means define, d for double word. So this d means double word, double word. So we are defining double word, and after that we have to assign our data. So let me show you a simple example here. So you can see we have defined number, like this is our variable name as a number here. So this is our variable name, then single colon, then space, then dd. dd means define double word. So in this case we have assigned 2 decimal values here, like 2 decimal data. like numbers. So you can see the first value is 3 and the second value is 63, and you can see this 3 will be stored in this 4-byte memory space. This 3 decimal value will be stored in 4-byte memory space because we have defined double word data here. That is why this 3 has 4 bytes of space, and this 63 will also have 4 bytes of space. So whatever you want to define, every single unit will be 4 bytes here. If you want to assign other number like 1000, or you can say 500, that 500 will also take 4 bytes. Each number will be stored in 4-byte memory space. So if we count these two numbers, like these two memory space, we will get 8 bytes of memory space. So this number will take 8 bytes of memory space when it is loaded inside the memory. So total 8 bytes. Why 8 bytes? This 4 byte plus this 4 bytes, because each memory unit is defined as double word. Double word means 4 bytes, 4 byte. So this was double word, and let's move on and let's see how we can define quad word. Quad word means 8 bytes. We call 8 bytes a quad word. So for defining 8 byte as a single unit in our assembly, we have to use the same syntax, but the only change is this Q. In place of D, we have to use Q here. Q means quad word. So we are defining 8 byte. We are defining 8 byte unit here. That is why DQ, define quad word. Q means quad word. And after that, we have to assign data for this particular variable. Now let me show you a simple example for this again. Now in this example, this is the variable name. You can see this is number, and after that we have our this DQ. D means define, Q means quad word. So we are defining quad word, and then after we have assigned data here. So we have assigned a single data here. 84 means 84. So we have defined this, we have assigned this 84 decimal value into this one quad word memory space, which is 8 bytes. So we have assigned 84 in this 8 byte memory space. It has 8 byte of memory space, and in this 8 byte we have stored this 84 decimal value. So if we want to find out how many byte does this number will take in memory, it will be 8 bytes. Now if we have defined two parts, if we define two elements here, two elements of this decimal number, like 84 plus some other numbers, then in that case, if you have assigned two data here, in this case this 84 plus something else, then that will take 8 plus 8, 16 bytes, because each unit of this data is 8 bytes, which is quad word. So 8 byte. So this is a quad word, how we can define quad word. Let's move on to our next part. In this part, I'm going to show you how we can define byte array, which is also called multiple bytes. If we want to define multiple bytes of same data, byte array means multiple data of the same data type. So in this case, we are going to define multiple bytes here. So the syntax is the syntax of this part is little bit different. First, we have to define we have to create our variable name here. Then as usual, we have to use a single colon then space, then we have to use this times keyword. We have to use this times keyword. Times means we want to create how many times something. We want to create multiples of something. So that multiple is called times here. So times, then space, the number of bytes. So this is the place where we are specifying how many, like this is this place where we are defining the number of elements here. So in this case we will define number of bytes which we want to create here. So number of bytes, then after that we have to specify the data type for this. In this case you can see here db means byte, so we want to define bytes here. And after that we have to specify the data here, which like what is the data which we want to define here. So let me show you the example for this. You can see we have like created the variable name first. Here you can see number, and in this number first we have to specify this like times. We have to use this keyword which is times here to indicate that we are going to create multiple bytes. We are going to create byte array here. So this is times, and how many times? 10 times. So this is the total number of elements of this array. So we are going to define 10 elements. We are going to define 10 elements of type byte. We are going to create, or you can define, we are going to create 10 elements of byte, of type byte. db means byte, define byte. And what is the data? This is the data, so this is 0. So we are going to create this 0 10 times. So we are going to create this 0 into 10 times, and you can see this is the actual representation what we have created here. So 10 times 0 means 10 bytes. So 10 bytes will be allocated, and in these 10 bytes, in these 10 bytes, this 0 will be filled in each byte. So this 0, whatever you specify at this place, it will be filled in these 10 bytes of memory space. So this is byte array. Now after that, let's move on. So let's see how we can define byte in our .bss section. So how we can define our data in our .bss section, which is also called uninitialized data. So let's see how we can do that. It's very simple. This is the syntax you can see here. First we have to define our variable name, then we have to use single colon, then space, then we have to use this special keyword which is res. Res means reserve. So this is reserve, and after that we have to specify the type of data unit here. So in this case it is B right now. B means byte. So we are defining bytes here. So reserve bytes. So in this variable we are reserving some bytes. So that the count, we have to specify the count also here. So we don't have to specify the data here. You can see this is uninitialized section, like the uninitialized data section. The data is not initialized here. So we have to just specify the data count here. So it's very easy. Variable name, then we have to specify the type of data, which is in this case byte, and we have to specify the data count here. Let me show you a simple example for this. And you can see here in this example, we have to specify, like we have created this variable name which is called number, and then we have just specified the data type here, which is reserve byte. We are creating byte here, and we have specified 10 here, which is data count. So we are creating 10 bytes. So we are reserving, not creating, but we are reserving bytes of count 10. So 10 bytes, you can see this 10 bytes is reserved. This 10 byte is reserved in the program. So like the same way, we can also reserve word also. We can also reserve word also in our BSS section, data section. So syntax is still the same. First we have to create our variable name here, then colon, then space, then we have to use this res keyword for reserve, and then just we have to mention the data type here. So we have to use w here. W means word, and then we have to specify the data count here. Let me show you a simple example for this. So in this example, you can see here I have defined number, then I have just mentioned the data type here by using res, then w. Res means reserve, then word, like I am reserving word here. So how many words I want to reserve? I have mentioned 2 here, means data count. So data count is 2, so I am reserving 2 words in memory. So you can see this is 1 word and this is the second word. Total 4 byte reserved, means 2 plus 2, 4 bytes are reserved, and each these are the 2 words. In each word we have 2 bytes, that is why it is 4 byte total. So we have reserved 2 words here by using res and w, means reserve words. So we are reserving words here. After that, we can do the same thing in for reserving a double word also. There is a mistake here. It should be not 2, it should be 4. Let me correct it here just for temporary. It shouldn't be 2 here. I will correct this after this video. Sorry for this. It will be 4 here. It should be 4 here. 4 byte, not 2 byte. So anyway, how we can define double word in our .bss section? The process is same for this also. First we have to define variable name, then we have to specify the type of data, in this case res, then d for double word, so reserve double word, and then we have to specify the data count here. Let me show you the example. So in this example you can see first we have created our first we have created our variable name, which is number in this case. Then we have to use this data type here, which is reserve d for double word, and in this case I have reserved 2 double words. I have reserved 2 double words. You can see here this is the first double word, this is the second double word. So I have created these 2 double words space in memory. So it is 8 bytes total. 8 bytes are reserved, and you can see 2 double words. Remember this one double word called one double word will take 4 bytes. So 2 double words will take 8 bytes. So this was all about how we can define our data in assembly program. So that's all for now, and if you have any confusion regarding this, let me if you have any problem or confusion regarding these concepts, let me know in the comment section. I will surely help you, and I will do some practicals on this part in the next video. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I am going to show you how we can define our data in assembly programs. So in previous part I have shown you how we can define our data in assembly, but that was only theory part. In this part I am going to show you practically how we can define our data in assembly. So for that, let's create our source file called data.asm in Vim. And first let's create our data section by using this section keyword, section space dot data, and then first let's define byte, some bytes, define some bytes. So in this case, let's define a string. Suppose we want to define a string name. So let's say let's first name our variable here. According to rule, first we have to give a name to our variable. For this, let's say my string, my underscore str. This is our variable name. So in this variable name, we are going to assign some bytes, some character bytes. For that, we have to use this db. db means define bytes. So we are going to define bytes, like we are going to store our data in bytes. So in this case, let's assign our data. In this case, let's say let's assign a, b, c, 3 characters. So a, b and c are stored in this variable, my string variable. So how many bytes it will take? It will take 3 bytes. You can see a, b and c. There are 3 bytes. So these 3 bytes will be stored in my string variable. After that, let's define a number as well in bytes. So how we can do that? My number. So we are defining just a number, and let's specify the data unit here, and the data unit will be db again, data byte, not data byte but define bytes. So we are defining bytes here. So let's see, I want to store a decimal value here. So decimal value is 5 here. So I'm storing this 5 into my number variable here. I'm storing this 5 into my number variable. Then after, let's define word. Let's define word. And I think you already know what word means. Word means 2 bytes. This was single byte. This is single bytes. In word, it is 2 bytes. So let's define our first word variable, which is a here. Let's name it a. And in a, we have to mention the type of data here. So in this case, we use dw, means define word. So we are defining word in a variable. So let's give a number. Let's give 2 numbers like 3 and 5. Not 3 and 5 but 3 and 7. So we have assigned these 2 numbers, like we have stored these 2 numbers in our a variable here. This is our variable name, which is a here, and in this a we have stored 3 and 7, and each of these numbers have have 2 bytes of memory space. So after that, let's define double word. Let's define double word here. So let's name our variable b here, and in this b we are going to assign some numbers, decimal numbers here. So first, before that, we have to mention the data type here. So in this case, d and d. D and d means define double word. We are defining double word here. That is why d and d. Then space. Then let's say I want to store 55 and just a random numbers 83. So we have just assigned these 2 numbers, 2 decimal numbers into this b variable. After that, let's move on to define the next data type, which is quad word. Let's define quad word. Quad word. Quad word means we are going to define 8 bytes. We are going to define 8 bytes. This double word means we have defined double word. Double word means it is of 4 bytes. It is of 4 bytes. Double word means 4 bytes, and quad word means 8 bytes. So we are going to define our quad word data type, and the name of this variable is C in this case, and let's specify the data type here. So in this case DQ means quad word. We are defining quad word here. So in this quad word, let's store let's say maybe 9. Let's store 9 into this quad word. So this 9 will be stored in the 8 bytes of memory space. So this is our quad word, and that's it. Let's write this file. Let's overwrite this file, and let's assemble this file using YASM. Then let's specify the format here, which is ELF 64-bit, and then we are going to use -L option here, because we want to we want to generate listing file, memory listing file. So let's use -L, and then let's name it data.lst. This is our listing file. Why I'm going to generate a listing file here, because I'm going to show you the memory layout, like the memory index layout of our defined data in our assembly program. So that is why I have used -L to generate our memory listing file, which is data.lst in this case. And then after that we have to mention our source file here, which is data.asm. So hit enter, and you can see we have successfully generated 2 files here. The first file is our object file, and the second file is our list file, which is data.lst. So this is our listing file, and let me show you how it looks like in my other terminal. So cat then data.lst and hit enter. You can see this is our listing file, and let me open our source code here, because we need that source code to reference our data from this listing file. So vim space then data.asm. So this is our source code of our assembly, and you can see this is our data.lst output. So you can see in this listing file we have different data, like we have different lines here. So let me show you, let me explain you the outline of this data.lst file. You can see this is our data section. You can see it is showing that section.data, which is exactly this part, section.data. So this is our, it is saying that .data section is starting from here, and after that this is our first, this is our first line which we have used here as an instruction. So this is our first line of instruction here, which is my string. Then you can see we have defined our my string variable here. So this is the first part where we have used our data unit, in this case db, defined byte, and then this is our data. So you can see all these parts, this is the right hand side, these are the instructions which we have used in our assembly program. You can see, so these are the variables and this is the data. So these are the variables. You can see my number, then A, then B, then C. So these are the variables in which we have defined our data. We have assigned our data. You can see 5. In my number we have assigned 5 here. In A we have assigned 3 and 7. And in B you can see 55 and 83. And in C we have 9 here. So in the right side, these are the our assembly code here. If you see in the left side here, this part, focus on this part, this whole column, you can see this and this. So this is the memory indexing. This column indicates the memory indexing, means the memory index from which our data is stored. These are the memory index at which our data is stored, which we have defined in our variables. So basically this ABC is stored at this particular memory index location. So it is starting from 0, and at this particular location you can see our A, B and C are stored. So this column indicates our data in hexadecimal formats. So this is our hexadecimal values of our data which we have assigned here to this myString variable, myString. So this A, B and C is this part. You can see 61, 62 and 63. 61 is A, then 62 is B, and then this C is 63. So this is in hex form, hexadecimal form. So this is our data, and this is the memory index. So it is starting to store from this 0, and it has stored 3 bytes. This is 1 byte, this is 2 byte, and this is 3 byte, like first byte, second byte and third byte, total 3 bytes. So it has stored our data starting from this 0 index, and it has stored 3 bytes here, and in 3 bytes we have stored 61, 62 and this 63, which is this ABC. And we have mentioned this is byte, like the data unit is bytes, that is why first, second and third byte. So these are the 3 bytes. After that you can see in the next line we have defined our number, my number, and in that in that variable we have defined only one decimal value, which is 5 here. So you can see here this is the memory index. So in memory index you can see 0, 3. If you count from 0, the fourth index will be 0, 3. 0, like if you start from 0, 0, 1, 2, 0, 1 and 2, that will be 3 bytes. In that 3 bytes we have stored ABC. After that, in the fourth byte, which is 0, 3 index here, from 0, 3 it has stored this 5 single byte value. This is single byte, which is in that single byte we have stored 5 here in my number variable. You can see clearly. Now after that, the next variable, which is A, in this A we have stored 3 and 7. Now the data type is word. Word means 2 bytes, and you can see after this 3 the program has stored at the fourth memory index. It has stored at the fourth memory index. What it has stored? Our A variable. Now in A variable we have stored 3 and 7. You can see 3 and 7, and if you look carefully you can see this is our 3, and our 3 is stored into 2 bytes memory space. You can see this is 1 byte and this is the second byte. So total you can see 2 bytes. This is 1 byte and this is 1 byte. So we have, because we have defined word as a data, like data unit, so that is why this 3 has taken 2 byte of space. You can see here this 3. So we have stored our 3 in these 2 bytes memory space. After that we have also stored 7 here. You can see this is 7. We can see the length of our byte is 2 here. This is our word, means 2 bytes. We are storing our data in 2 bytes memory units. So that is why this is the way how data is stored in our memory using these memory formats. You can say formats, or you can say what we define here, like we are defining word, because that is why it is giving this result. So we have defined 3 and 7 as a word here. After that, in the next line, our B is here, B variable is here, next variable is B. So this B, in this B we have defined 55 and 83. So like we have mentioned that our data is of type double word. Double word means 4 bytes. So this 55 is stored in 4 bytes of memory space. You can see here, this is our 55. If you convert 55 into hex, you will get 37. So this is 37. So this 30, like this 55 is stored in 4 bytes of memory space. You can see clearly here, this is our 4 byte memory space. You can see 1 2 3 4, so this is 4. So this 55 is taking 4 bytes here. After that, this 83 is taking 4 bytes here, total 8 bytes. So 4 plus 4, this 4 and this 4, total 8 bytes. So this b variable is taking total 8 bytes of memory space. Because of this dd, we have, like, because we have defined the data type as double word, that is why it is taking 8 bytes of memory space, 4 byte and 4 byte, 4 byte for this 55 and 4 byte is for this 83. Now the next variable c, you can see our next variable is c, and this, the data type of this c is quad word. Quad word means 8 bytes. So we have stored our 9 into this 8 byte of memory space. You can see this whole area, this is 8 byte, and in this 8 byte this 9 decimal value is stored here. The rest bytes are empty, not empty but filled with zeros. So this is 8 byte, and in this 8 byte this 9 is stored. So you can see how the data is stored, how our defined data, like what is the impact of our data in our memory area. You can see these are the effects by, like by using these data types here, dw, dd and dq, then db. So let's add our BSS data section here, and let's define some data in our BSS section, and let's see what is the effect of that particular like what is the effect of those data in our listing file, data listing file. So let's add something here. So let's define our BSS section, and first let's reserve. We cannot say define, we can say reserve here. So we want to reserve bytes. We want to reserve bytes first. So to reserve bytes, what we have to do, first we have to define the variable name. So in this case, let's name it var1, variable 1, and in this variable we have to first specify the type of memory unit. In this case, res, then b. We are going to reserve bytes, res for reserve, b for byte. Then I want to reserve 5 bytes. I want to reserve 5 bytes here. Then let's reserve some word here. So variable 2, and let's use resw to reserve words. So let's reserve maybe 2 words of memory space, and after that let's reserve double word. So how we can do that? Let's define first our variable 3, and let's use res keyword, res, then in place of w we have to use d here, which is for double word, and let's define again, let's define 2 double words, not 2 but 3 double word, and let's also reserve some quad word as well. Let's reserve quad word. So in quad words, let's first define our data, variable name, which is var4, and let's use res then q for quad words. So we are reserving quad words, so res q. Then let's reserve maybe 2 quad words, and that's it. And let's save it. Let's write this file, and let's assemble this again with the same options. you can see -l then data.lst. We are again generating our memory listing here. So hit enter, and right now let's open our file again, vim data.lst, not lst, sorry, my mistake. Let's open our data.asm here so that we can cross reference our outputs. So let's clear the screen and let's cat our data.lst, our memory listing file. And you can see this is our memory listing file. You can see this is our data section, and now this BSS section is added here in this our listing file. So this is our BSS section. So I already covered these parts. You can see we have covered these parts already. Now we are going to cover this part .bss, which we have defined here. You can see. So in the first part, you can see the memory indexing is starting from 0. So this is our memory indexing, which is starting from 0. So at 0, we have defined our variable 1 in our BSS section. So this is variable 1. So in variable 1, we have defined 5 bytes. We have defined 5 bytes. So 5 bytes is defined from this 0 memory index. So this is a gap. Gap means it is uninitialized data. That is why there is no data in our data section. We have data because in that part we have initialized our variables with some data. You can see these are the initialized data. These are the initialized data in those variables. But in our BSS section, we already know that it is uninitialized. These variables are uninitialized because these variables don't have any data. So that is why there is a gap. This is gap, means no data. There is no data here. Only the memory index and the variable name here. You can see this is our variable 1, which has taken 5 bytes starting from 0. After that, we have our variable 2, which is reserving 2 words here. 2 words means 4 bytes. So if you count from 0, 5 bytes, it will be 0 to 4 means total 5 bytes. After 4, at 5th location, at 5th indexing, our variable 2 is starting. Our variable 2 is starting from this 5th index, memory index. So we have stored 2 words. 2 words means 4 bytes total. So starting from 5, we have stored 4 bytes. After that, in variable 3, we have stored 3 double word. We have stored 3 double word. 3 double word means 12 bytes. 1 double word takes 4 bytes. So total 12 bytes. So we have stored, started storing 12 bytes from this 09 index. Like the same way, our variable 4, in our variable 4, we have stored 2 quad words. 2 quad word means 16 bytes. So we have stored 16 bytes in variable 4 starting from this memory index. So this is the memory indexing. So if you make some analysis on these memory indexes, you will find out that these bytes, these bytes are equally, these bytes are distributed according these memory indexing, because you can see here 0 to 5 means 0 to 4. There is here it is 0 to 4. Then after 0 to 4, at 5th location, it is storing. It is started to store variable 2 here. After 2 words, 2 words means 4 bytes. So if you count from 5 to if you add, if not add, but if you count from 5 till 8, not 8 but 4 bytes, 5, 6, 7, 8. After that, this is 9, 0, 9. So from starting from 0, 9, it has reserved how many bytes? 12 bytes. So if you start counting from 9 to 12 bytes, you will reach this 15. This 15 is in hex. This 15 is in hexadecimal format. So don't get confused. It is not a decimal here. It is in hexadecimal format. So you will get 15 here, and at 15 location in memory indexing, from 15 it is started to store this fourth variable. So this fourth variable we are reserving, in this fourth variable we are reserving 2 quad words. Quad word means total 16 bytes, 8 plus 8, which is 16 here. So this is how the memory layout works in our assembly programs. So this is just a static layout, like the program is not running. This is just a static layout, and this is how our data is stored in our assembly programs. You can see here both in data, like our data section and our .bss section, which is uninitialized data here. So that's all for now. If you are facing any kind of like problem, conceptual problem or technical problem, let me know in the comment section. I will surely help you. So till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how you can set the disassembly format to Intel syntax in your GDB debugger. So for that, you just have to open your GDB init file in your home directory in your Kali Linux. So this is Kali Linux, and in Kali Linux, what you have to do, you have to just open or create. So if you don't have this kind of file, GDB init in your home directory, then you have to create it by using vim. So you have to just type vim space then .gdb init, and then hit enter. So in this file, what you have to write, you have to write set disassembly to Intel. So you have to just write these 3 words, set disassembly then Intel, and you are all set. After that, you have to overwrite this file, and then after you have to exit. So this will set the disassembly the disassembly format to Intel syntax in your GDB. So this is very important in order to follow all the video tutorials in the coming videos. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can move our data in assembly programs. So in order to move data in our assembly programs, we need to use this move instruction. This move is an instruction. So we have to use this move instruction in order to move our data in assembly. So this is the syntax of move instruction. Here you can see, and in this syntax you can see this is our source and this is the destination. So this is our source data which we want to move at this destination place. So this is very simple syntax of move instruction. So let's see how this let's see how this instruction works in our assembly program. So let's minimize this and let's use this move instruction to move some data in our assembly program. So let's create a simple assembly program and let's name it move_data.asm. So this is our assembly source file. So in this source file, let's write some assembly codes. First, let's create our text section here, and then let's specify the entry point for our assembly program. So this is start. So our entry point will be start label here, That is why we have used this global keyword to specify the entry point. After that, let's implement our start label here. So first let's move constant values. Move constant values into registers. So for that, let's first move. This is just an example. We can move any constant values here. So in this case, I want to move a value into I want to move a value into REX register. So in this case, we can take a number like 7. So this 7 is called constant, or you can say immediate value. So we are moving this 7. This is our source. You can say, let me give some space so that I can explain you. So you can see this 7 will be moved into this REX register using this move instruction. This is very simple concept. So like the use of this move instruction is very simple. You have to specify source in the right side and the destination part is in the left side. In this case, we are moving this 7, this constant value 7, into this REX register. So let me clear the sketches. Now after that, we can move another constant value. Let's remove this space. So RBX, in RBX I want to move like 5. Like the same way we can move something in our RCX register. I want to move something like 100. So I want to move 100 into RCX register using this move instruction. So in these three move instructions, we have moved. In the first move instruction, we have moved 7 into RAX. In the second instruction, we have moved this 5 into RBX, then 100 into RCX using the move instruction. Now after that, we have to use exit system call here. We have to use exit system call because we don't want our program to be crashed. So if I don't use exit system call here, then what will happen? Our program will crash every time when we run. So we have to use exit system call here to exit the program normally. So exit system call. So I already told you about system calls. So to use exit system call, the two information is needed. The first information is system call number. So first we have to move the system call number into RX register. So the system call number for exit is 60 in this case. So we have to move 60 in RX register, and this 60 is system call number for exit. So this 60 will be moved into this RAX to tell the system that we are going to use exit system call for this program. And after that, we have to move our return value into RDI register, and return value will be 0 here. So let me comment out. So return value for exit. This is the kind of return status. So the return value for exit will be moved inside this RDI. So don't get confused here. This whole part is a system call. This is not a system call. This is just data movement. Here it is just data movement, and this is our system call. This is our exit system call, and this is the system call number 60, which is moved inside this RAX using move instruction, and this is 0, which is the status, like return status of this exit system call, which is moved into this RDI register, and this is the move instruction. This is very simple, so don't get confused here. So after that, what we need to do, after that, what we have to do, we have to use this syscall keyword in order to execute this exit system call. So we have to use syscall after every syscall arguments. So that's all, like that's all about this program. So let's write and quit, and let's assemble this program using YASM, and then let's specify the format by -f, and then let's give 64-bit format here, and then we have to specify our source file here, which is movedata.asm. Right now you can see object file is generated here with .o. Now what we need to do, we need to link it using ld command. So ld space, then we have to specify our object file, then our output file -o for output. So in this case I want to name it move_data. Right now you can see that move data is generated. This is our binary file, executable binary file. So in this case we can load that binary file into our GDB for some analysis. So first let me open our source file here so that we can cross reference our data. In this case this is .asm and this is our source file. So in the another terminal, like this is the same terminal, like this is also Kali terminal. So in this terminal we are going to use our GDB, and in GDB let's load our binary file. So you can see in this case we have this move data which we need to load in our GDB for analysis, for debugging. So let's use GDB-q, then move data, move_data. Now this file is loaded inside this GDB, and let's make some analysis on this binary file. So let's see if these values are, if these constant values are going inside these registers or not in our GDB. So let's disassemble our start label. Let's disassemble this start label, this part. So let's hit enter here, and you can see the this is the disassembly of our program. This is the disassembly, or this is the disassembly of our start label here, which is this is our start label. So these are the same, and after that you can see these 3 lines of instruction. So we have 3 moves here first. So these 3 moves are this, you can see these are the 3 moves, these are the same. You can see in the first line we are moving this 7 into this RAX. You can see here we are moving 7 into this RAX with move instruction. Like the same way we are moving 5 into RBX, we are moving this 100, which is hexadecimal value here, 0x64. It is converted in our disassembly. So 0x64 will be moved in RCX. Now after that, this part, these 3 lines of instruction, you can see here, these are the exit system call here. So this is our disassembly, and don't get confused, like every line I have cleared all these lines one by one. So let me clear the screen for now, and let's move on. Now after disassembling our start label and carefully understanding all these lines one by one, now after this we have to put a breakpoint on our start label. So we can put a breakpoint using B command here. So B for breakpoint. I have used short notation here, B. So B space underscore start. So let's put a breakpoint at our start label, and you can see breakpoint is set at this particular address location. You can see this is the 401000, 40 and 1000, which is this. So at this particular memory address our breakpoint is set. Now after that I want to display these register values. I want to display these RAX, RBX, RCX values while the program is running in each step. So what we have to do for that, we have to use display command, display, and I want to display RAX register while the program is in running state, and I also want to display I want to display RBX as well, and I want to display RCX as well while the program is in running state. Right now program is not running, program is loaded inside the GDB, but it is not running. So after that, after displaying these three values, these three RAX, RBX and RCX values, I want to display at least three instructions of our program where it is running. Like the next three instructions, we want to display the next three instructions which the program is going to run. What we need to do for that, we need to use the same command, display, and this time we have to use different command here. So we have to mention how many instructions we want to display, so how many lines of instruction here. So display, then let's suppose 2 instructions, not 2 but 3 instructions. I want to display 3 instructions, not $sign but 3 instruction here. 3 instructions of RIP. RIP means instruction pointer register. So wherever is wherever our RIP instruction is, I want to display 3 instructions from the RIP. I want to display the 3 instructions of 3 instructions from this RIP location, and you already know that the RIP contains the next instruction which is to be executed by the program. So don't get confused here. I'm just displaying the next 3 instructions of our program when it is in running state. Hit enter, and these are these are the errors, which is just normal because program is in program is not running right now. That is why these errors are coming here. So don't get confused. So it's okay here. So let's clear the screen by using Ctrl+L command, not command but keyboard shortcut. So after that, let's run our program, and you can see the right now program is running and the program is paused at this location. So program is paused at this location, and you can see this is our first display. You can see here, this is our first display. You can see 1. So this is RAX, and right now this RAX has value 0 stored, right? This the same way our RBX has a value 0 stored. In RCX we have 0 here. So all these registers have 0 values, and you can see we have used this command to display 3 instructions, means 3 lines of instruction starting from this RIP location. So right now this RIP is located at this memory location. You can see this arrow indicates RIP location, instruction pointer location. This is the RIP, means this RIP is pointing at this location right now. That is why it is showing 3 instructions. We have mentioned 3 instructions. 3 instruction means these 3 instructions, 1, 2 and 3. So these 3 instructions are displayed here. That is why we have used 3 instructions. If you want to display 4 instructions from this RIP location, from this particular location, it will display one more line here, adding one more line here. So I want to display 3 instructions here only. So that's why we have used 3 here. So after that, you can see that we are going to move 7, this 7 into RAX, and you can see this is our first instruction. In this instruction we are going to move this 7 into this RAX register. Right now you can see RAX is 0. So when this move instruction, this line of code execute, what will happen? This 7 will be moved into this RAX register. So this 0 should be changed by 7 in the next step. So let's run it. Let's execute this line of code by using next instruction, like ni next instruction, and for next I for instruction. So execute next instruction. So it will execute this instruction, this particular instruction where it is pointing right now, and you can see it has executed right now. This RAX is 7, and you can see now this pointer is moved at the next location. You can see the pointer is moved at the next location, which is here. Here you can see this 5 is going to move into RBX. You can see this 5 part. So we have executed one line here by using next instruction command. Right now this RAX has 7, and after this line, what will happen? This 5 will be moved into RBX. You can see here we have moved this 5 into RBX in the next line. So this RBX should be 5 in the next step. So let's use next instruction to execute this line of code. You can see right now RBX has 5. It was 0 before. You can see, because we have used this move instruction to move this 5 into RBX. Like the same way, our next instruction, you can see it is pointing here. Our RIP is pointing here at this part, at this line. You can see in this line we are moving this 100. This 0x64 is 100, which is in hex here. So this 100 is moved into RCX in the next step. You can see RCX is 0 right now. And let's use next instruction to execute this line. So you can see this RCX has 100. You can see. So we have moved all these three numbers into these registers. 7 is moved into RAX here. This 7 is moved into this RAX. This 5 is moved into RBX, and this 100 is moved into RCX. Now after that, this is our system call. This is our exit system call. You can see this part, exit system call. So these three lines of instructions are exit system call. So if we sorry, so if we continue here, the program will exit normally because of this exit system call. So this is the way how we move our data from one location to another. Not location here, but this is just a constant value. So we have just moved some data into registers. So we have just moved these constant into these registers one by one using our move instruction. So that's all for now. If you are facing any kind of trouble regarding this practical, let me know in the comment section. And if you have any problem regarding understanding of this concept, please let me know in the comment section. I will surely help you. So that's all for now. I will see you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can move data from memory into registers. So let's begin. So let's create our assembly program to demonstrate this concept. So let's create data.asm for that. And first, let's create our data section here. In this data section, let's create one variable, which is my string variable. So this is our variable, and the data type for this variable will be a byte. So for byte, we have to use db, means define byte, and let's assign data to this my string variable, and that will be this hello. So this is our data which is stored inside this my string variable, which is of type byte. So these bytes are stored in my string. Now after that, let's create our text section here, and in text section let's specify our program entry point using this global keyword, and this the entry point for this program will be start here, and let's implement our start label here. Now before writing any code into this start, first we have to understand how these variables looks like inside our primary memory. So when we create these variables in memory, in our primary memory, how this looks like. So we have to understand the concept of address and value here, because we are going to move addresses and values in our registers. So before that, we should know what is an address of a variable and what is the value of a variable. So let's understand it. You can see this is our variable, which is my string in this case, and this is the value of this variable. So in memory, what it looks like. So this is our simple memory representation of this variable. This is our memory. So in memory, whenever we create any variable, two parts are saved, like two things are saved in memory, in our primary memory. What are these parts? The first part is our address. The first part is address. So A double D means address here. So the first part is address. Now the next part is value. V-A-L-U-E, value. So these two parts are stored whenever we create any variable in our data section. What will happen? This address and values are filled with the data of this variable. So in this case, the address, like there is an address which is assigned for this my string variable. So address, let's suppose the address is like something like this, A, B, C, A, B and C. This is just an example. So this is an address of my string in this case. So address is stored and then value is also stored. So the value in this case is this hello. So this is a hello. This is a value of this variable hello. So we have just created this my string variable, this string, and what is happening inside memory? Inside memory, the address of this memory, like address of this variable is stored, and value is also stored in memory. So we have two locations here, address and value. At this address, this value is stored, and this address is my string, like this is the address of my string variable in this case. So this is the address of my string. So this my string contains two information here, address and value. So our variable contains two parts here, address and value. At this address, this value is stored. So this is the concept of address and value. So you should know address and value concept in memory before moving anything. So let's move. So what we want to move in this particular example, what we are going to do, we are going to move this address, the address of my string, into RAX register. First we move the address of this my string variable into RAX register. Sorry, this is not X, this is A, my mistake. This is RAX. So we are going to move address into RAX and we are going to move value into RBX. Value into RBX register. RAX. My drawing is very bad. So anyway, so we are like, our task is to move the address into RAX and value into RBX. Which address? My string address in this case. So let's do this. So let's move like we use move instruction. So move, then first we have to specify what we want to, like where we want to move. In this case we want to move in RX register. We already know here we want to move the address. First we want to move this address of my string into RX register. So RX, and then what we want to move, we want to move the address. So we have to specify my string variable here. You can see this is the name of my string. You can see my underscore string. So my string. So by using this we are moving address. Here we are moving address. Now the next task is we want to move value of this string, like of this variable, into RBX. How we can do that? Again we can, like we have to use move instruction, move, then we have to specify the destination, and in this case we want to move in RBX. So RBX, and we want to move the value in this case we want to move value, not an address. So what we have to do, we have to enclose the variable name with square brackets here, like this. You can see here this time we have used this square brackets around our variable. So you can see we are moving the value of my string. We are moving the value of my string. You can see here we have square brackets. Remember this part, this is very important. So we are moving the value into RBX here, and in this case you can see here there are no square brackets. There are no square brackets. If there is no square bracket, this means that we are just moving the address, not the value. So we are just moving the address of this variable, not the value. Remember this part, because this is a little bit confusing for the most for the most freshers who don't understand the difference between these two. So whenever there is an address, sorry, not address, but square bracket around any variable, it means that it is sending the value. It is sending the values, like it is moving the values. If there are no square brackets, then it means that it is sending the addresses, not values. So let me comment out here for you. So moving values, moving the value, not values. So we have just moved the address and value. So addresses are moved without square brackets, and values are moved using square brackets around the variable name. So let's first clear all the sketches. I think your concept is clear, right, like by now. And let's use our system call, or sorry, let's exit system call to exit our program normally here. So for that we have to move we have to move 60, which is system call number, into RAX. So syscall number for exit, and then we have to move the return value, or you can say return status for this. So we have to move that in RDI register. So in this case I want to move 0 here. So 0 indicates the return value for exit system call. So return value for exit, and then after we have to use syscall keyword to initiate the system call for this exit system call. So let's write this file, and in other terminal, in this terminal we are going to assemble this file first. So let's assemble it by using yasm. So yasm, then space, then this time we have to include the debugging symbol for this program. So for that we are using this -g option, -g, then dwarf 2. So this is just a keyword used here as an option, like specifying that this dwarf is specifying that we are just including, like, generating all the debugging symbols for our program, and that's it. There is no more like confusion should be here. So -g is used for including the debugging symbols which we use in our GDB program. So after that we have to specify our format, in this case ELF 64-bit, then our file name, in this case source file. So source file is our data.asm, I think, if I'm not wrong. And you can see that we have successfully generated data.object file. You can see here, this is our object file. Now after that we have to use ld to generate our final executable file. So ld space data.o as an input, and in output let's name it data. Now data is generated, data binary file is generated, and let's execute, not execute, but let's load this data into our assembly, not assembly but GDB program. So let's specify the name of our file here to GDB. So this is data, enter. Now this data is loaded inside our GDB. First let's clear the screen, and first let's disassemble our start. And you can see here that this is our disassembly. This is our disassembled code of our program. Now let me explain you few lines. You can see this is the first line, this is the first line, and this is exactly this part. This is exactly this part. Let me link it like this. So these are the same parts. So we are moving this address. You can see this is the address. This is the address, and what this address is, this is the address of my string variable. So this address is moved into RAX register in the first line. You can see we are moving address of my string. So this is the address 402,000. We can confirm it. How we can confirm it? We can confirm it using info variables. Hit enter. You can see in the output it is showing like this variable name here, and this is the memory address. You can see this is the memory address of my string variable. So you can see 402,000. This is exactly the same. You can see here 402,000. This is the memory address of my string. So we are just moving my string memory address into RAX, and you can see here clearly this is the memory address we are sending into RAX register. So first line is clear. Let me clear the screen. Now moving on to the second line, we are moving the value. We are moving the value into RBX here, this part. Next line is this part. So this part is exactly this. Now what is happening here? You can see this DS, like from starting from here, keyword, then PTR. What this means? This keyword and PTR. Keyword means squad word. Q means squad. WORD, then word. So quad word, PTR means pointer. So quad word pointer. This is just a pointer. Where it is pointing right now? It is pointing in data segment. So this is our data segment. This is our data segment. Data segment. Remember in our CPU lecture, data segment. Data segment points to the data segment. In our primary memory. So this is data segment, and in this data segment where it is pointing, because this is quad word pointer, this is just a pointer, which is pointer where it is pointing. It is pointing somewhere, and where is somewhere? This address, at this address it is pointing. So at this address it is pointing at this value, it is pointing at this data, so it is pointing at this. So this address is pointing to this data in data segment. That is why it is DS, data segment. So this is quad word pointer in data segment. Like this is quad word pointer which is pointing at this data segment at this particular memory address at which this hello string is stored. Clear, I think. So now let's clear the screen for now. So this is our value which is pointing at this hello. So this hello will be moved inside this RBX register in the second line, in the second move instruction, clearly in this part. So this line is cleared. I already cleared this line, so these two lines are cleared right now. After that we have our just like these three lines are nothing but our system call, like exit system call, like this is our exit system call here. So let's clear the screen first and let's execute, like let's debug this program. So let's debug the program and let's see if these movements are happening in reality or not. So let's see. So let's put a breakpoint first in our start label, and after that let's use some display command to display all the registers. So in this case we only need two registers. We want to display RAX and RBX, so we need only two registers here in order to clarify if these data movements are happening inside these registers or not. So let's use display. Then I want to display in hex format, and I want to display RAX, and also I want to display RBX. After that I want to display not three but two instructions of RIP register, so that we can counter the program execution. So let's clear the screen by using Ctrl+L keyboard, like keyboard shortcut, and let's run our program. You can see right now that program is paused at this location. You can see here clearly, which is the first line of our program. Let me show you this part. Program is at this part. So this is our first line, and program is going to execute our first line here. So let's clear the screen and let's see. Now look carefully here. This is RAX and this is RBX. Right now RAX register is 0. RAX register has 0 value. RBX is also 0. So we have to watch carefully these two registers one by one. So at first we are sending the address, we are sending the memory address of this myString variable to RAX here. So you can see this memory address is going inside RAX register. So in the next step, what will happen when this line is executed? This address should be stored here in the next step. So let's perform the next step, means then let's execute this line of code using ni, and right now you can see in RAX this address is moved. That address of myString is moved inside RAX. Clear? Now in the next part we are moving this quad word pointer from data segment, which is located at this memory address, which is our hello string. So this is going to move inside RBX in the next step. Let's use ni to execute this line, and right now you can see this is our hello string in the reverse order. So this hello word, sorry, not a word, but this hello is stored inside this RBX register. We have successfully moved this value, the value of my string. We have moved the value of my string using this quad word pointer, which is stored in data section at this particular address, which is hello. So we have moved this hello, which was the value of my string, into RBX register successfully. You can see this. This is the hex value of hello. So right now, after that, we have our exit system call. You can see that this is our exit system call. Move this 60 value into RAX, then 0 into RDI. You can see that. Then we have our system call. If we continue, it will just exit normally. So through this program, I think right now you have clear concept. You should have a clear concept of how we can move address of our data, as well as how we can move the value of our data in our data segment, not data, but the data section, in our data section. So if you have any problem, conceptual problem regarding this particular tutorial, regarding this particular concept, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can move data from registers to memory. So let's see how we can move our data from register into our memory. So for that, let's create a simple assembly program in our Kali Linux. So vim space, then let's name our program move underscore data dot asm. So first let's create our data section, and in data section let's create a simple variable called my number, and let's specify the data type here, which is D and B for define byte. So this my number is of bytes, this my number is of type byte. After that, let's specify the value here. In this case, let's store 100 in this my number. After that, let's create our BSS section. In BSS section, let's reserve single byte variable here. So let's first name that variable, and the name will be variable 1. So this is our variable, and the size of, I want to reserve single byte, so RESB. So this is the data type here we are specifying here. Reserve B means byte. We are reserving bytes. So how many bytes I want to reserve? I want to reserve single byte here, 1. Now after that, let's create our text section, and in this text section let's specify our entry point, which is start label here in this case. And after that, let's implement our start label here. So first let's move our my number value into RAX register. So let's move this my number value. You can see here this my number value. I want to move this my number value, which is 100, into RAX register first. So let's do that. How we can do that? It's very easy. I already told you in my previous part. We have to use move instruction, then we have to specify the destination. Here in this case it is RAX register. We want to move that 100 into RAX register. So after that, we have to specify the variable name here. So we have to use variable name with square brackets. Remember, we have to use that variable name, this variable name in square brackets, so that we can access that value. So in this case, I am moving this 100 using this square brackets around my, like around our variable, which is my number in this case. So this 100 will be moved into this RAX register by using this instruction, this move instruction. Now after that, I am going to move RAX value. I want to move RAX value into variable 1. So I am going to move RAX value. Right now RAX has 100. After this instruction, this move instruction, the RX, this my number value will be transferred into RX, and at that position, at that particular moment, this RX will be like, this RX has stored this 100. Now after that, we want to move that RX, that 100 value which is stored in our RX, in this RX, into variable 1. So I want to move this RX value into this variable 1, which is our variable here in our .basis section. So I want to move this 100 into this variable 1 using this RX register. So what we have done so far, first we have moved this 100 into RX. After that, we are going to move that 100 from this RX register into our variable 1. So let me clear the screen so that you will not, like, you are not get confused here. So how we can do that? We can use move, then we have to again use square brackets around this variable 1 where we want to move. So this is our destination. So we want to move our value into this variable 1, this variable 1. So we have to use square brackets and then comma, and then in the source I want to move RX value. So this is RX register. So I am moving this RX value into variable 1 here. Very simple. I am just moving this RX value into this variable 1, which is in this case 100. So we are moving 100 here. You can see we have just first moved my number, which was 100. We have moved this 100 into this RX register. Then in the next move, we have just moved this RX value into our variable 1, which is this. So after that, let's use our exit system call. One more important thing to remember here, that how you can see here how we have used square brackets. You have to use square brackets in order to access the value at any variable. You can see this is variable. My number is a variable here in which 100 is stored. Variable 1 is empty right now, like variable 1 has the size 1 byte here. So we have reserved variable 1 as 1 byte. So we are just moving our data into these, like we are moving our data into this variable 1 using RX register. So let's use our exit system call here, exit sys call, to exit our program safely. So move, and I want to move this exit system call number 60 into RX, and let's comment it, syscall number for exit. And after that, let's move our next value, which is the return status for this exit system call, return status in our RDI register. After that, we have to use this syscall keyword, which will execute this exit system call here. So we have totally used two move instruction basically to move our data from one place to another place, from our one memory location to another memory location using our RX register. So let's write this file, and let's assemble this file using YASM using G option. G option is used for generating the debugging symbols in our program. So -G, then dwarf 2, and then we have to specify our format. So in this case 64-bit, ELF 64. Then we have to specify our source file. So move data.asm. Right now object file is generated, you can see .o. So let's link it. So move data.o in output, move data. Right now we have successfully generated our file, move data. So let's clear the screen and let's use our GDB to load our file, to load our binary file. So move, not move, it's move data. So this file is loaded, and let's disassemble our start label first. And in start label you can see this is our first move instruction and this is our second move instruction. Now in this case you can see that in first move instruction we are moving this part, like this move instruction is moving this particular value, which is quad word pointer. You can see quad word pointer in data segment, and this is the value, like this is the address. And what is this address? We can clarify that what is this address, like where this address is pointing. How we can do that? Using info variables. You can see these are our variables in our program. So you can see we have variable 1 and my number. We have two variables. You can see here my number and variable 1. So my number, you can see clearly here, my number memory address is 402000, and which is exactly the same here. 402000 means this is the address, memory address of my number. So it is taking the value, like this is quad word pointer. This is quad word pointer. This is just a pointer which is pointing the data of my number, which is pointing the value of my number variable at this particular address. So at this particular address this 100 is stored. That is why this is quad word pointer. So this is just a pointer which is pointing at this 100 using this data segment memory address. So what will happen? So at this particular location the data will be moved inside this RAX, which is in this case 100 here. So this 100 will be moved from this memory location to RAX in the first part. Now after that what is going to happen in the next part? You can see here RX, in the next move our RX value will be moved into another memory location. You can see this is another pointer, this is another memory pointer address. So this is another memory location, and if you look carefully, 402004, this is the address of our variable 1. So in the next part we are just moving the value into our variable 1. So we are just moving the 100 from our RAX. We are moving just 100 from this RAX into that particular memory location, which is our variable 1 here. You can see 402004, 402004. This is also quad word pointer in data segment, which is pointing at this particular address. So at this particular address this 100 will be stored. So let's clear the screen for now. And this was the dry run for our disassembly code. And if you get confused, don't worry, the things will be clear after running this program in GDB. Not clear but L. So let's use display to display RAX in hex, RAX register in hex while the program runs. And also let's display the value of variable 1 in hexadecimal form. So now it is it is printing, it is displaying the address here, not the value. I think we have to use examine command for that. So let's delete this display for the moment. Let's delete this particular display because it is not giving what we want. here. And let's also display uh, two instructions of RIP, so that we can counter our program where our program is right now when the program is running. So let's run it. Not now, but let's clear the screen first. Let's run our program. Okay, so we have not given any breakpoint, so let's give a breakpoint and let's run our program. So you can see right now we have used display to display two parts, like two things here. This is the first part and this is the second part. In the first part we have displayed RAX value. You can see right now RAX is 0, and you can see the program is paused at this particular location, at this particular memory location here, in which you can see this is our first move instruction. In the first move instruction we are just moving our my variable data, which is 100 in this case. So we are moving my number variable value using this quad word pointer at this address into this RAX register. So after this movement, this data movement, what will happen? This RAX value should be changed to 100 here. Let's execute that instruction using next ni command, and you can see that this RAX value is changed from 0 to 100. So this is the hex value of 100. This is the hexadecimal value of 100, which is converted here 0x64. So if you convert this 0x64, you will get 100 in decimal. So our first part is completed. We have just moved the value of my number variable into this RAX. The first part is completed. Now moving on to our second part, which is this part. So this is our second part. So this part is this second part. So in this part, what is going to happen? This RAX value, you can see this RAX value will be moved at this particular memory address. You can see 402004. So this is just a pointer, quad word pointer, which is pointing at this particular memory address. And at this particular memory address, this variable 1 is stored. Sorry, this variable 1 is the memory location of this particular memory address. So what is going to happen? This RAX value will be stored in this variable 1, which is in our data, like .bss section. So first let's clear this mess, and let's use next instruction to execute our next part. So now this has executed. It means that right now our variable 1 should contain 100 value. How we can find out that? We can use x command, means examine command, to find to see the value of variable 1. So x, then we can use d here for decimal. I want to print the value in decimal, and what at which address we want to print? We want to print at variable 1 address. And you can see this variable right now, this variable 1 has the value 100. Why? Because in this particular line, at this particular line, we have just moved the value from this RX register into this variable 1. You can see this is exactly here. So we have just moved this RX value into this particular address by the use of this quad word pointer, which is pointing in data segment at this particular address where our variable 1 is located. So this is our variable 1, and this 100 is received from this RX register. So this is very simple concept, nothing to be complex here. This is our like this is the data movement. First we have just moved this into Rx, then from Rx we have just moved our data into this variable one. So anyway, just do the practicals, and if you stuck on anything, if you have any problem, confusion regarding this concept, let me know in the comment section, and we can continue our program and the program exit normally. And I will see you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I'm going to show you how we can move values from one register to another register. So you can see in this slide, you can see here RAX has a value 4 and this is our RBX. So if we want to move this RAX value 4 into this RBX, what we need to do? We need to use this move instruction. You can see here. You can see here. We have to move, we have to use this move instruction in order to move our 4, this 4 value which is stored in RAX at this location, at this RBX location, RBX register location. So how we can do that? We can use this move instruction. So let's implement this concept in our assembly program in order to demonstrate this concept. So for that, let's create a simple program called data move.asm, and in this program let's first define our text section here, and in text section let's specify our entry point by using this global keyword, and in this case our entry point is start. And let's implement our start label here. So first let's move a value into our RAX register. So use move, then RAX, then 4. So we are moving 4 into RAX register in this move instruction, like in this particular line. So let me comment it, moving 4 into RAX. Now after that we are going to move RAX value into RBX register. So RBX and RAX here. In this case RAX value has 4, like RAX has the value 4 right now. This RAX has value 4. So this 4 will be moved into RBX register using this move command. So simply we are moving RAX register value into RBX register. That's very clear. Like that's very simple concept here. So we are moving RAX into RBX. Let me comment it, moving RAX value into RBX register. Now after that let's use our exit system call to exit our program normally. For that we have to move 60 into RAX. 60 is the system call number for exit. So exit syscall number. Then we have to move our return status value, in this case 0. So 0 is moved into RDI to indicate the return value, return status value. So return value, return status value for exit. After that we have to use our syscall keyword in order to initiate the execution of this exit system call. Let's write this file and let's assemble it using YASM. Then let's specify the format here. So in this case ELF 64-bit, and let's specify the source file, in this case data move.asm. Now our object file is generated here, data move.o, and let's link it. So data move.o object file. So as an object file should be given here as an input, and then in output we have to specify a name here. In this case, this is data underscore move. So you can see that we have successfully generated our binary file data move. So let's load this file in our GDB data underscore move. Now right now data move is loaded inside GDB, and let's first disassemble our start label. You can see this is our start label code, and in this start label you can see, and this is our first line. In this first line we are moving 4 into RAX. Now after that, in the second line we are moving this RAX value. You can see this second line. So this second line is this part. We are moving RAX into RBX. You can see here this is like this. So let's clear the screen for now, because this is very simple program. It's easy to understand here, nothing is complex here. So let's put a breakpoint at our start label, and after that let's use our display command to display the RX value, and after that let's use display command to display our RBX value, and in the last we have to we are using display to display at least 2 instructions of RIP, so that we can counter our program while it is running. So let's first clear the screen and let's run our program. So right now you can see that we have displayed 3 parts here. In first part we are displaying RAX, in the second part we are displaying RBX value, which is 0 in this case. You can see RAX is also 0, RBX is also 0. In the third part we are just printing the instructions, program instructions from the RIP register. So right now RIP is pointing at this particular place, this particular memory address, you can see, which is the starting of our code, like starting of our start label. So this is our first line. In this first line you can see this 4 is going to move into RX. So let's use next instruction. So this instruction, this line is executed, and after execution of this line you can see it was 0, RX value was 0. Right now it is 4. You can see RX equals to 4 because we have moved 4 into RX. Now after that what is going to happen? This RX value will be moved into RBX. So right now you can see RBX is 0 here. So let's execute it and let's see if this RBX is changing or not. So let's use next instruction, and you can see RBX is 4 now. It means that we have successfully moved the RX value into RBX here. So this value is moved into RBX register, and after that you can see that this is our system call. This is our system call here, exit system call, in which it is moving 60 into RX and then it is moving this return value into RDI. So let's continue, and this program exits normally. So this was very simple concept, and if you are facing any kind of trouble regarding this practical or regarding this concept, let me know in the comment section. I will surely help you. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I'm going to show you how we can move different data sizes in registers, how we can move different size of data in our registers. So let's see how we can do that. So you can see here, this is our RX. So in this example we have taken this RX register, this RX general purpose registers. So this is RX and the size of this RX is 8 bytes. So this is our 8 bytes. So if we look at small memory sections of this RX register, you can see here these are the 2 small memory sections of this RX register. So the lowest part is called AL, and after that we have our AH. So this is AL. This L means lower. This H means higher from that particular lower. So basically this is AL and this is AH. So suppose if we want to store data in these two memory locations. Suppose if you want to store data into these two memory locations in AL and AH, how we can store some data in these two specific bytes of this RAX register, not this RAX but specifically into our general purpose register. So this is also a general purpose register here. So how we can do that? How we can store some data into this particular AL or in this AH register, not register but AH location of this RX register. So let's see how we can do this in our assembly program. Let's minimize it for now and let's create a simple example code here. So vim, then let's name it move data.asm, and first let's create our data section here. Data. In this data section, let's create two variables here. Variable A, which is of type data, which is of type byte here, defined by db, and then let's assign a value called 3, and let's create another variable B, which is of the same data type, and let's assign 5 here to B. So we have A which has the value 3 and B which has the value 5 we have assigned here. Now after that, let's create our .text section, and in text section let's define our entry point by using this global keyword, and in this case our entry point will be start. So let's implement our start label here. Now let's see how we can move these A and B. I want to move this A into AL. I want to move this A. Let me show you. Let me adjust the screen for now here. Okay. I want to move this 3. I want to move this 3 means this A. I want to move this A value into this AL location, and I want to move this B into this AH location in our RX register. So how we can move this? Let's see how we can move this in our assembly here. I want to show you. So we are using move instruction. So move, first we have to specify our destination. In this case our destination is like we are going to move this A into AL, so we have to specify AL here. I want to move our value into this AL register. So AL, and after that we have to specify the source. So which what we want to move. In this case I want to move this A, so we have to specify this A variable here. This is A, but we have to use square brackets around this A because we want to move the value, not the address. So in the first part we have successfully moved this 3 into this AL register. AL register is a small unit of RAX register. So we have moved A value into AL register. After that, the same way we can move our B value, which is 5 in this case, in our AH register. In AH register, this is our AH register. So first we have to specify the destination, which is AH, where we want to move, and then we have to specify what we want to move. I want to move B, so we have specified this B variable here. So this way we can move A and B here, A and B into this AL and AH registers. So in this case, let me clear the screen for now, and we are just moving A here and B, not A and B here like this. So basically we are moving 3 here and we are moving 5 here using this move instruction. So let's clear the screen and let's minimize this and let's continue our program. So we have moved A and B into AL and AH here. After that, let's use our exit system command to exit our program normally. So move RX, move into RX. What we want to move? 60, which is the syscall number for exit, and we want to move the return value here, which is 0 in this case, and we can specify a return value for exit. After that, we have to use syscall to initiate the system call, and let's write this file. After that, let's assemble it using ysm-f, and we have to specify the format here, so 64-bit, and then let's specify our source file, which is movedata.asm, and right now you can see our object file is generated here. So now we have to link it using ld, then movedata.o. in output we have to name it movedata. Now our file is ready to load in our GDB. So let's load this move data file in our GDB. So gdb-q, then move data. So we have loaded our file into GDB. Let's disassemble start first, and you can see that these are the disassembly of our code of our start label. You can see this is start label. So this is our first move, in which we are moving our data into this AL register, and you can see this byte pointer. You can see byte, then PTR pointer. So byte pointer. So this byte pointer from data segment, which has the memory address this 402000. This is the memory address of the data which we want to move into this AL. So we can cross verify this particular address as what is stored at this particular address. We can cross verify. So we can use examine command X, then we want to print like we want to print 1 byte in decimal form. Here B is for byte. We want to print 1 byte only at this memory address. So B, and then D for decimal. We want to print the value in decimal. So let's specify this particular address. Let's copy it. Copy, and then let's paste. So hit enter. You can see at this particular address there is 3, and this 3 is where it is coming from, this A. So we have specified A here. You can see this A. So we are moving this A value into AL. So this is our A, which has the value 3 clearly. So right now we are just moving byte pointer from data segment of this address, which is 3, into our AL register basically. So let's put a breakpoint first at our start here, and this is the first movement in which we are just moving our 3 into AL from this particular address, memory address. And in the second move, you can see we are using the same technique, like we are using the same technique to move our second value, which is B, into this AH register using this particular memory address. So we can cross verify again, just copy this address to see what is stored at this particular address right now. So we can use the same command, like examine command here, and let's change the address to this 402001. You can see this is exactly the same, and hit enter. You can see we are just moving 5. So this is indicating 5. This is pointing to 5, and this particular pointer is pointing to 3. Clear? Now we have our breakpoint set here at this particular address, which is this. After that, what we have to do, we have to just use display command. So let's use display. Let me clear the screen first so that you can see better. So display, I want to display in hex, like hexadecimal value, and I want to display AL value. I want to display AL value when the program runs, and I also want to display AH value also. And after that, let's display 2 instructions of RIP so that we can see where we are in our program. So let's again clear the screen and run our program, and you can see clearly right now that this AL value has a 0 value. AH is 0 right now. So AL register is 0 and AH register is also 0 right now. So right now our program is going to execute. You can see this arrow. Our program is at this location, and right now the program is going to execute this move instruction, in which we are moving some data, like we are moving this data which is pointing at this particular memory address by this byte pointer, and this data is stored in our data segment, which is our dot data section here. So this particular value will be moved into AL register. Right now you can see this AL register which has a 0. So after this instruction, after executing this part, this line, this AL value should be changed to 3. You can see here 3. We are moving 3 here in this first line. A is moved into AL, which is 3 here. So let's use next instruction to execute it, and you can see right now this AL value has value 3. So we have successfully moved this particular value into AL, which was A. So 3 here. After that, the same way we are moving our next variable value, which is B in this case. You can see B is moved into AH. So this is our B, which is going to move into AH register, and AH is right now AH is 0 here. Let's execute it, and you can see AH is 5 right now. So we have moved this 5 into AH register successfully. So we can use C to continue the program. Now you can see program exited normally. So this was very simple example, nothing complexity here, nothing complex here. We just moved this 1 byte into this AL and another byte in AH. So we have moved one data byte, not 1 data byte, but 1 byte into AL, and this 5 into AH register. So this was the basic basic demonstration how we can move the data into these 2 small memory segments here into our RAX register. So we have just moved some data into AL and AH. So that's all for now. If you have any problems or you have any questions regarding this, let me know in the comment section. I will surely help you, and I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can move array data in registers. In this case, this is our RAX register, and this is the AL register, and this is our AH register of this RAX register, and this is our variable A. You can see here clearly this is a variable, and we have just defined this a variable with the data unit byte, and in this a variable we have assigned 3 elements here. You can say 3 elements, you can say 3 bytes. So we have defined 3 bytes here, and these bytes are just decimal numbers. You can see 3, 5 and 2. So this a variable has three values here, like we have assigned three values, which is 3, 5 and 2. See, these are the three numbers which are assigned to this a variable in our program. Suppose if we want to move this 5, if we want to move this 5 number here, AL. So if we want to move this 5 at this particular location in our register, how we can do that in our assembly? So let me show you how we can do this in our assembly. Let's create a program and move this particular 5 at this particular location in our RX register. So let's minimize it and let's create a program called move underscore data.asm. First, let's create our data section, and in this data section let's create our a variable which is of type byte, and in this a let's assign our data elements here. So 3, 5 and 7. So we have assigned three decimal numbers here into this a. After that, let's create our text section here. In text section, let's define our global entry point, which is start in this case, and then let's implement our start label. Now let's use move instruction to move this 5, to move this middle element of this particular a variable. So I want to move this 5. I want to move this 5 into AL register. So how we can do that? My target is my target location is AL here. So we have to first specify our target AL, and after that we have to specify the source here. So I want to move this 5. I want to move this 5 of this a variable. How we can do that? We can use indexing here. So this is the concept of indexing. So first we have to specify the variable name here, a, and then we have to use this plus sign. We have to use plus sign. So by using plus, I am specifying that which index value I want to move from this a variable. So the index value will be, this is the 0 index. This 3 is stored at 0, because in programming when you create an array or list, the list or array elements starts from 0 index. So this is 0, this is 1 and this is 2. I want to move this 5, so this will be at 1 index here. So I have to specify 1 here. So 1, and that's it. So moving 5 into AL register. So you can see we are just moving this value. This value means 5. So what this denotes, a plus 1 means this a is variable and plus 1 means index value. So we are just specifying the index value of our a variable, which is in this case 5. So this indicating the 5 here. So this file will so this 5 will be moved into this AL register here. So let's clear the screen first and let's continue. After that, let's use our exit system call to exit our program. So move then 60 into RX, which is the syscall number for exit, and let's move the return status value, which is 0 into RDI, and let's comment it, return status for exit, and let's use our syscall keyword to execute exit system call. So let's write and let's assemble using ysm. So ysm space, then let's specify the format here, so elf64, and then let's specify our file name, in this case move data.asm. Now our object file is ready to be linked, so let's link it using ld move data.o. in output let's name it move data. So our file is generated, our executable file is generated successfully, you can see here. Let's load this in our gdb. So gdb-q, then move underscore data. So our data is loaded, our binary file is loaded in our gdb, and let's first disassemble our start here. So you can see in start, at first you can see this is our first instruction, like this is our first line here. Let me show you. So this is exactly the first instruction of our assembly code, this particular instruction. So in this particular line you can see that we are moving this 5, means we are moving this particular index value of a into this al register, So at this particular location you can see this is the location address. You can here you can see byte pointer from data segment at this particular address. So this is the address, and we can confirm it here. We can confirm it like what is the address, like what is the value stored at this particular address. So we can use just the same technique which I have told you in my previous video. So let's use examine command x, then I want to examine single byte, so b, and then decimal, I want to see the value in decimal. So let's paste the address here. You can see this is exactly the same, 402001. You can see 402001, hit enter. You can see 5 is stored. You can see now, you can see this particular expression is pointing to 5 in our program. So this particular address is pointing to 5. So this address is pointing here, exactly this location. So this means that we are pointing 5. So I think that is clear now. So we are just moving this 5, this byte pointer at this address at AL, like in AL. So we are just moving this value into this AL register, which is 5. So let's put a breakpoint at start, and let's use display command to display AL value, and I want to display 2 instructions of RIP so that we can counter our program where we are. And let's again clear the screen and let's run our program. Right now you can see that this AL value is 0 here, and our program is paused at the first line of our code, like first line of our program, which is move. So we are just moving this 5, means this 5 from this A, and you can see this is the address. So we are just moving this byte pointer at this particular memory address into this AL register. Let's execute this line and let's see if our AL register has this 5 value or not. And you can see that AL is 5 right now. So 5 is moved into this AL register. It was 0 before and right now it is 5. So we have moved this particular, like we have moved the data at this particular memory address, which is 5 in this case here, from this A variable into our AL register. After that we can use C to continue, and you can see the program exited normally. So we have just accomplished this task. So in this way we can move any data from our array data variable. So in this case our variable was a, and in this variable we have three data here, 3 5 and 2 here, and I think one number is changed, 357 is there. So this, there is a 7 and here it is 2, but it doesn't matter. The only thing which is matter here, how we are sending the data in our registers. So the main concept was to use index, and this is the proper way of pointing at particular index value. We can move this 7 also using the index value. So in place of 1 we have to use 2 here, because it is located at 2, means this is 1, this is 0, this is 1, and this is 2. So if you want to move this 7, in place of 1 you have to use index value here, so a plus 2. When you specify a plus 2, then what will happen, this 7 will be moved into this AL register. So this 7 will be moved into this AL register, and it's very simple concept. So that's all for now. If you have any questions regarding this concept, let me know in the comment section and I will surely help you. So till then, goodbye. Hello everyone and welcome to the next part of this tutorial. So in this part I am going to show you how we can store our data into this AX register and in this EX register as well. You can see this AX is a word. The size of this AX register is a word. Word means 2 bytes. And this EX is of 4 bytes. You can see 1, 2, 3, 4. So this EX is 4 bytes in size, which is also called double word. So let's see how we can store our data in AX and EX as well. This is very simple. So let's use Vim to create our file. In this case, let's create data.asm and let's create our data section first. So data, in this data section, let's create a variable called a and let's specify the data type here. So in this case the data type will be DW, means word. So define word, we are defining a data, like we are creating a data which is of type word, and the variable name will be a in this case. So let's assign some value. So in this case let's assign 10. So this 10 will be assigned to this a variable, and let's create another variable called b and let's specify the data type here. In this case it will be dd means define double word. So we are defining double word means 4 byte. So this is of size 4 bytes, and let's assign a value called 500. So we are assigning this 500 to this b variable. Now the sizes, let me show you, let me comment here sizes. So 2 bytes, or we can say word, and let me specify the size here as well. 4 bytes, 4 bytes, which is called double word. So this way, there will be you can understand this well, easily. So this a is 10 and this b is 500. So let's create our text section after that, and let's first specify our entry point using this global keyword, and our entry point will be start in this case. So let's implement our start label. So first let's move this a. So let's move this a variable value 10. So let's move this a value into our AX register. So move, then AX. I already told you here. So we are going to move our value into this AX register. That is why we are using AX here. So we want to move our value, our data value into AX. What we want to move? We want to move A here. That is why A. So A should be in square brackets. So this A means this 10 will be moved into AX. Let me comment it. Moving A value into AX register. After that, we want to move our B into EX register. Let me show you EX register. So we are not going to use this EX name because you can see in this EX, this AX is also in this EX. So we cannot use this RAX. We can use RBX register here. So in place of A, we have to use B here. So EBX. So we have to use EBX because we have to change the register. This is A register and we have to use the B register in this situation, because we don't want to overlap this AX into this EAX. That is why we have to change the register here. So in place of A, we have to use B register here. So EBX in place of A. So let's use EBX. So EBX, and then I want to move this B value. So what we have to do? We have to use square brackets around this B variable. So square brackets, in square brackets B. So we are moving this B into EBX. After that, let's comment it, moving B value into EBX register. After that, let's use our exit sys call. And for exit system call, first we have to move the system call number into RAX, which is 60 in this case. System call number for exit. After that, we have to move the return status value, which is 0 in this case, into RDI. Let's comment it, return status value. After that, we have to use our syscall keyword to execute this exit system call in this program. Now after that, let's write this file and let's compile it using ysm space, then we have to specify the format elf64, and then we have to specify our source file, in this case data.asm. Now our object file is ready to be linked. So this is our object file. So let's use ld to finally generate our binary file using this object file. So data.o as an input. In output, we have to use any name in this case. So we want to use data here. So now our data is ready to be loaded into GDB. So let's open our file in GDB. So gdb-q and then data. And first, let's disassemble our start label here. Hit enter. And right now you can see that like we have used these two move instructions, and this is exactly this part. This is exactly this part. So these are the two instructions. So now you can see that in the first part, focus on this part first. In the first part, this is our first part. In the first part, this word pointer, you can see this WORD word. Let me erase first these sketches because it is getting, it seems like that was not good. But anyway, you can see this is word pointer. This is word pointer. This word means word. This point PTR means pointer. So this word pointer, which is pointing at this particular data segment. This DS means data segment. So this pointer, this word pointer is pointing at this particular address, memory address in our data segment. So let's see what is stored at this particular memory address. Let's copy it and let's examine. Let's examine single byte in decimal. So let's examine and print the value in decimal, the single single value in decimal. So like you can see this is a word. And so this is a word means 2 bytes. So we we want to see, if we want to see a word, like if we want to print the value in word, we can specify like 2 bytes here, 2b, like 2b means 2 bytes, and we can use d for decimal. We want to print it in decimal, and then we have to specify the address, memory address. You can see this is our memory address, which is exactly this part, this value. So I want to see what is stored at this particular memory address, and you can see that 10 is stored. You can see this 10, this is the first byte and this is the second byte. So in the first byte this 10 is stored. You can see here this a, we have specified a here, a variable. So at this a location, at the first byte, because we have 2 bytes here, we have created 2 bytes of space, but in the first byte this 10 is stored. So this is showing 10. So 10 is stored and this 10 will be moved. So this is pointing at 10. This memory address is pointing at 10. This is 10. So this 10 is stored at this particular memory address. So this 10 will be moved through this pointer, this word pointer, into this AX register. Like the same way, we have our double word pointer, which is pointing at this particular memory address. So if we can confirm it by using using examine command. Let's just copy this address. Just copy this address and use the same command. Let's paste our address of our double word pointer, and let's change the format here. In this case, we have to use word here. Like we have used we are moving double word. Double word means 4 bytes. Our operation is doing our move operation is moving in 4 bytes. So 4 bytes will be there. So we have to specify 4 bytes here by using W. So W means word, here in GDB, W means 4 bytes. So we want to see what is stored in these 4 bytes, and I want to display that values in decimal at this particular memory address, which is this address in our second part, like this part. So this dword pointer is pointing at this particular memory address, which is nothing but 500. And let's see if this is true or false. Yes, it is true. You can see that we have used examine command to see what is stored at this particular memory address, which is nothing but this address is same. You can see this is the address. So at this address, this 500 is stored. So we have confirmed it, like we have confirmed all the parts. We have confirmed that this 10 is moved from this memory location into this AX, and this 500 is moved from this memory location into this EBX register through these pointers, which is in this case double word pointer, and in this case it is a word pointer. So let's first clear the screen first. So let's Control L to clear the screen. Let's first put a breakpoint at our start, and after that let's use our display command to display our AX register to see the values when the program execute. So display, then I want to display in hex format, like hexadecimal format, and what we want to display, we want to display AX register value. After that we want to display our EBX value as well, and after that I want to counter all the instructions of our program while it is running. We have to use this this display command. I want to display 2 instructions in this case of RIP register. And again let's clear the screen by using Control A, and after that let's run our program. So in this case you can see that this arrow is showing at this place, at this memory location, and right now our program is paused at this particular memory location, and in this particular memory location this move instruction is going to move this particular pointer value into AX, and this is the address from which it is taking our value, and this part, and in this situation this is 10, this is 10, this is like this is 10. So this 10 will be moved into AX. You can see this. So we are moving 10 here into this AX using this A variable. And let's use next instruction to see if our AX, you can see AX and EBX. So AX is 0 right now. After executing this part, this AX should be 10 here. So let's execute this line. Let's execute this line. You can see this line is executed right now. You can see this AX is 0xa. So this AX is changed from 0 to 0xa. 0xa means 10. If you convert this hexadecimal value into decimal, you will get 10 here. So this AX is 10. So this 10 is moved. You can see this in this first part. In this first part, this 10 is moved from here to here, like into AX. Now this first instruction is completed. Now we moving on to the next instruction, this B. So this B value will be moved into this EBX in the next part, and you can see right now EBX is 0. EBX is showing 0 here. So let's clear the screen first, and let's you can see right now we are going to move our next value, means B value into EBX using double word pointer. Double word pointer and using this address. So this double word pointer is pointing at this particular memory address where our 500 is stored. So this 500 will be moved into this EBX register. So let's execute this instruction and let's see if EBX is like if EBX is receiving that 500 or not. And you can see exactly EBX is changed from 0 to 500. So this is the hexadecimal value of 500. If you convert this hexadecimal into decimal, then you will get 500. So this 500 is moved into EBX as well. So after that we can use C to continue the program. You can see program exited normally. So this is the way how we can move our data into these different size of registers. So this AX is of 2 bytes in size, and this EBX is of size 4 bytes. So we have successfully moved 2 byte values and 4 byte values as well in our registers. So that's all for now. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I'm going to show you how we can move our characters, our character data in different sizes with the help of memory indexing into these registers, these different sizes of registers. You can see here this AL, this AH, both of these registers are of only single byte in size, and in this AX is of 2 bytes in size called word, and this EX is 4 bytes in size. So let's see how we can move our character data into these registers one by one. Let's minimize it and let's create a simple program called data.asm, and let's create our data section here. And in this data section, let's create a variable called A, and let's specify the data type as byte. So D and B, define bytes. After that, let's assign 2 characters here, A and B. So we have assigned 2 characters to this A variable. After that, let's create our text section, and in text section let's specify our entry point by using this global keyword. In this case our entry point is start. So let's implement our start label here. So let's move this A into AL register and B into AH register. Let me show you what we are doing here, like what we are going to do here. So I want to let me move this little bit. What I am going to do here, I am going to move this A. You can see this A. I want to move this A into this AL, and I want to move this B character into this AH location. Simply we will move this A character into this AL register, and B into this AH register. So let's see how we can do that. Let's clear the screen and let's minimize it. So let's use move, and we want to move first, we want to move this A character from this A variable. So first we have to specify the destination. In this case I want to move the data into AL register, and where we want to move, I want to move this A character, this particular A. So in this case I have to use an index here. So A plus 0. I can use index here if I don't use, like if I don't specify the index of our data, then it's okay. I think if I do this, then what will happen, this one byte of this A variable will be moved into this AL register, because AL register has the capacity of taking only 1 byte, holding 1 byte. So it can hold, like it can store 1 byte only. That is why we don't have to specify index here. So this will work. So we are just sending this A into this, like we are sending just this first byte of this A variable, which is A, into this AL register. Now after that let's comment it, moving first byte A into AL. Now after that I want to move the second byte is B. So this is the B, the second byte of this A variable. I want to move this B into AH register, like our next register, which is AH, in this register. So how we can do that? We can do it in the same way. So we have to first specify our destination location, in this case AH. So AH, and then we have to specify the index here. So in this case I want to move A plus and 1. A plus 1 means if we count from 0, the index 0, the first byte of this A variable is this A, and the second byte is the second byte is B. So if you count 0, like if you start counting from 0 index, this B is at 1 position. Like the memory is like here, like the memory is stored like this, like the data is stored like this. So this is our A data, like A variable. In this A variable we have stored A and B like this, and if we count the index value, so index value is 0 here, this A index is 0 and this B index is 1. So A is stored at 0 index of variable A and B is stored at 1. So that is why we have specified this one here, this one here. So A plus 1 means take the value of A which is stored at index 1 here. So at one location, at one index, our B is stored, this B is stored. That is why we have specified A plus 1 here. So we want to move this B into AH register. So after that, let's use our exit syscall to exit our program. So move, I want to move the system call number of exit into RAX, and let's specify syscall number for exit. After that, we want to specify the return status, which is 0 in this case here. So return status value of exit syscall. Okay, exit. So let's use our syscall keyword to execute this system call in memory. Let's write this program and let's assemble it using YASM-F format ELF 64-bit, and then let's specify our source file, in this case data.asm. Now our object file is ready. Let's link it. So data.o in output data. So our data file is generated successfully. Let's load this data into our GDB and let's see what is happening inside our program. So first let's clear the screen, Ctrl L. First let's disassemble our start. So you can see clearly here that in the first line, you can see this is our first line. This is our first line. Let me clear the screen first. So this is our first line. Focus on this part. So this is our first line. This is exactly this. So in this line you can see that byte pointer, this byte pointer is pointing at this address, and this address is nothing but this A this A character. So at this particular memory address 0x402000, at this particular memory address this A character is stored in memory. So this A means this A, the A is here, this A will be moved into this AL register by using this byte pointer. So this byte pointer is moving this A from this address into AL register. Like the same way in the second instruction, in the same way the next character which is stored at this particular address, which is B. So this byte pointer is pointing at this particular address where B is stored. So this B will be moved into this AH register in the same way. So in both cases byte pointer is used. So byte pointer is pointing at this particular address to point the data which is stored, and by using that byte pointer program is moving the data into the destination, which is AL here. So let's clear the screen for now and let's verify what is stored at these addresses using our X command. So X, I want to print a single byte value in hex. So let's specify the address here, and you can see clearly that at that particular location using B and X, we have confirmed that this is our A value. If we convert this hexadecimal into character, this 61 indicates this A value. So this is A, 0x61 is our A, and let's confirm our second value. Let's copy it and let's paste the second address, which is our B in this case. You can see this is our B. This is 62. 62 means in hexadecimal, this 62 means this is our B, the next character. So we have cross verified that A is moved from this place to AL, from this particular location by using this byte pointer into this AL, and then the next value is also moving like the same way into our AH register. So for now, let's put a breakpoint at our start label, and then let's use some display command to display our register values of AL and AH, so that we can see how these characters are moving inside our registers AL and AH. So display, I want to display AL, and I also want to display AH also, AH register also in hexadecimal format. After that, I want to display two instructions of RIP, so that we can counter our program execution. So again, let's clear the screen and let's run it. And you can see right now our AL has a value 0, AH has a value 0. And right now the program is going to execute our first line of instruction, which is move, and we are moving our first character byte, which is A in this case, into this AL. So this A will be moved by using this byte pointer into this AL register, and this A is stored at this particular memory location. So let's use next instruction to execute this line, and you can see A is moved into this AL register. You can see 0x61. This is the hexadecimal form of A character. After that, we are going to move B character into AH using this byte pointer. So let's use next instruction, and you can see this B is also moved into AH register. You can see 0x62. It was 0 before, right now it is 0x60. So this 61 is A, then 6 and this 62 is B. So we have successfully moved A here and B here easily. So right now we are going to move our A and B into this AX register. Right now we have we have done with AL and AH. Right now we are going to move this AB into this AX register. So we are going to do the same thing, but this time we are going to move our data, our character bytes, into this AX register, and you already know that this AX is of 2 bytes in size and our data is also 2 bytes. So let's see how we can move that AB into this AX register. Let's clear the screen for now. So let's minimize it, and let's do some change in our program. So what we can change, let's delete these 2 lines first. Let's delete these 2 lines, and here let's change, let's quit here, let's clear the screen. Let's use move, and let's move our data in AX register. So this time we are going to move our data in AX register. Remember this this presentation here. You can see we want to move our data in AX register, which has the capacity to store 2 bytes. You can see 1 and 1, 2 bytes. So in this case we don't need any index. We don't need to specify any index, because our target, like our source is already 2 bytes, A and B. So in this case we only specify this A like this. So by using this, what it will do, it will take 2 bytes, these 2 bytes A and B, and it will store these 2 bytes into this AX location, which has capacity to store 2 bytes. So A and B both will be stored in this AX register. So let's comment it, moving AB into AX register. register. So let's write this file, and let's again assemble it first, and let's link it, and let's load this in GDB, in our GDB. So let's load it. First let's disassemble our start. This time we have only this single move instruction which we have used to move our data. You can see here. So this time you can see again our program has used word pointer this time, because we are moving into a word pointer, like we are moving into a word you can say a word data unit, you can say, because this AX is a kind of word. Like this AX has a capacity to store a word value. This AX has the size of word. Word means 2 bytes. 2 bytes. Remember this. So this AX is a word. So that is why this word pointer is used. So word pointer. So word pointer which is pointing at this particular memory address. So at this particular memory address, what is stored? This AB is stored. So this A value will be moved into this AX register using this particular pointer address. We can cross verify by using X command, examine command. I want to examine 2 bytes in hex. And what we want to examine? We want to examine 0x40, this address. I'm making some examination on this particular address 402000. You can see, and hit enter. You can see this is our A 61 and this is our B 62. So both of these values are stored at this particular memory location. And at this, like the pointer is pointing at this particular memory location here, you can see. So that is why at this particular location A and B, our A and B is stored at this particular location, and this will be moved into this AX register using this pointer which is pointing at AB using this particular memory address. You can see here memory address. So let's clear the screen first, and let's put a breakpoint first. Let's put a breakpoint at start, and let's use our display command to display AX value in hex so that we can see what is happening in our program while it is running. And after that, let's use display to display 2 instructions of RIP so that we can see where we are in our program while it is executing. So let's clear the screen and let's run our program. You can see that in the first part, you can see first line, this AX is 0 right now, and right now the program is going to execute our first line. First line means this line, this particular line where we are moving AB, this AB character from A into AX register. So AB is stored at this particular memory address. You can see here this particular memory address. Using this word pointer, it is pointing at our data using this memory address in the data segment. So this will move the AB into AX register, and right now you can see it is 0. AX is 0. After executing this line, what will happen? AB will be moved into this AX register. Let's execute using next instruction. Right now you can see that this AB is moved into AX. You can see 61 and 62. It was 0 before. Right now it is 61 and 62, which indicates this is A and B. After that, we can continue to exit our program. You can see. Now we have moved our data, our character bytes into AX. After that, now we are going to move our character bytes into this EAX register using the same method. How we can do that? You can see here EX is of 4 bytes. So in this case, we have to do some modification into our program. Let's first delete this line, and then let's increase our characters. So in this case, A, B, C, D. Let's use let's insert these two characters into this A variable. So C and D. So now we have 4 bytes here. We have 4 bytes of data here, 4 characters. So A, B, C and D. If I want to move A, B, C, D, A, B, C and D into EX register, which has the 4 bytes in size, you can see which has 4 bytes in size. This EX has 4 bytes, 1, 2, 3, 4. So it's very easy here to move. So use move, and then we can use the same method. So I want to move my data in EAX. So we have to specify the destination EX here. What we want to move? We want to move A, this A. So by using this square bracket, we are telling that we are going to move 4 bytes starting from this A variable location. So at A, the data is starting from this place A. So A, B, C and D. Suppose if it has E and F, like two more character bytes. Suppose I have increased 2 more bytes. In this case, what is going to happen? In this case, only 4 bytes, like these 4 bytes will be stored in this EAX register, because this EX has the capacity to store only 4 bytes. So all the other bytes will be neglected in this case. So let's remove those 2 bytes, and let's comment it, moving A data to EX register. And let's write this file, and let's quit it. Let's assemble and link it again, and let's load it in our GDB. Let's disassemble our start again, and you can see that our first instruction, which is move in our start, in this move, this is the same. Let me use my what I did. Okay, so this is our first instruction, first line you can see, which is this. So in this, we are moving A value into this EX register, and which is exactly the same is going on here. Same thing is going on here. So in this case, what is happening here? It is using this address, and this address is of address this ABCD character. So we can confirm it by using our examine method. So let's see what this address contains. So X, then I want to see 4 bytes in hexadecimal, and I want to see this. I want to examine this particular address. So 0x402000, and you can see that this is A, this is B, this is C, and this is D. So all these characters are stored at this particular address. So starting from this address, A is stored, then after B, then C, then D. Our 4 characters are stored like these, like this way. So this double word pointer is pointing at this particular address where our data is stored, and by this method it is moving those data into our EX register. So let's clear the screen and let's execute our program, and let's see if it is storing or not. Our EX register is storing this data or not. So first let's put a breakpoint at start label, and let's use our display command to display our EX values in hexadecimal, and let's also display two instructions of RIP so that we can counter our program where we are. Now let's clear the screen first and let's run our program. Right now you can see this is our first instruction which is going to be executed, and in this part you can see that this A is moving the value ABCD into this EX register using this address. So you can see dword pointer is used to point at this particular address, memory address where our data is stored, and using this address it is moving the data into EX register. And right now you can see EX is 0, and let's execute this whole line using next instruction, and let's see if this EX is storing our value or not. And right now you can see that this our ABCD is stored into this EX register. You can see 61, 62, 63 and 64. This is ABCD. So our ABCD, like our data is, our character data is stored into this EX register. So we can use C continue to exit the program normally after that. This is our exit call which is executed after that. So this is the way how we can move our character bytes into these different size of registers, different data sizes of our registers easily. So if you are facing any kind of confusion problem regarding this, let me know in the comment section. I will surely help you. So till then, goodbye. Hello everyone and welcome to the next part of this tutorial. So in this part I'm going to show you how we can add two integer numbers in our assembly program. So to add two numbers we have to use add instruction in our assembly program. You can see this is our add instruction, and this add instruction is taking two inputs. This is the first input which is our source, and this is the second input which is our destination. So these two inputs will be added, the contents of these two inputs will be added, you can see, and after addition the result will be stored in our destination location. You can see here result will be stored in destination. So result will be stored in our destination location. So let's create a simple program in order to demonstrate this concept. Let's minimize it and let's create a simple program in our Kali Linux terminal. So vim space, then let's name it addition.asm. And first let's create our data section, and in data section let's create two variables a and b. So let's first create a. So this a will be of type byte, not byte this time, but let's create this a of size 8 bytes, which is dq. We are defining quad word. So the size of this a will be 8 bytes, and let's input some data into this a, and in this case let's input 10. So this 10 is stored in this a variable, and let's create our b variable, and same and we specify the data type here. In this case dq means we are again defining quad word, which is 8 bytes in size. So this b will be of 8 bytes in size. The data of b will be 8 bytes in size. So let's use, let's assign 20 to this b variable, and after that let's create our text section, and in text section let's define our entry point by using this global keyword, global then start. So this start will be our entry point, and let's implement our start label here. So let's add these two numbers a and b. So first let's move the value of a into a register and then the value of b into another register. then we have to add those two registers using our add instruction. So let's first move the value of a variable into a register. So let's use move command, not command but instruction. So move, I want to move the value of a into RAX register like this. You can see we have used square brackets here. Square bracket means I am moving the value of a, which is 10 in this case. So I am moving this 10 into RAX here. Let me comment it, moving value of a into RAX. After that, I want to move the value of b, which is 20 here, into RBX again. So let's specify the destination, which is RBX, and let's specify the source here, which is b. So I want to move the value of b variable, which is 20 in this case, this 20, I want to move this 20 into RBX. So let's comment it, moving value of b into RBX. And then let's add these two numbers by using these two registers. So let's use add instruction. So add, then I want to add RAX and RBX. So adding RAX and RBX. Now result will be stored in RAX. So result will be stored in RAX. Remember this part. So result in RAX. So result will be stored in RAX register here. You can see we are adding RBX and RAX values. So in RAX we have a, you can see in RAX we have our a, and in RBX we have our b. So this is a and this is b. So we are adding a and b. So the result will be stored in, after addition of a and b, the result will be stored in our RAX register according to rule. And let's clear the screen and let's continue our program. After addition, let's use our exit system call to exit the program normally. So let's specify, first we have to move the system call number into RAX register. So in this case 60 will be the, like 60 is the system call number for exit. System call, not like this, exit sys call number. Then we have to move the return value in our RDI. So return status value. Then after we have to use our syscall keyword in order to execute this exit system call. So our program is completed. In this program, like you can see, we have just moved. First we have moved the value of a variable into our RAX, then value of b into RBX. Then we have used these two registers RAX and RBX to add. So you can see we are adding RAX and RBX, you can see. So in this case the result will be stored in our RAX register. After that we are exiting. So let's write this file. Let's overwrite this file with W in Vim. Now after that let's use YASM to assemble our source file. So YASM, then we have to specify the format, in this case 64-bit. After that we have to specify our source file, in this case addition.asm. So we have our object file ready to be linked with ld command. So ld space, not ls but ld, addition.o, and we have to specify the output. So addition, simply addition. You can see our file is ready to be loaded in our GDB. So let's adjust our terminals a little bit. Okay, now let's use our GDB to load our addition program to see that how this add is working. So it is loaded in our GDB. Let's first disassemble our start label, and you can see this is our start label, this is our program. And in this program you can see first we are moving. You can see this is our first instruction of move, which is this. These two parts are this. You can see these are the two parts, two lines, in which we are moving the values of A and B. You can see this move, and after that we have used add. We have used add instruction to add RAX and RBX. So let me clear you some parts first. Let me explain you some parts here. You can see here, first we are moving value of A into RAX. You can see here A is like value of A is moved into RX. So in assembly, how this can be done, like in memory, how this can be done, you can see this is the location of our A variable. This is the memory location of our A variable. And in this case, this quad word pointer, because we have declared our A variable quad word, you can see, and it also this quad word pointer is pointing at this particular address at which our A is stored, which is 10. So this 10 is stored at this particular memory address. How we can verify this? We can copy it and we can use xs examine command and let's paste it. You can see at this particular address our 10 is stored. You can see 0A, 0A, this A means 10 in hexadecimal. So this 10 is stored at this particular memory address, which is moved into this RAX in our first move instruction. So we are just moving 10 from this particular address from with the help of this quad word pointer, which is pointing at this particular address. So this is the concept like this. This is a quad word pointer, you can see. So this quad word pointer is pointing at this particular address location, and at this particular address location our 10 is stored. You can see here our data is stored, which is 10 in this case. So this quad word pointer is pointing at this particular memory address at which our 10 is stored, right? And this 10 will be moved into this RX register in our first line of code at this line. So this will be moved into RX. Like the same way, our second value of B, which is stored at this particular memory address 402008. So this this value is stored at this particular address and it will be moved into this RBX register using the same method, using this quad word pointer. After that we are just adding RX and RBX. Let's clear the screen and let's put a breakpoint first at our start, and let's clear the screen first and let's use our display command. Display, I want to display in hexadecimal and I want to display RAX. Then after I want to display RBX value, and after that I want to display two instruction of RIP so that we can counter our program where we are. And let's clear the screen and let's run our program. And you can see right now program is paused at this particular address in memory, from where our first line of instructions are executed. So this is our first line where our A is, this is our A, and our A is stored at this particular memory location where this quad word pointer is pointing right now. So this value which is stored at this particular memory address will be moved into RX, and right now you can see in our display command RX is showing that it is 0 right now, and RBX is also showing 0 value. So after executing this line, after executing this move, what is going to happen? This Rx should be 10. After executing this line, this Rx, the value of Rx should be 10. Let's use next instruction, and you can see this Rx, right now this Rx is 0xa, which is 10. So this is the hexadecimal value. So this is 10. After that, the same way we are going to move our next value into rbx, which is 20. Here you can see b, this is b. So let's use next instruction, and you can see this is our 20. So this is the hexadecimal value of 20, which is 0x14. So our rx is 10 and rbx is 20. After that, we are going to use this add instruction, which will add rbx and rax. So after addition of these two numbers, means after addition of this 10 and 20, the result will be stored in rax. So in the next step, what will happen? This rax should be like this, rax should store the result. So let's execute this line, this add instruction, and you can see that this rx is changed. This rx value is changed from 0xa to 0x1e. So what this 0x1e? This 0x1 is nothing but 0x1e. Let's convert this value into decimal using our print command. Print, I am using print command here. So print in decimal this value. So I want to print this value in decimal. So hit enter, and you can see the value is 30. If you add 10 plus 20, if you add this 10 and this 20, you will get 30 in decimal, and in hexadecimal it is 0x1e. That is why it is showing 0x1e here in rx, which is 30. So our values are added and the result is stored in our rx register, and we can print the rx like this. You can see the value of rx is 30, and after that we can use C to continue our program, and the program exited normally, you can see here. So this is the way how we can add two integer numbers in our assembly program using our add instruction. So that's all for now. If you have any problem regarding this program or regarding this concept, let me know in the comment section. I will surely help you. So till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can subtract our integer numbers in assembly program. So to do subtraction, we have to use sub instruction. This is our sub instruction in assembly, which is used to do subtractions between integer numbers. So this sub instruction takes two inputs. You can see here it is taking two inputs, which is source, this is the source, and this is our destination. So this source will be subtracted. You can see here this source will be subtracted from the destination. So this source will be subtracted from this destination, and the result will be stored in our destination again. So all the result will be stored in our destination part. Like in the same way we have, like in which we did addition in our previous part. In previous part you have seen already that the result were stored in our destination. Like the same way in subtraction also, the result will be stored in our destination location. So let's see how we can do this in our assembly. Let's create a simple program in order to demonstrate this concept. Let's jump into our Linux terminal, Kali Linux terminal. So let's create a simple program called vim subtraction subtraction.asm. And first let's create two variables here, which is in this case a. Let's create this a variable, which is of type dq quad word. So data type, the data type of this a variable is quad word, which is 8 bytes in size. And let's give some, let's assign some value. In this case, let's assign 10 here, and let's create our next variable, which is b here, and let's specify the same data type here also, which is dq, which is defined quad word. We are defining 8 bytes here, 8 bytes of data. So let's assign 100 here. This b is 100. We have assigned 100 into b. After that, let's create our text section, and let's use our global keyword to specify our entry point. In this case, it is start. Let's implement our start label here, and in this start label, first let's move our variable values. Let's move our a and b values into registers. So let's use move. So move, first let me move this a variable value into rax. Let me comment it, moving value a into rax, and like the same way, let's move the value of b variable into rbx register. So moving value b into rbx. After that, we want to use, like, we are going to subtract. We are going to subtract this a from b. So we are subtracting a from b. So for that, we have to use this. I want to subtract rbx and rax. So we are going to subtract this rax from this rbx. This rax means a, and this rbx is 100. So we are subtracting 10 minus, sorry, we are subtracting this 10 from this 100. So it is going to be like this. So 100 minus 10. So this 100 is rbx. Here this 100 is rbx, and this rax is 10. So we are subtracting this 10 from this 100, and the value will be stored in, sorry, not value, but the result will be stored in rbx. So result will be stored in rbx here. So if you subtract 10 from 100, the result will be 90. So the 90 will be stored in rbx in this case. After that, let's use our exit system call to exit our program normally. So move, we have to move our system call number into rax register, which is 60 in this case. So moving syscall number into rax. Then we have to move our return value, which is 0 for this exit system call, into RDI. So return status value into RDI. After that, we have to use our syscall keyword to initiate or to run our exit system call here. Now let's override this using w in our vim. So the file is overwritten, and let's use yasm to assemble our source file. So in this case, let's specify the format, which is in this case 64-bit, and then let's specify our source file, which is subtraction.asm. Right now our object file is created here, and let's use our ld command to link it. So subtraction.o, and in output we specify the output name here. So our file is ready to be loaded in our GDB. So let's load our file in our GDB. Subtraction. So the file is loaded. Now let's first disassemble our start label here. In this start label, you can see this is our code. This is our disassembly code of our assembly program which we have written here. So you can see, let me show you all the lines. So these three lines, you can see these three lines are these three lines. So these are the disassembly of these three lines. So this is our first line. This is our first line. You can see in this first line, we are just moving the value of a into Rax, and in the disassembly of this line is this part, in which you can see this is the memory address which is pointed by this quad word pointer, which is pointed by this quad word. So this quad word pointer is pointing at this particular memory address. So this memory address, like, let's see what is stored at this particular memory address. Copy, and then let's use examine command X, and let's paste it. And you can see at this particular memory address, our 10, which is a in this case, our 10 is stored, this 10. So a variable has a value 10. So this 10 is stored at this particular memory address. So right now what is going on here? This quad word pointer is pointing at this particular memory address, and this memory address is pointing, like, this memory address, at this particular memory address this 10 is stored, this 10 value is stored. So basically this quad word pointer value will be moved into this Rax, like this, whatever it is pointing, wherever this quad word pointer is pointing at in that particular memory address, that value will be moved into this Rax register. Simple. So using this quad word pointer, we are just moving our a value, which is 10 here, into this Rax register, like the same way this quad word pointer is pointing at this particular memory address where our b value is stored. So this b value will be moved into RBX in the second line. Let's clear the screen. After that, we are using this subtraction sub instruction to subtract our numbers, integer numbers, which is Rax and RBX. So we are subtracting this Rax from this RBX value, and after that we are just using our exit system call to exit our program. So let's put a breakpoint here. So using b space, and then we have to specify our start label. So let's put a breakpoint at start, and first let's clear the screen. Let's use display command to display our values. So I want to display Rax. I want to display RBX first, and after that I want to display Rax, and then after I want to display two instructions of RIP so that we can counter our program while it is running. After that, let's run our program. So you can see here that right now RBX value has 0, like IBX value is 0 right now, and RX value is 0 also. So RBX and RX is 0, and we are going to execute our first line of instruction, first line of our assembly instruction, which is move here. So we are just moving our a value from this particular memory address using this quad word pointer into Rax. So after executing this move instruction, what is going to happen? This Rax value should be changed. Rax should be changed to 10 here. Let's execute it using next instruction, and you can see right now it was 0, right now it is 0xa. 0xa means 10. So this a is in hexadecimal, like this value is in hexadecimal. So if you convert this hexadecimal into decimal, you will get 10. So Rax is 10. So we have successfully moved our a value into Rax in the first line, from the first line of instruction, move instruction. Like the same way, we are just moving our next value, which is B, from this particular memory address using this quad word pointer into RBX. You can see RBX is 0 right now. Let's execute it to get the value 100. Right now you can see RBX is 0x64, which is the hexadecimal value of 100. So before that it was 0, right now it is 0x64. So 100 is stored in RBX. Right now the program is going to execute this line, which is sub instruction, in which we are just in which we are subtracting this RAX from this RBX. So if we subtract 10, if we subtract 100 minus, if we subtract 10 from 100, this is 10 and this is 100. If we subtract 10 from 100, what we will get? We will get 90. So this the result will be stored in this RBX register, and this RBX is right now 0x64, which is 100. So after that 90 should be stored in this RBX register. So let's execute this command so that our subtraction will happen. So next instruction, and you can see right now this RBX value is changed from 0x64 to 0x5a. So if you convert this 0x5a using print command, print in decimal 0x5a, what we are getting? 90. So this RBX is 90 right now, which is correct. We have subtracted 10 from 100. If you subtract 10 from 100, you will get 90. So we have subtracted this like this. We have subtracted 10 from 100 and we are getting 90. So this 100 was RBX, and this 10 was RAX, in this case RAX. So we have subtracted and we are getting 90, and this 90 is stored in our RBX register, like this. And you can see clearly RBX is 90 right now. So this RBX is 90. 0x5a means 90, you can see here, and we can confirm it by printing the value of RBX here. You can see RBX is 90. So this subtraction is successfully completed, and after that we can use continue to continue our program. You can see program exited normally. So this is the way how we can subtract any integer number in our assembly program. So if you have any question regarding this concept, let me know in the comment section. I will surely help you, and I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can multiply our integer numbers in assembly program. So multiplication in assembly is a two-step process, and in this two-step process, this is our first step. You can see here in this slide. In the first step, we have to store our first input in RAX register. So in the first step, we have to store our first input in our RAX register in our assembly program. And you can see we have just moved our first number, which is our first input here, into RAX register using our move instruction. So this is the first step. In first step, we are just moving our first input into our RAX register. Now moving on to the next step, which is the step 2 here. In step 2, we will use this IMUL instruction to specify the second input. We use IMUL instruction to specify our second input to multiply with the RAX. So second input will goes into this IMUL instruction. So you can see this is IMUL instruction, and this instruction is taking this second number input, like this is taking second input here. So we have to specify the second input in IMUL instruction. After that, what will happen? This IMUL instruction will take this second number and it will multiply this second number with the RAX value. So it will multiply this second number with this RAX value, and after that it will store the result in RAX register. Remember this part. This part is very important. After multiplication of these two numbers, first and second number, the result will be stored in this RAX register. Remember this part. So this is the two-step process, and let's do it in our assembly program. So this is our Kali Linux terminal, and let's create a simple program here using Vim. So multi multi.asm, let's name it multi.asm, and let's input our code. So first let's create our data section, and in data section let's create two variables. Let's define two variables here. So this is variable A, and the data type of this variable will be DQ. DQ means define quad word. Quad word means we are defining 8 bytes of data, 8 byte of data. So in this case, I want to assign 5 to A, and let's create our B variable, or you can say define our B variable. So the data type would be the same, DQ means 8 bytes, and in this case let's assign 3 here. So in A we are assigning 5, and in B we are assigning 3 here. After that, let's create our text section, and after that let's specify our entry point using this global keyword. So in this case our entry point is start label, and after that let's implement our start label here. So let's just follow our steps. So in the first step, you can see here, in the first step we have to move our first number, means we have to move our first input. So first let's move our data, let's move our A and B into registers, so that we can use these registers in our IMUL instruction. So first let's move our A value, our A variable value, you can see this A variable value into RAX. So we are just performing our first step. We are using, like we are following the first step here. In the first step you can see that we are just moving our first number in our RAX register, and you can see we are moving our first number, which is A here. So we are moving this A number into RAX register, and let's comment it here, moving A value into RAX register. Now after that, first step is completed. We have successfully moved our first input into RAX register. Now we have to use our second step here, like we have to follow the second step here, and in second step we have to use IMUL here. So IMUL, then we have to specify our second input. So in this case the second input is B here, like this. So we cannot, like we cannot use B directly in IMUL instruction here. In place of this B we have to use a register. So what we can do here, first we have to move our B value into RBX register, so that we can use our B value in IMUL instruction. So let's move it here. So we are moving B into RBX register, so that we can use this B into our IMUL register, not register but IMUL instruction. So moving B value into RBX register. Now after that we can use our RBX register here in our IMUL instruction to move our second input. So let's do that. So we are just using RBX here as an input in IMUL instruction. So moving, not moving, but multiply RBX with RAX and result in RAX. So what will happen? This RBX will be multiplied by RAX and the result will be stored in RAX register. It's very easy here. After that, let's use our exit system call to exit our program normally. So let's move 16 to RAX, which is the system call number for exit. So syscall number for exit. After that, we have to move the return value in RDI register of this exit system call. So return status value. After that, we have to use our syscall keyword to initiate our exit system call here. Let's write this file and let's assemble in this terminal. So YASM, then we have to specify the format here. So -F, then ELF 64-bit, and then after we have to specify our source file. So multi.asm, and you can see our object file is generated. Let's link it using LD. So ldmulti.o, we have to specify the object file as an input here, and in output we have to specify any name. In this case I am using multi as an output file name, and you can see our file name is our binary file is generated successfully. Let's load this file in our GDB and let's disassemble our start here. And you can see this is our disassembly of our code. So this is the disassembly, and let me show you these first 3 lines. So these are the first 3 lines. So this is our code here. This corresponds to this line, these 3 lines. So in these 3 lines you can see that we are just moving our values. You can see in the first line we are just moving this A into RAX. You can see here A is moved using this quad word pointer, which is pointing at this particular memory address where where A value is stored. So if we can examine at this particular memory address, you can see 5 is stored. You can see here this 5 is stored. A value is 5. So this 5 is moved using this quad word pointer, which is pointing at this particular address where 5 is stored. So this 5 is moved using this quad word pointer into RAX register in our first line. Like the same way, our second value, which is B here, which is the value 3. So this 3 is moved using again this quad word pointer, which is pointing at this particular memory address where 3 is stored. Let me show you the value of 3 here at this particular address. You can see at this particular address this 3 is stored. So this 3 is moved using this quad word pointer which is pointing at this particular memory address into this RBX. So this 3 is moved into this RBX register. After that, we are using IMUL instruction to multiply this RBX value with rax value, in which it will be multiplied with rax and the result will be stored in rax register after that. And after that you can see this is our exit system call. So everything is clear right now, and let's clear the screen for now. And let's first put a breakpoint at start. After that, let's use some display command. So display, I want to display in hexadecimal, and what I want to display rx value, and then I want to display in hex rbx value as well, and I want to display 2 instructions of RIP so that we can counter our program where we are right now. And after that, let's clear the screen, Control L, and let's run our program. So you can see this is our first line at which the program is paused right now at this particular address, which is our first line, which is this line. You can see in which we are moving our a value using this quad word into RAX, quad word pointer into this RAX register. So right now you can see RX value is 0 right now, and RBX value is also 0 right now. So after executing this line, what will happen? This RX value will be changed. So let's use next instruction to execute this line, and after that you can see RX value has 5 right now. It was 0 before, right now it is 5. So 5 is moved from this A into RX in the first line. After that we are going to move our second value, which is 3 here, which is B. So this B value is moved using this quad word pointer into RBX register. Right now you can see RBX register is 0. So let's execute this instruction, this move instruction, to get the value of B in our RBX register. So let's use next instruction, and you can see that right now RBX has a value 3 here. So both values are set, like our first input and second input are set here, 5 and 3. Now we are going to multiply both of these values, like we are going to multiply RBX with RAX. So you can see we have used IMUL, and in IMUL instruction we have specified our second input, which is RBX. So this RBX will be multiplied by RAX, and the result will be stored in this RAX register. So if we multiply 5 into 3, it will be 15, and that 15 will be stored in RAX register in the next step. So let's execute this line using an next instruction, and you can see that RX is changed from 5 to 15 here. You can see 0xf means 15. This is the hexadecimal value. If you convert RAX in decimal, you can see it is 15. So RAX is 15 right now. So if you multiply 5 into 3, you will get 15. So we have successfully performed, like we have successfully multiplied 2 input values here in our assembly program, which was A and B here, A and B. So if we use C command here to continue our program, the program exits normally using our exit system call. So if you have any question regarding this concept, this multiply concept, let me know in the comment section. I will surely help you. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can perform division arithmetic operation of integer numbers in assembly. So we have to follow 2 steps in order to divide any number in our assembly program. So this is our step 1. You can see here, this is our step 1. So in the first step, we have to store the dividend in our RAX register. So this is step 1. You can see we have used this move instruction to move our dividend into RAX register. After that, in the next step, in step 2, we have to pass the divisor to our idiv instruction. So this is idiv instruction, you can see here, and we have just passed our divisor number. So we have to pass our divisor number into idiv instruction. So these are the 2 steps by which we can divide any number in our assembly program. And in the last, you can see the result will be the quotient part. The quotient part will be stored in RAX register, and the remainder part will be stored in RDX register. Quotient part will be in RAX and remainder part will be in RDX register. So let's divide a number in our assembly program, and let's see how this can be done in assembly. So first let's create a simple program and let's name it div.asm. let's create our data section first. In data section, let's create a variable called a, and not a, but let's name it dividend. This number will be our dividend. So this is our variable name, dividend, and the data type would be dq, means quad word, and which is of 8 bytes in size, and let's assign 17. So our dividend is 17. After that, let's define our second variable, which is divisor. So this is our divisor, and the data type will be the same, dq. And after that, let's divide this 17 with 5. So this is our divisor, which is 5 here. So we have just created 2 variables, dividend. In dividend we have stored 17, and in divisor we have stored 5. So this is our dividend and this is our divisor, and the data type is of 8 byte, which is dq. Dq means define quad word. So this is quad word, which is of 8 byte in size. So both are 8 bytes in size, dividend and divisor, 2 variables. After that, let's create our text section, and in text section let's first define our entry point by using global keyword, in this case start, and let's implement our start label here. So in the first step we have to move our dividend. Let me show you our slide again. So you can see in the first step we have to move our dividend into RAX. So let's perform our first step here. Let's follow, not perform. It was an old slide. Let's close it. So let's move our first part, which is dividend in this case. So move in RAX. So what we want to move? Our dividend. So dividend, dividend. So we are moving our dividend in our RAX register. Let me comment it so that you have a better understanding, I think. Moving dividend in RAX. After that, we want to move our divisor into RBX register. So for that, let's specify the destination first, RBX in this case, and after that let's move our divisor here. So divisor, divisor. So we have just moved our divisor into RBX, and after that let's use our idiv instruction, and in this idiv instruction we have to mention our, we have to give the divisor here. So in this case the divisor is stored in our RBX register. You can see here we have moved this divisor into RBX, so we can give RBX here. So in idiv we have given divisor number here as an input. So what this IDIV will do, it will divide this RAX, like this RBX will be like this RX will be divided by this RBX, which is our divisor. So this is our divisor, RBX is our divisor. Let me comment here, RBX is the divisor, and I think we should write like this, RAX will be divided by RBX, which is in this case divisor. That will be perfect. So after that, let's use our exit system call to exit our program normally. So let's move the exit system call number here in RAX, which is 60, moving syscall number in RAX, and after that let's move the status, return status value in RDI. Let's comment it, return value in RDI. After that, let's use our syscall keyword in order to initiate the exit system call here. Let's use W to write this file, and let's use our YASM to assemble our source file. So in this case, let's first specify our format, which is 64-bit in this case, and then let's specify our source file, in this case div.asm. This is our source file of assembly. Right now we have successfully generated our object file. You can see here div.o. This is our object file. Let's load this file in our, sorry, not now, we have to, I forgot to link it. So ld space, we have to specify our object file as an input, and in output we have to give any name here. In this case I am giving div, and you can see, if we check, you can see that we have successfully generated our binary file, like our assembly program. So let's load this div program into our GDB like this. So this is loaded in our GDB, and let's disassemble our start label here, and you can see this is our disassembled code. And let me show you all the codes. So this is our first three lines of code here. This is the first 3 lines of our disassembly, and this is our, like, these are the 3 lines you can see. So these are the disassembly of these 3 lines. First 3 lines, you can see, first we have just moved our dividend into RAX, then divisor into RBX, then we have used IDIV in order to perform the division operation on our numbers. So let me show you, let me briefly explain you all these 3 lines one by one. So in the first line, we are just moving our first number. In this case, this number is our dividend. You can see here, this is our dividend. So we are moving our dividend into RAX. So how this can be done in our program? This can be done using this quad word pointer. You can see this quad word pointer. So this pointer is pointing at this particular memory address. So if we look at this memory address using examine command in assembly, not assembly but in GDB, you can see that here it is. This is the number. So this 11 is hexadecimal value of 17. If you convert this 11 into decimal, let me show you. I'm just printing this 11 value in decimal using print command in GDB. You can see it is 17. So this is our 17. This is the first value which is stored at this particular address, which is this address. Now at this particular, this value is moving into this RAX register using this quad word pointer, which is pointing at this particular memory address at which this 17 is stored. So this is our first instruction in which this pointer is moving our first value into this RAX register, which is our dividend here, which is our dividend, this part, this 17. After that, like the same way, our divisor, this is our divisor. So this divisor is moved from this particular memory location using this pointer into RBX register. Let me show you the content which is stored at this particular address using examine command, and you can see this is 5. So 5 is our divisor. So this divisor is moved with the help of this quad word pointer into this RBX register. So our second value is moved into RBX like the same way. After that, in the third part, we have used idiv instruction to divide our number. So what it will do, it will use the RBX value to divide this RAX value. So it will use RBX as a divisor to divide this RAX value. RAX value is 17 and this RBX value is 5. So this 17 will be divided by this 5, which is in this idiv instruction. So let's clear the screen for now, and let's put a breakpoint at the start of this program. So let's use b command, b underscore start. So breakpoint has been set, and after that let's use some display command. Let's clear the screen first. Display, I want to display RAX, I want to display RBX, and I want to display RDX. So we are displaying three registers values, RAX, RBX and RDX. Why we are displaying RDX? Let me show you why. We are displaying RDX because we want to see the reminder also. You can see here, according to rule, reminder will be stored if there is any reminder in our calculation, in our divide, that the reminder will be stored in RDX register and the quotient will be stored in RAX register. That is why I am showing RDX register and RAX register. Let me minimize it. After that, I want to display two instructions of RIP so that we can counter our program where we are. After that, let's clear the screen and let's run our program. So right now you can see RAX value is 0, RBX value is also 0 and RDX is also 0 right now, and our program is paused at the first instruction, first line of our program. You can see this is our first line in which our first number, which is our dividend, so this dividend is moved inside this RX register. So let's use ni next instruction to execute our first line of code, which is this part. So after this line of execution, this RAX should be changed with 17, which is our dividend, because we are moving our dividend from this location into RAX. So let's use ni next instruction, and you can see after executing our first line, after executing this part, this first line, this RAX is 17 now. So this RAX was 0, right now it is 17. So first number is moved successfully. Now moving on to second part, we are just going to move our divisor, which is 5 in this case. So this 5 will be moved from this memory address into this RBX. So let's use next instruction, and right now you can see RBX is 5. It was 0 before. So RBX is 5. So this is our divisor and this is our dividend. So RAX and RBX is set up. Now we are going to perform our division using idiv instruction. You can see here. So in idiv we have to mention our divisor only. It will take the dividend from RAX and it will divide accordingly. So in the next phase, like in the next line, it is going to divide. It is going to divide this 17 with 5. So when we divide this 17 with 5, what will be the quotient? The quotient will be 3 and the reminder will be 2, because there will be 2 left after 15 plus 2 17. So 2 will be in reminder part in this rdx will. So this rdx should be 2 after executing this part. So let me execute it using ni, and you can see right now after division what is happened here. Let me draw you a simple picture here to clear the concept. So we are doing this here, like we are doing this thing here. This is 17, this is our divisor, and this is our dividend. So 5 3 5 into 3 times it will be 15 here, and if we subtract we will get 2. So this 2 is our reminder, and this 2 will be stored in our rdx register according to rule. So this reminder will be stored in our rdx register, and this will be stored in our rax register. So this is the rule by which we are storing our results. So you can see this rax is 3, this rax is 3. You can see this rax is 3, this 3 is quotient. You can see if we perform divide we will get 3 as a quotient. So this 3 is here in rax, and remainder is 2 which is stored in this rdx. You can see this is rdx register. So in this rdx register our remainder is stored. So quotient is stored in rax and remainder is stored in rdx. So if we divide this 17 with 5, you can see like this way. So 5 3 is 15, and this 2 will be our reminder, and this 2 will be stored in our rdx register. And you can see clearly here this 2 is stored in our rdx register, and this quotient is stored in our rx register. This rx was 17 before, right now it is 3 because we have successfully calculated our division arithmetic. That is why rx is 3. So rx is quotient and rdx is our reminder, and rbx is still our divisor. So I hope that by using this example your concept is clear by now of dividing any numbers in assembly program. So if you have any question regarding this concept, let me know in the comment section. I will surely help you. Let's continue our program to exit, and I will see you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I'm going to show you how numbers are stored in our CPU registers. So let's begin. So let's take 8-bit register as an example here. First we will take 8-bit register as an example, how the numbers are stored in this 8-bit register. So you can see here this 8-bit register has 2 parts here. You can see this is positive numbers and this is negative numbers. So in this 8-bit register we can store positive numbers as well as negative numbers. So we can store both numbers of negative and positive digits. So let's see how many numbers we can store in this 8-bit register. Like what is the range of numbers which we can store in this 8-bit register. You can see here in this slide, in the positive direction, this is our positive part. In the positive part we can store numbers starting from +1, or you can say starting from 0. This is the center position. So we can store numbers starting from 0 up to +127. And in the negative direction we can store our negative numbers up to -128. So this is the range of numbers in positive and negative directions as well. This is the total range in which we can store our positive and negative numbers. So let me give you a simple example here. In our program, let's create a simple program, and in that program I'm going to explain you the concept of how the numbers are stored in our register, in this 8-bit register. So for that, let's create a very simple program called number. I think we have some files. Let's remove these files first. Let's create a file, a source file called number.asm, and let's create our text section first, and let's use our global keyword to specify our entry point. In this case, start label is our entry point. So let's implement our start label. So in this start label, let's store a number in this 8-bit register. In this case, this is AL. So this AL is our 8-bit register. So we want to store a number which is 120. So I want to storing 120 in 8-bit AL register. So we are storing 120. We are storing this 120 into AL register using move instruction. So we are just moving 120 into AL. So this 120 will be stored in this 8-bit register at this particular part, like in this part. Now after that, I want to store 129. I want to store 129 here. Let's comment it, storing 129 in 8-bit AL register. After that, let's use our exit system call to exit our program normally. For that, let's move our system call number first into RX register, which is 60 here. So 60 is the system call number. So system call number for exit. After that, let's move the return value in the RDI register. So in this case, the return value will be 0 for exit, and return value for exit. After that, let's use our syscall keyword to exit to call exit system call here, to execute this exit system call here. Let's write this file, and let's assemble this source file in our other Kali Linux terminal here. So YSM, then we have to specify the file type. In this case, it is 64-bit. After that, we have to specify the source file, in this case number.asm. So right now we have our object file number.o here, which is ready to be linked. So let's use ld command to link it. So ld number.o, we have to specify the object file as an input, and in output we have to specify a name here. So in this case, I am using number. Right now you can see number binary file is generated here. So let's open our GDB, and let's load this number in this GDB. Now the number binary file is loaded in our GDB, means our assembly program is loaded in this GDB. Let's clear the screen first, and let's disassemble our start label first. And you can see in this disassembly, this is our disassembly, and in this disassembly, first 2 lines are our code. So this is our first 2 lines. This is our first 2 lines. You can see. So this is the disassembly of these 2 lines, and in this disassembly, you can see clearly that first we are moving 120, and this 120 is in hexadecimal form here. So this is going to move into this AL register first. Like the same way, our second value, which is 129, it will move like in the set in the next line. We are just moving our 129 into AL. So these two lines are our data movement here, in which we are just moving 120 and 129 into our AL registers. So let's clear the screen first and let's continue. So let's put a breakpoint at this part. Let's put a breakpoint at this location. So how we can do that? We can use B and then start. We have to specify the start label. So we have used breakpoint at our start label, and let's use our display command to display AL register value here. And after that, I want to display two instruction of RIP, so that we can counter our program where we are right now when the program is running. So let's clear the screen and let's run our program. You can see here that program is paused at our start label here in the first line. And in this first line, first we are moving 120. So we are moving 120. You can see 0x78. This is 120. So we are just moving this 120 into AL register. Right now AL is 0. Now let's execute this first line in which we are moving 120 into AL. And you can see that 120 is stored successfully in our AL register. You can see AL. So 120 is stored in our AL register. And you can see here in our picture here, this is the picture of 8-bit register. So in this case, we are storing this 120. You can see here, we are storing 120 in this 8-bit register, and it is okay right now because this 120 falls in this range, in this number range, in the positive direction. So it's okay. Now 120 is stored successfully in AL. Now after that, we are going to store 129. If you notice, this is 129 and we have the capacity, like this 8-bit register has the capacity to store up to plus 127. It can store up to 127 only, and we are giving 129. So let's see what is going to happen if we want to store 129 in our program in this particular register. What is going to happen? So let's execute our next instruction in which we are moving 129 into AL register. So let's use next instruction and hit enter. Right now you can see that the AL value is changed to minus 127, means we have moved 129. You can see we have moved 129 into AL register, but what is happened here? Minus 127 is showing here. So how like what is this minus 127? We have to understand this part, like we have to understand this concept here. So let's understand it. You can see we have moved 129 in the positive direction. So how many numbers are extra from this 127? If you add, like if you subtract 127 from 129, we will get 2. So 127 plus 2. 127 plus 2 is 129. So this 2 digit is extra, like this 2 count is extra here. So 2 digits are extra. That 2 digit will be shifted in the opposite direction here. That 2 digit will be shifted in the opposite direction here in this register. So it will move in the negative direction here, and in the negative direction it will count 2 digits from here from the last digit. So the last digit is 128, this is minus 128, and it will count from here, like it will count 2 from this particular part. So minus 128, this is first and this is the second, this is the second value. So this is the first one and this is 2. So at the second position it is minus 127. At the second position it is minus 127 here, and that minus 127 is showing at this place in our program. So this is the way how if you try to move more than this number, in this case we are moving 129, so this will going to happen. Whatever the extra numbers you are adding from this 127, like whatever extra number you are giving into this positive direction, that extra number will be added in the opposite direction, and it will point that particular number in the opposite direction. In this case it is pointing at minus 127, which is 2 digits, like which is 2, you can say 2 digits, you can say 2 count, whatever you want to say, but in this case it is moving 2 points in the opposite direction. The first point is minus 128 and the second is minus 127. So in this case it is first it goes here and it will start counting from this particular number in the opposite direction, and after counting you can see it is 2 digits are like 2 is more than 127. So this 2 will be counted like this. This one is minus 120 and the second part is minus 127. This is the second part. So this 127 is stored here in our AL register. So this is how this 8-bit register stores our numbers. So let's create another situation here. Let's create another scenario here in our program. So let's continue it and let's change our program something else. So we have just moved 129. So let's change something here. So let's move a negative number here. So let's move minus 130. Let's move minus 130. You can see we have the capacity to store minus 128 in the negative part, in the negative direction. We can store up to minus 128 here in the negative direction, and we are trying to store minus 130, means it is more than minus 128. It is 2 numbers extra here, like this is minus 128, minus 120 and minus 130. So this is like 2 is extra here. So in this case what is going to happen here, let me show you. If you try to store more than that range, what is going to happen here? So let's quit this and let's try to assemble this program. You can see we have tried to assemble this program, but there is a warning here. This is a warning, and it is giving warning that value does not fit in 8-bit field, because we have crossed this limit. We have crossed this limit. We can only store minus up to minus 128 in the negative direction, but we are trying to store minus 130, and it is not possible. It is not possible. 130 minus 130 is not possible here. That is why it is saying value does not fit in 8-bit field. This is giving warning. So this is how numbers are stored in our 8-bit registers. And let me show you few more, like not few more, but let me show you the other registers limit as well. So in this case this is our 16-bit register, and in this 16-bit register you can see this is the limit. We can store all the positive numbers up to plus 32767, and in the negative direction we can store up to -3276 in this direction. Like the same way, this is our 32-bit register. In this 32-bit register, all the rules will be same, like all the rules which we have seen in our 8-bit register, that rule will be applied in all these registers as well. So in this 32-bit register, you can see that we can store up to +2147483647. So we can store positive numbers up to this range starting from 0, and in negative direction we can store up to -214748, whatever like number this is. So we can store up to this minus, like this negative range. Like the same way, this rule is applied in 64-bit register as well. In the 64-bit register we can store up to, like we can store the positive numbers up to plus this number, whatever is, like this is very huge number. And in the negative direction you can see we can store up to this negative number in the negative direction. So this is the concept of how the numbers are stored in our assembly programming, or you can say that how the numbers are stored in our CPU registers. So this is the concept, and you should try, like you should do some practicals based on this, like this concept. So if you have any problem regarding this, let me know in the comment section. I will surely help you, and I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I am going to show you how overflow flag works in our assembly program. So let's start. So you can see this is our Kali Linux terminal, and this is also our Kali Linux terminal in which we have, like I have logged in here, and this is a picture of 8-bit register, and this is the picture which shows how the numbers are stored in our 8-bit registers. I already explained you everything about this picture in our previous parts, so I'm not going to explain again that part, like that concept here. I can only say that in this 8-bit register numbers are stored, like the positive numbers are stored like this up to plus, like the range of positive numbers which we can store here is up to +127, and the range of negative numbers which we can store here is -128 up to -128. So these are the positive numbers which we can store here, and these are the negative numbers in this 8-bit register. So we will need this picture in order to understand our overflow flag in our registers, in our assembly program. So let's create a simple program in order to demonstrate this concept. So let's name it overflow.asm. First, let's create our data section here. In this data section, we are going to create a variable called a here. So a, we have to specify the data type here, which is byte in this case, and I want to assign a value to this a variable as 5. So we are assigning 5. After that, let's create another variable which is b here, and let's specify the data type as db, means byte, and after that let's assign a value called 7. So we are just assigning 7 to b. So a has 5, b has 7 here. After that, let's create our text section, and in this text section let's specify our entry point using global keyword, global space underscore start. So in this case our start label will be our entry point in this program, and let's implement our start label here. So let's move our a and b into registers, 8-bit registers, so that we can like we are going to add these a and b using add instruction, but before that we have to move the value of a into a register, into 8-bit register, and b as well. So let's first move the value of a into AL register like this. So we are just moving the value of a into AL register here. So let me comment here for your reference, like for your understanding. So moving value of a into AL register. After that we are going to move the value of b into BL register like this. You can see I'm using square brackets here to move the values. So moving value of b into BL register. After that let's add AL and BL, AL and BL. So in this case AL is 5, AL has the value 5 here. You can see this AL has the value a, which is 5. So AL is 5 and we have moved the value of b into BL, which is 7 here. AL is 5 and B is A is 5 and B is 7, which is moved in AL and BL, and we are just adding this AL and BL here. So AL is 5 right now and BL is 7 here. So this 5 and 7 will be added here in this add instruction, and the result will be stored in AL register. Remember, the result will be stored in the destination part, and in this case the destination is AL. So the result will be stored in our AL register. So 5 plus 7, whatever will be the result, that result will be stored in this AL register, this AL. So let's clear the screen and let's comment it. So result of add will be stored in AL register. After that let's use our exit system call to exit our program, to exit our program normally. So we have to first move the system call number 60 into RAX register. So this is the system call number for exit. After that we have to move the return status value, which is 0 here, into RDI. So exit system call return value, or you can say status value. After that we have to use our syscall keyword in order to execute this exit system call. After that let's write this file, means that let's create this file using w command in vim editor, and let's assemble this file in this terminal, in this Kali Linux terminal here. So YSM, then let's specify the format here. So ELF 64-bit, we are assembling this file into 64-bit format. So ELF 64, then we have to specify our source file here. So in this case this source file is overflow.asm, you can see here. So overflow.asm. Right now you can see that our object file is generated. Now let's use this object file to generate our final binary file. So let's use ld, then we have to specify the object file here, overflow.o, and then in output we have to use the name. In this case I am using just overflow. So right now you can see that our file is generated successfully. Let's clear the screen. So let's open our GDB first, and in GDB let's load our overflow file. So overflow. Now overflow file is loaded, and first let's disassemble our start label here. So this is our disassembly of start label. This is the disassembly code of our start label, and in this disassembly you can see that, let me show you this part. So these are the first 3 lines of our start label, and you can see these are the 3 lines in which we are just adding. So these 3 lines are here. So these 3 lines are the disassembly of these 3 lines in which we are just moving our values A and B, and then we are just adding. You can see move, then add, right? So in first move, we are just moving the value of A into AL register, and you can see here the program is using byte pointer here. Program is using byte pointer. This is just a pointer which is pointing at this particular memory address where the value of A is stored. So at this particular memory address, the value of A is stored, which is going to move using move instruction into this AL register. So at this particular memory address, this byte pointer is pointing at this particular memory address at which the value is stored, and that value will be moved into this AL register using this byte pointer. So this is the simple concept here. And let me show you the value which is stored at this particular address, memory address. We can confirm it by using examine command here. So X, then I want to examine byte here, single byte. So X, then B for byte here, single byte, and X means I want to display the value in hex format, hexadecimal format. And then we have to specify the address at which we want to examine. So this is the address at which at this particular address location we want to examine what is stored. So let's hit enter, and you can see that at this particular memory address 5 is stored, and the value of A is 5 right now. You can see that here. So this 5 is stored at the location of A, which is pointed by this byte pointer at this particular memory address. So we have confirmed that 5 is stored, and this 5 will be moved using this byte pointer into this AL register. Simple. So like the same way, our next value, which is B here, so our B value will be moved using this address, address location by using this byte pointer. So this byte pointer is again pointing at this particular memory address at which our B value is stored, which is going to move inside this BL register. Simple. And let's confirm it by let's examine this particular memory address so that we can confirm that what is stored at this particular memory address. So in this case, you can see that 402001, this is the memory address, and you can see we have used the same memory address here, and hit enter, and you can see right now at this particular memory address our B value is stored, means 0x07. This is 7 in hexadecimal. So 7 is stored, and this 7 will be moved into this BL register like the same way it was moving our A value into AL register by using this byte pointer. So this byte pointer is used to point the value at this particular memory address, and this DS is data segment. Don't get confused here. So our value is our values are stored in our data segment. That is why this is DS, and this byte pointer is pointing in this data segment at this particular memory address at which our values are stored, right? Very simple concept. After that, we are just adding AL and BL. And the value of the result of this add will be stored in AL register. So this is very simple concept. So let's clear the screen for now. So let's first put a breakpoint at our start label here. You can using B command here. So breakpoint is set, and after that let's clear the screen by using Ctrl+L, and let's use some display command to display some information while the program is running. So display, I want to display AL value. I want to display the value of AL in hexadecimal format. So let's use this display slash then X. This X is for displaying the value in hexadecimal. That is why I'm using X here. Hit enter, and right now the program is not running. That is why it is showing no registers error. it's okay here. So I want to also display the value of BL here, and I want to display, this is a new command for you, so not new command but this is a new thing for you here. I want to display the flag values, like I want to display the flag register values here, the status, you can say the status flag or you can say simply flags. So I want to display flags, the status of flags in this program while it is running. So how we can do that, we can use e flags here. This is the technique by which we can display the flag status, the flags status of our program while it is running. So display e flags. So through this we can see the flag status of our program at that particular moment when the program is running in each step. Hit enter. Right now program is not running, that is why it is showing error. It's okay here. Now the last part is we have to display, we want to display like 2 instructions of RIP so that we can counter our program, so we can trace our program where we are in that particular situation. So after that, let's clear the screen for now and let's run our program. You can see these are the output of our display command. You can see in the first place we are just displaying the value of AL register in hexadecimal. Right now you can see it is 0. After that, this is our second display in which we are just displaying the value of BL in hexadecimal. You can see it is 0 right now. After that, you can see in the third display, you can see we have E flags. So this E flag is showing the status, the flag status here. In this case, we have only single flag which is set here, which is IF, means interrupt flag. This is just an interrupt flag here. So in this case, only interrupt flag is set here, and in this particular tutorial, in this particular video, we are focusing on overflow flag. So we have to watch here carefully when the overflow flag is set or unset. So after that, we have our fourth display in which we are just displaying our next 2 instructions which is going to be executed through the use of this RIP instruction pointer register. So this is very simple, like this is very simple concept to understand here. Like now let's move on. So the breakpoint is set at our first line here. You can see this is our first line in which we are just moving the first value, means we are just moving the value of A into this AL register. So let's use next instruction, and right now focus on this part, AL and BL. So AL is 0 right now. After executing this, like after executing our first move instruction, this AL should have the value of A here, which is 5. So this AL should be 5 after this, after executing this command. So let's execute it using ni command. So ni, and you can see the AL value is 5 right now. After that, the same way we are moving the next value, means B value, into BL register. You can see right now BL is 0 here. Next instruction, you can see AL is 5, BL is 7. Now AL and BL is ready to be added. In the next instruction, we are just going to add AL and BL. Right now you can see that AL is 5. In the next step, the result will be stored in AL. Remember, the result will be stored in our destination parts, and destination is AL here in this add instruction. So the result will be stored in AL. So focus on this part. So let's use next instruction, and you can see that this is 0xc. AL value is changed to 0xc, means this is the result of our addition. So if we want to find out what is the value of this hexadecimal value, we can use p and d command. It means print in decimal, and we can specify the input here, which is 0xc, and you can see this is 12. So the result is 12, which is stored in this AL. If you add 5 plus 7, you will get 12, and that 12 is showing here in hexadecimal format in our AL register. Right now you can see there is no overflow. Let's jump into, like, let's focus on our overflow flag here. Right now you can see we have added 5 and 7. You can see this is a 5 and this is 7. So we have added 5 and 7 using our 8-bit register, and there is no overflow flag set here. You can see the parity flag is set, interrupt flag was already there, but no overflow. Why? Because there is no overflow in this particular addition. You can see we have taken 5 and 7 and we have added, and the result is 12. The result of this addition is 12. And if you see in this particular diagram, here, what we are getting 12 here. You can see this is our 12, the addition result, which is this part, like this is 12. So we are under the range. We are under the range of this 8-bit register in the positive direction. You can see here in this positive direction, like in this positive part, this is plus 12, means we are getting 12 here, and it means that this is 12. Now it's like it's normal here. There is no problem, like there is no overflow here, because it's under the range. Like our result is under this range, is from 0 up to 1 plus 127. So our result falls in this, like our result falls under this particular range in this 8-bit register. 8-bit means this AL is our 8-bit register. Remember here, AL and BL is our 8-bit register, and we are storing our result in AL register. We are storing our result in this AL register. Remember this. So we are storing our result in AL register, and in this AL register 12 is 12 is okay. Like our result is 12, and this 12 is this 12 falls in this particular number range in our 8-bit register. Now let's change, like let's add something which exceeds this particular range, and let's see how the program behaves. For that, let's remove these things. Like let's erase these sketches first. Now let's change our program a little bit. So let's, in place of 5, let's use 125. In place of A, let's use 125. Sorry, not in place of A, but in A we are just changing number here. So in place of 5 we have just used 125, and in B we are not changing the B, it is 7, so it's okay here. So 125 plus 7, so it will add 125 and 7 here, and the result will be stored in our AL register. So let's see what will happen in this case. And you can see right now, let me show you this. This is our 125, you can see here. So this is our 125, and you can see here this is our 125. So we are just using 125 as our first input here. So let me erase this, and let's overwrite this file so that we can assemble it. So let's continue here, and let's quit this particular GDB session, and let's assemble this program again, YSM. Then let's link it again. Now our file is ready to be loaded in GDB overflow. So let's open our GDB first, and let's use our file to load in our GDB. Let's load our file in our GDB using file command. So after that, let's use the same the same commands in our GDB to display the informations here. So first let's put a breakpoint at our start, and let's disassemble our start label first. You can see that in the first line we are just moving our first value, the value of a, using this byte pointer from this particular address. So this byte pointer is pointing at this particular memory address at which our first value is stored. So right now, if we want to see what is stored at this particular address, we can use x command, x then byte in x. So I want to display the value which is stored at this particular address in hexadecimal format. And you can see this is 7D, 0x7D, and we can also display the value in decimal, I think, using D here. You can see if we specify the format here as decimal, which is D here, in previous part, in previous command we have used x here. So in place of x, if we use D here, D means decimal, so we are displaying the value in decimal. So you can see that 125 is showing here. So we are just moving 125 from this particular memory address using this byte pointer into this AL register. So the first value is moved into AL register here, which is 125 here. After that, like the same way, we are moving our second value from, like, with the help of this byte pointer using this address into this BL register. So our 125 is moved into this AL, and the second value, which is 7, which is moved into this BL register. And after that we are just adding these two values, nothing complex here. So we have already set the breakpoint at start, and after that we have to use our display command to display our, to display some informations here. So let's use display, and I want to display the value of AL here, and I want to also display the value of BL here, and after that I want to display the flags here, so E flags. After that I want to display two instructions of RIP, so that we can trace our program when the program is running. So let's run the program using run command, and you can see right now the value of AL, this, like the AL register has 0 right now, BL register has 0, and in E flags, like in the flags, you can see our only interrupt flag is set right now. So right now the program is going to move our first value from this particular memory address into this AL register, and then, like the same way, it will move our second value into BL register. So we have to focus on these parts, AL and BL, right now. So let's execute it using next instruction, and you can see this AL is 125 right now. So 125 is moved into AL register. After that the next value, which is B, is moved into BL register. Right now BL is 0. So let's use next instruction, and you can see that BL is 7 right now. And you can see the both numbers, like both inputs are ready to be added using this add instruction here. So we are just going to add BL and AL here. So let's use next instruction, and you can see the result should be stored in AL register. You can see right now, you can see the result is -124. The result is -124. Why there is -124? If you add 125 plus 7, what you will get? Generally in mathematics, if you add 125 plus 7, what you will get? You will get, I think, 132. We will get 132 as a result in, like, in our general mathematics. But here it is giving -124. It is giving -124. Let me confirm you why it is giving -124. it is giving minus 124 because focus on this 8-bit register. We are storing our result in 8-bit register here. So you can see if you add, like it is giving minus 124. If you like, we are just adding, let's focus here. We are adding 125 plus 7. You can see this is our 125. Focus on this part. This is our 125, not 127. So this is our 125 in our positive direction because we are adding two positive numbers. So in this case, this is 125 and we are adding 7. In this 125, we are adding 7. So 125 plus 7, let's count it in this particular range. So 125 plus 7 means 120 up to 132 in general. So 125, you can see this is our first 1, 2. So 125, 126, 127. After 127, the program will shift here. Program will shift at this direction. Program will shift at this direction and it will continue to count the numbers, like it will continue to add numbers in this case. So 1 and 2, then 3, then 4, then 5, then 6, then 7. You can see like this. 124 plus 7 means 125, 125 plus 7, 125, then 126, 127. The range is like the range is you can say it is out of range. After after counting 2, like after adding 2 number, there is no numbers left. So in this case, what is going to happen? This will shift. The program will shift from this direction to negative direction, and it will continue to count. So we have counted 2. Then after that, this is 3, 4, 5, 6, and 7. In the 7th position, you can see this is our 7th position. At this 7th position, minus 124 is there. That is why the program is showing us here. You can see the program is showing minus 124. The result of these two numbers is minus 124 here in AL register, because we are adding in 8-bit register. So this is happening here, and you can see this is an overflow, means we have overflowed this range. We have overflowed this positive range, this part. We have overflowed this positive range, and because of that, it is the program is shifted towards this negative part. That is why this is an overflow. So in this case, this is an overflow. So that is why if we exceeds this part, this range, what will happen? Our overflow flag is set here. You can see that there is an overflow flag set. This is our overflow, and this is the concept of overflow, because there is an overflow in this particular 8-bit register in which we are adding our, like we are storing our addition, like in which we are storing our result here. So this is an arithmetic operation. So in every arithmetic operation, arithmetic and logical operation, I will show you the logical operations in the later videos, but here the concept is that in every arithmetic operation, when there is an overflow in the registers, whether it is 8-bit register, whether it is 16-bit, 32-bit and 64-bit, this rule is applied to every other registers as well. Means in other sizes, you can say the other registers as well, means 16-bit, 32-bit and 64-bit. So this rule is applied in every other registers as well, like every other sizes as well. So this is an overflow. This is an overflow. That is why this overflow flag is set here. OF means overflow register. Sorry, not register, but status. So there is an overflow in this program. That is why in the status you can see there is an overflow flag set. Why? Because we have exceeded the range here. We have exceeded this particular positive range, which jumps into this negative range, negative part in this register. That is why there is an overflow, and that is why in place of 132 it is showing the value in -124. It is showing -124, which is this, and it has counted from this 125 like this 1 2, and then it shifted towards negative part, and it has continued to count from in the reverse direction in negative part. So 128, 127 like this, 3 4 5 6, and then 7. At the 7th part it is -128, and because it has jumped from this particular range to the negative part, for that reason the overflow flag is set, because we have overflowed. The result is overflowed in this 8-bit register. I hope this concept is clear by now for you, and if you have any confusion regarding this concept, let me know in the comment section. I will surely help you, and try to practice it with different numbers, then you can understand it very well. I hope your concept will be clear by now. So I will see you in the next part. If you have any problem regarding this, any confusion, let comment it. I will surely help you there. So that's all for now, and I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part we will look at carry flag. So let's see how this carry flag works in our assembly program. You can see, according to definition, carry flag is set when there is a carry left in arithmetic and logical operations. So when there is a carry in any arithmetic and logical operations, then there will be carry flag set in our assembly program. So let's try to understand this concept, this carry flag concept, with a simple example here in this slide. You can see this is just an example. In this example we are adding two numbers. We are adding just two numbers. You can see this is our first number, like this is our first number, which is 128, and this is our second number. We are just adding these two numbers using our 8-bit registers. You can see we are just moving 128 into AL register using move, and then we are just moving 128 into BL here using move command, not command but instruction. So we are just moving the numbers into AL and BL, and after that we are just using add instruction to add these two numbers AL and BL and store the result in AL here. And these are the binary representation of these numbers. So this is the binary representation of 128, and this is also the binary representation of 128 here. And the result is, like we have in this example, this is the result of binary addition of these two numbers. You can see here. So let me calculate this for you. Let's try to understand the concept here, the concept of carry flag, how this carry flag works with this simple example. You can see we are adding 128 and 128, and this is the result here. So let's add manually here. Let's add these binary numbers manually. You can see this is our first number, which is 0 and 0. So this 0 and 0 will be 0. Again this 0 and 0 will be 0. This is very simple calculation. Now this 0 and this 0 will be 0 here. Like the same way, next 0 is 0, then 0 plus 0 will be 0, 0 plus 0 will be 0, then 0 will be 0. In the last part, you can see in this part, this 1 plus 1, if we add 1 plus 1 in binary, 1 plus 1 like this, if we 1 plus 1 in binary, we will get 10. The result is 10. Now what is happening here? We put 0 here. So there is a 0 here, and this 1 will be carry here. So this 1 will be carry here. So there is a carry. So in this operation, in the last part, you can see 1 plus 1 is 10, and in 10 we are placing 0 here, and carry is 1. This is carry 1. So there is a carry in this addition, in this arithmetic part, like in this arithmetic operation there is a carry. So this is the carry, this is the carry. Because of this carry, the carry flag will be set in our assembly program. So let me erase all the parts and let me show you the presentation here. You can see there is a carry. So if there is a carry like this in this operation, there is a carry one left here in this arithmetic operation, in this arithmetic add operation where we have added 128 plus 128. So the result of this add operation is a carry. There is a carry left in this arithmetic operation. Because of this carry, the carry flag will be set in our program. This is very simple concept, nothing more complex, nothing complex here. So if there is a carry like this in this 8-bit register, like this rule is applied in other registers as well, this rule is applied in the same way in other registers as well. When there is a carry left in any register, then the carry flag will be set, then the carry flag will be set like this. So let's implement the same example in our assembly program and let's see how this carry flag is set when we add these two numbers in our assembly program. And let's see. So let's create a simple program called carry.asm and let's create our text section here. We are not using variables here in this part. We are just using direct numbers into our register. We are just going to move numbers into our registers directly. So first we are going to create our text section. In text section, let's specify our entry point using global keyword here. So this start is our entry point in this case, and let's implement our start label here. Now first let's move our first number into our AL register, which is 128 in this case. Let me comment it, moving 128 into AL register. Then we are going to move our next number, which is again 128 into BL register. So we are moving 128 into BL register. After that we are just adding using add instruction AL and BL. So adding AL and BL, result in carry, resulting carry. I don't know if my English is correct here or not, but the meaning is that this addition will result carry. So after that let's use our exit system call to exit our program here. So exit system call. So for exit system call, first we have to use, we have to move our system call number, which is 60 into RX register, and let's comment it, moving syscall number, not moving but system call number. Then we have to move the return status value here. So in this case 0 in RDI, system call return value. After that we have to specify our syscall keyword in order to execute our exit system call. Now let's write this file and let's assemble it using YSM. So YSM -f and ELF64, because we are going to generate our object file in 64-bit mode. So that is why -f and ELF64. After that we have to specify our source file. In this case the source file is carry.asm. Right now our carry.object file, like carry.o means object file, is generated here, and let's use it to create our binary file. So ld, then we have to specify our object file here, and after that we have to specify the output name. In this case I am using the same name, carry. Right now you can see that our carry file is generated. Now let's open our GDB and let's load this carry file into our GDB using file command. So this file is loaded, and let's first disassemble our start label, and you can see this is our disassembly of our start label. And in this start label we have used these 3 instructions to add our numbers. So these are the 3 instructions. Let me show you like this. So these are the three instructions which we have used in order to add our numbers using AL and BL register. So in this case you can see that this first number, which is 128, this is written in hex here, hexadecimal form. 0x80 is the hexadecimal representation of 128 here. So this is the 128. So this 128 is moved into AL, and after that this 128 is moved into BL again. So we are just using move instruction to move 128 into AL and BL. After that we are just adding AL and BL. So everything is clear by now. After that we have our system call, exit system call here. This is our exit system call. So everything is clear right now, and let's clear the screen first, and let's first put a breakpoint at our start label. After that let's use some display command to display some information while the program is running. So let's clear the screen first and let's use display command. So display, I want to display AL, then I want to display BL, and then I want to display, let's delete for the moment, like let's delete display or display. I want to display the values in binary form, because we can like we are doing our arithmetic operation in binary here. That is why we need to see the values in binary form. So for that we have to display the values of AL and BL in binary here. So for that let's delete our display first. So delete display 1, and then also we want to delete our display 2 here. See, these are the display numbers. You can see this is the first. I have deleted this first display, and I have deleted the second display also using this command, delete command. So this is delete, then display, then I want to delete the first display. So this is the first display, and like the same way I am going, like I have deleted the second part here. Sorry, this is the second part. So anyway, let's clear the screen first and let's use display again. So display, I want to display in binary form. So T is used for binary format. So T is used here. So I am using T here to display the numbers in binary form, whatever is stored in our AL register here. So it will display the values in binary format here. Hit enter, and again I want to display the value of value of BL register into binary form. Then I want to display E flags, means I want to display the flag status for using E flag variable here. After that we have to display 2 instructions of our RIP so that we can counter our program when it is running. So everything is set. Let's clear the screen by using Ctrl+L and let's run our program. You can see the program has paused at our first line, like at this part. Our program is paused at this line right now. You can see in which, like in this line, we are just moving 128 into this AL register. you can see right now this AL is 0 and this BL is also 0, and in flag status you can see there is only interrupt flag set right now. So we have to watch for carry flag here. Like we have to check if carry flag is like if carry flag will be set after this addition operation or not. So let's execute our first part, like let's execute our first line in which we are just moving 128 into this AL register. So let's use next instruction, and you can see our first value is moved into this AL register. This is 128 in binary format. This is in binary form, and this is exactly the same as we have seen in our presentation here. You can see this is exactly the same. This is 1 then 7 zeros, so this is 128. So you can see this is 1 and then 7 zeros, so this is our AL. So this is our 128 which is moved into AL register. After that we are doing the same thing, we are just moving 128 into BL. So this BL will contain 128 in binary in the next step. So let's execute it using NI, and you can see this is exactly the same. So 128 and 128 is stored in our AL and BL. Right now we are going to add these two values, and the final value will be stored in our AL register. So we have to check this part here. So we have to focus on this E flag part here. In this E flag, if there is a carry, so there will be a carry, because you can see in the last part this 1 plus when this 1 and 1 will be added, there will be a carry. There will be a carry left, and because of that carry, the carry flag should be set in the program. So in this particular column, not column you can say, but in this particular bracket, there should be a carry flag set in the like after the add instruction, after executing this add instruction, because there is a carry. So let's execute next instruction, and right now you can see in the E flags carry flag is set. You can see this carry flag is set. Why there is a carry flag set? Because in our arithmetic operation, you can see this AL, the result is stored in our AL register right now. You can see when we add these two numbers in binary, then we will get 0 in our AL register. Let me show you our presentation here. You can see when we add 1 plus 1, 1 plus 1 will be 10. So the 0 is here and carry is 1, like the 1 carry is left here. You can see. So the result is 0 here. The result is stored in our AL register here, and the AL value is 0, all the zeros here, and that 1 carry is left here. So because of this 1, which is a carry, our carry flag is set. You can see this is 0, AL is 0, and there is a carry. Because of that carry, you can see the status is showing that there is a carry because of this carry flag. So if there is a carry flag set here, it means there is a carry in your arithmetic and logical operation. Whatever arithmetic and logical operations you are doing in your program, if there is a carry like this, then carry flag will be set. Carry flag will be set in this particular situation. So this was all about carry flag. So this is carry flag set when there is a carry in your arithmetic and logical operations. So let's continue our program, and if you have any problem regarding this concept, let me know in the comment section. I will surely help you. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part we will look at parity flag. So let's see what this parity flag is and how this parity flag works. So this is just simple definition of parity flag, and you can see here the parity flag is a status flag. I already told you in my previous basic videos that this parity flag is a status flag, which indicates whether the binary number of set bits in the result of an operation is even or odd. If the number of set bits is even, the parity flag is set to 1. If it's odd, then the parity flag is set to 0. So if you don't understand this definition, don't worry. We will do, like, I will show you the practical way how you can understand this parity flag here. So let's move on to our example to understand this parity flag. You can see this is simple example. In this example, you can see here we have used 3 instruction, means 2 move and 1 add instruction. We are just adding 2 numbers here, nothing more like nothing complicated here. We are just adding 12 and 2. We are just adding 2 numbers here, 12 and 2. Using this move instruction, we have moved, like we are moving this 12 into AL and this 2 into BL, and then after we are just using add instruction to add AL and BL. This is very simple. So in this example, you can see if we convert this 12 into binary form, if we convert this 12 number into binary form, we will get 1100. You can see here. And if we convert 2 in binary, we will get 10 here, 0010. This is the binary representation of 2. So we are adding these 2 numbers. We are adding 12 and 2. So in binary, if we add these 2 numbers, what we will get? You can see 0 plus 0 will be 0 here. If we add 0 plus 1, we will get 1. If we add 1 plus 0, then we will get 1. Then if we add 1 plus 0, then we will get 1. So this is overall the result of these 2 binary number addition. So if we add these 2 binary, we will get this. And in this result, you can see we have 3 1. We have 3 ones here, 1 1 and 1, total 3 1. So if we count these ones, we will get 3. And this 3 is an odd number. This 3 is odd number. Because of that, parity flag will not be set. Parity flag is not set in this condition. You can see parity, P for parity. Just think of it like pair. This is indicating pair. And which pair? One pair, like this 1 number pair. So if this 1 is in pair, you can see it is not in pair. Pair means 2. So it is not in pair, it is in 3. Like if we pair it, like if we pair this 1 and 1, this is 1 pair. And if we pair this 1, you can see there is no other numbers to pair this 1. That is why it is not paired, like this number is not in pair. So that P is for pair. Okay, if you're not like it, like this is just simple concept. Parity flag means pair. You can see this is odd, means it is not in pair. This is odd. So because of this, parity flag will not be set. Because of this result, this is 3. If we add these ones, we will get 3. Because of 3, this is an odd number. In this case, when the result is odd, the parity flag will not be set. But in other case, if we change the number, you can see we have changed this number. Like the first number is 12, the second number is 3. So in this case, you can see we are adding 12 and 3. So this is the binary representation here. In this binary representation, if we add, let's add it. So 0 plus 1 will be 1. 0 plus 1 will be 1. 1 plus 0 will be 1. And in the last, 1 plus 0 will be 1. So this is the result here. This is the result of addition. This is in binary form. So if you add it 1, 2, 3 and 4, if you add all the ones here, we will get 4. and this 4 is even number. This 4 is an even number. So that is like, because of this even number, parity flag will be set. It will indicate that your result all the bits are in pair. All the bits are in pair. All the one bit are in pair. You can see this is in pair. These numbers are in pair. This is one pair. This is one pair. That is why it is parity flag. Try to understand this parity flag. So which parity? The one number parity. This one number is the pair, not 0. Like, don't confuse. Like, if I am talking about parity, it is not counting 0 here. It is counting 1 only. So it is pairing 1 only, not zeros. Okay. So total, if you count these ones, you will get 4. So 4 is an even number. Okay. If it was an odd, like in the previous, it was odd. So in this odd, if the number is odd, parity flag will not be set, and in the even, the parity flag will be set. Very simple concept. You have just count these ones. If the result is even, then parity flag will be set. If the result is odd, then the parity flag will not be set. It's very simple concept. So let's implement the same thing like this example in our assembly program, and let's see how this works. So let's create a file, a source file called parity.asm. Parity.asm, and let's create our text section first, and in that text section, let's define our entry point using global keyword, and in this case the entry point will be start label. And let's try to implement our start label here. So first let's move our first number in our AL register. So in this case the first number was 12, so we are just moving 12 into AL register. After that we are going to move our next number, which is 2 in this case, so we are just moving 2 into BL register. After that we are going to add these two numbers using these registers. So AL has 12 and BL has 2. So in this case we are adding AL and BL. Let's comment it, adding AL and BL. Now after that, let's use our exit system call to exit our program. So for that, first we have to move our system call number, which is 60, into RX register, and let's comment it, system call number for exit. After that we have to move the return value or return value status in RDI register. So return value status, or you can say simply return value. After that we have to use syscall keyword in order to execute our exit system call. Let's write this file and let's use ysm to assemble our source file. So we have to specify the format here, ELF64, which is 64, like indicating 64-bit. So after that we have to specify our source file here, in this case parity.asm. So our object file is ready to be linked. You can see parity.o. So let's use our ld command in order to generate our final binary file. So ld, and then we have to specify the object file as an input, and in output we have to specify a file name. In this case I am specifying parity here, and you can see we have successfully generated our binary file parity here. So let's open our GDB first and let's load our parity using file command. Now this file is loaded in our GDB, and first let's disassemble our start label. So this is the disassembly of our code, and let me show you the codes here. So this is the first 3 lines of our source code here, you can see. So this is the first 3 instructions, like this is the disassembly of our first 3 instructions here, you can see. So you can see in the first part we are just moving 12 into AL. You can see this is 12, which is in hexadecimal, so we are moving this 12 into AL. Like the same way we are just moving this 2 into BL, exactly the same. We are just moving 12 into AL, 2 into BL. After that we are just adding this AL and BL using add instruction. You can see here add. After that we have our exit system call. This is our exit system call, and this is exactly this. This is the disassembly of this part. You can see we are just moving this 60 into RX, then 0 into RDA, then we have our syscall keyword. So this was the just overview of our disassembly. So let's clean the screen. Now after that, let's put a breakpoint on the start label using B command, and after that let's use our display. Let's use our display command to display the information while the program is running. So let's use display. I want to display the values in binary format. So display hyphen, not hyphen, but /t, T for binary. So I want to display AL. I want to display AL value in binary form. After that I want to display the BL register value in binary form. Then I am going to use display to display the flag status. And after that I am going to display 2 instructions of RIP so that we can counter our program when we execute our program, like when we run our program. So let's clear the screen and let's run the program, and you can see the program is paused at the first line of our program. You can see this arrow, and program is paused at this particular memory address in our program, which is the first line of our code. You can see in this first line we are just moving this 12 into AL. You can see here this 12 into AL. So this is our first line, and in the display output you can see this is the first display in which we are just printing the value of AL register into binary form. Right now it is 0. This AL has 0 value, and BL is also 0 here, you can see, and this is the status of our flags here. You can see this is interrupt flag only right now by default. So let's execute our first line and let's see if this AL is changing its value or not. Let's use next instruction, and right now you can see this AL has this binary value, which is nothing but 12. So this 12 is converted into binary in this AL. So this is our 12. So first value is moved into this AL register. Right now the program is going to move the next value, which is 2, into BL register. So right now you can see BL is 0. So let's execute it, and you can see right now that BL is changed to this 10 in binary, which is 2. And after that we are going to add these 2 numbers. We are going to add BL and AL, and the result will be stored in AL register. So after that, let me show you our presentation. So what is going to happen, we are just adding 12 and 2. This is the binary representation. You can see this is 10, this is the 2. So when we add these, we will get 3 1s in binary. We will get these 3 1s after adding, and if you count these 3 1, we will get 3, which is odd number. In this case the parity flag will not be set. And let's see, I think it was previous PDF. Let's close it. So right now we are going to add AL and BL, and let's see if the parity flag is set here or not. So let's use next instruction, and you can see there is no parity flag set. Why? Because you can see this is the result. The result is stored in AL register. So in AL register you can see this is 3. If you count the 1 here, we will get 3, and 3 is an odd number. So 3 is an odd number. Because of that, parity flag will not be set because of this odd number, this odd result here. If the result is even, then the parity flag will be set. So let's create that situation as well. So let's change the number. Let's change the number to let's change our second number to 3 here. So let's change it here. Let's, in place of 2, let's change it to 3. So let's change here also 3, and let's overwrite this file, and let's quit our GDB, and let's assemble this source file again, and let's link it. And right now we have our parity file ready to be loaded in GDB. So let's load it again, parity, and let's disassemble our start. All the code is same, you can see still only this line is changed. You can see here, in place of 2 we are just moving 3. You can see we are just moving 3, so this is 3, and after that we are just adding both of these numbers, AL and BL. So let's put a breakpoint first, and after that let's use our display command. So display, I want to display in binary, I want to display AL, and I want to display BL as well in binary, and I want to display 2 instructions of RIP so that we can counter our program where we are when the program is running. And after that I want to display our flag status flags. So E flags. Now let's clear the screen and let's run our program. So right now you can see in our display, these are the display. This is our AL, which is 0 right now, and in the second display we have our BL register, which is also 0, and then these are the instructions which is going to be executed in the next step. So after that, in the fourth display we have our flags, like status flags. Right now this is the default value, which is interrupt flag, like IF. So anyway, we are going to first, we are going to move our first value into AL register, like this is the first value 12, which is going to move into AL here. So this is our 12, which is going to move into AL. Right now AL is 0. So let's execute it using next instruction. You can see that 12 is moved into this AL register, and this is the binary representation of 12, which is stored in AL register right now. And in the next step we are going to move this 3 into BL. So let's use next instruction, and right now you can see 3 is moved into this BL register. You can see it is 1 1. This is in binary format. So after that we are going to add these 2 numbers. So we are going to add these 2 binary numbers, and the result will be stored in our AL register. Result will be stored in our AL register here. So let's execute it and hit enter, and you can see here that this is our result. Like the result is stored in our AL register, which is 4 ones in binary. So if we count this one, we will get 4 here. If we count these ones, if we count these ones, we will get 4, and 4 is even number. 4 is even number. So when the result of this, like when the result is 4 of this binary, which is an even, so in that case what is going to happen? The parity flag is set. Right now you can see that parity flag is set here. You can see here parity flag is set. PF means parity flag, because of this value. because of this result. In this result, you can see in this binary result 4 1 is there, and 4 1 is there is 4 means even. So this number is even, that is why PF flag is set here. Let's clear it, and right now you can see PF flag is set because of this result. In this result we have 4 ones, 4 is an even, that is why parity flag is set. So this rule is applied in all other registers of different sizes. So this is standard rule here, so it will be applied to other registers as well. So let's continue our program, and program exited normally. So if you have any confusion problem regarding this concept, let me know in the comment section. I will surely help you. So till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. In this part we will see how we can move strings in assembly programming. So let's take a simple example to understand this concept. Suppose we want to move this string which is stored in memory to another memory location. In the first step, we need to clear the direction flag using CLD instruction. Now we need to set up a source pointer register which points to the source string memory address. So in this case, the source pointer will be our RSI register which points to the string source memory address location. Now the source pointer is set. Let's set up the destination pointer register which points to the destination memory address where we want to move our source string. So in this case, we will use RDI register which points to the destination memory address location where we want to move our string. Now after setting up the source and destination pointer registers, we use move string instruction to move our string from source location to destination location. If we want to move a single byte, then we have to use move SB, which will move a single byte from the source string to the destination memory location. In this move SB instruction, this S means string and this B means byte. So it is move string byte. If we want to move 2 bytes at once, then we have to use move SW, which will move 2 bytes from the source string to the destination memory location. In this move SW instruction, this W means word, so this means move 2 bytes. Now if we want to move 4 bytes, then we can use move SD instruction which will move 4 bytes from the source string to the destination memory location. In this move SD instruction, this D means double word, so this means move 4 bytes. In the same way, we can move 8 bytes at once with move SQ instruction which will move 8 bytes at once from the source string to the destination memory location. In this move SQ instruction, this Q means quad word, so this means move 8 bytes. So this is how we can move strings in our assembly programming. So that's all for now. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. I will see you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. In the previous part, I have explained to you the basic concept of how strings are moved in assembly. In this part, I will show you the practical demonstration of how we can move strings in an assembly program. So let's create our source file in our Kali Linux terminal and name this file as my_string.asm. Now let's first create our data section. Now in this data section, let's create our source string variable. Let's name this variable as source_string and store some character bytes into this variable. After this, let's create our BSS section. Now in this BSS section, let's create our destination string variable. Let's name this variable as destination underscore string and reserve 15 bytes in this variable. Now our source and destination variables are set up. Now let's create our text section. Let's specify the entry point using global keyword, and in this case the entry point will be start label. Let's write our start label. Before moving our strings, first we need to clear the direction flag using CLD instruction. After this, we need to set up the source pointer register, which will point to the source string memory address location. In this case, our source string is our source underscore string variable. So we will load the source underscore string address location to RSI register with the help of LEA instruction. In the same way, we need to set up this destination pointer register, which will point to the destination string memory address where we want to send our string. In this case, our destination memory address is our destination underscore string variable memory address location. So we will load the destination underscore string address location to RDI register with the help of LEA instruction. Now our source and destination pointers are set up. Let's move 1 byte from the source to the destination location using move SB instruction. After this, let's write our exit system call to exit our program normally. Let's save this file. Now let's assemble this file using YASM. I have given -G DWARF2 option to include debugging symbols in this program for easy debugging. Now let's link our object file and generate the final binary file. Our final binary file is generated. Let's load it in GDB. Our binary file is loaded in GDB. Let's disassemble our start label first. You can see this is our disassembly of our assembly program. In this disassembly, you can see in this second line, the program is loading the memory address of our source string to RSI register using LEA instruction. In the same way, it is loading the destination string memory address to RDI register using LEA instruction. Now let me explain this line here. In this line, program is moving single byte from the source byte pointer, which is pointed by this RSI register, to the destination byte pointer, which is pointed by this RDI register. After that, we have our exit system call. Let's put a breakpoint at our start label. Let's use the display command to display the value of our source underscore string variable and destination underscore string variable so that we can see the string data movement when the program runs. Let's clear the screen first and run the program. Now the program is paused at the start label. The program is going to clear the direction flag using CLD. Let's use the ni command to execute this line. Right now you can see the program is going to load the source underscore string variable memory address location into RSI register. Let's execute this line to load the source underscore string address to RSI register. Right now you can see the source underscore string address location is loaded in the RSI register here. Now the program is going to load the destination underscore string address to the RDI register. Let's execute this line to load the destination underscore string address to RDI register. Right now you can see the destination string address is loaded in RDI register here. Now the program is going to move a single byte from the source string to destination string using this moves instruction. Let's execute this line using the ni command. Now you can see the program has successfully moved the first byte from the source string to destination string variable location here. After that, let's use C to continue our program so that program executes the exit system call and exits normally. So you can see how strings can be moved from source to destination location in assembly programs. Now you can change this movesb to movesw to move 2 bytes at once. And if you want to move 4 bytes, you can use movesd. Likewise, you can move 8 bytes using movesq in this program. So that's all for now, and I hope that by now you have a clear understanding of how we can move strings in the assembly program. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. I will see you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, I am going to explain you how the direction flag affects the string movements in assembly programs. So let's take a simple example to understand the working of direction flag. Suppose we have a string in memory which we want to move to another location in memory. For this, first we set up the source string memory address pointer to RSI register. Like the same way, we set up the destination string memory location address pointer to RDI register. Now let's set the direction flag on. Now let's move a single byte from this source string location to destination string memory location. You can see the first byte is moved in the destination location. But here, if you notice, the RSI register pointer is shifted 1 byte in the backward direction from the source string memory location. Let's try to move 2 bytes with movesw instruction here. You can see now the source RSI register pointer is shifted 2 bytes in the backward direction in the source string memory location. And in the destination location, the RDI pointer is also shifted 2 bytes in the backward direction. Now let's disable the direction flag and see how this affects the string movement here. Let's move a single byte again using movesb instruction. Now you can see after moving 1 byte from the source to destination, the source RSI register pointer is pointing to the next immediate byte location in the source string memory location. Now let's use movesw instruction to move 2 bytes from the source to destination here. You can see after moving 2 more bytes from the source string memory location, the RSI register pointer is shifted 2 bytes in the forward direction from the previous location, and this has the same effect on the destination RDI register pointer also. So this is how this direction flag affects the string movement in our assembly programming. I hope that by now you have a clear understanding of how the direction flag affects the string movement in assembly. So that's all for now. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. I will see you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, I am going to show you how to move an entire string at once using REP instruction. Let's take a simple example to understand this concept. Suppose this is a string which we want to move to another location. So in order to move this whole string, we first need to set up the source and destination pointers, which are RSI and RDI registers. Then we need to specify the byte count which we want to move in the RCX register. In this case, we want to move this whole string, which is test string, which is of 11 bytes. So the RCX value will be 11 here. Then we use REP instruction with the movesb instruction, which repeats the byte movement until the RCX value is 0. You can see all the bytes are moved one by one until the RCX value is decremented to 0. This is how REP instruction works with the MOVES instruction. We can move bytes, word, double word and quad word using this REP instruction with the MOVES instruction. So let's jump into the Kali Linux terminal and use this repeat instruction in our assembly program to move a string from one location to another location. Let's name our program as rep_move.asm. Let's create our data section. In this data section, let's create a variable var1 and store some character bytes. Now let's create our BSS section. In this BSS section, let's create a variable var2 and reserve 15 bytes. Now let's create our text section. In this text section, let's use the global keyword to specify the entry point, and in this case, the entry point for this program will be _start label. Now let's write our start label. First, let's clear the direction flag using CLD instruction. Let's specify the byte count in the RCX register which we want to move. Then let's load the RSI register to point to the source string memory address. Then let's load the RDA register to point to the destination string memory address where we want to move our string. Now let's use a repeat instruction to move bytes from source var1 variable to destination var2 variable. After this, let's use the exit system call to exit our program safely. Let's save this file. Now let's assemble it using YASM. Now let's link it using LD. Now our binary file is generated. Let's load it in GDB. First, let's disassemble our program and see the disassembly. Let's put a breakpoint at our start label. Let's use display command to display the source and destination variable string values to see the string movement in real time when the program is in running state. Now let's run it. You can see the program is going to clear the direction flag using CLD instruction. Let's execute this line using the ni command. Now the program is going to move the loop count in RCX register. Let's execute this line using the ni command. Now the program is going to load the address of var1 into the RSI register. Let's execute this line using the ni command. Like the same way, the program is going to load the address of var2 into the RDA register. Let's execute this line using the ni command. Now you can see the program is going to move our string bytes from the source string to destination string location using repeat instruction. Let's use ni command to execute this line so that it moves our first byte from the var1 to var2 memory location. You can see the first byte is moved in var2 and the value of RCX is decremented to 10. Let's use ni command until the whole string is moved to var2 memory location. You can see right now the RCX value is 0 and our string is moved to the var2 successfully. Let's use C command to continue our program. So this was a simple demonstration of how a repeat instruction is used to move the whole string at once. So that's all for now. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, I am going to show you how we can compare two string values if they are equal or not in assembly programming. Let's take a simple example to understand this concept. Suppose we have two strings in memory which we want to compare if their values are equal or not. To compare these two string values, first we set up the source and destination register pointers, RSI and RDI, which points to source and destination strings memory location. After this, we need to clear the direction flag. Now we need to specify the number of bytes in RCX register which we want to compare in our strings. Then we use repeat instruction with compare string instruction to compare all the bytes one by one from source to destination. Let's visualize the comparison in this example one by one. First, this A is compared with the destination A, which are equal here. In this case, both values are equal. So the 0 flag will be set, which means both the bytes are equal here. Now the first byte comparison is completed, so the RCX value is decremented by 1. Now let's compare the second byte, which is B here. In this case, both values are equal. So the 0 flag will be set here, which means these bytes are equal here. Now the second byte comparison is completed. So again the RCX value is decremented by 1. Now the program is going to compare the next byte, which is C here. In this case, both values are equal, so the 0 flag will be set here, which means both the bytes are equal here. Now you can see how we can use repeat and compare string instructions to compare two strings in our assembly program. Now the RCX value is 0, which means all the byte comparisons are completed. Now let's change the string values and then compare again. First, this A is compared with the destination A, which are equal here. In this case, both values are equal. So the 0 flag will be set here, which means both the bytes are equal here. Now the first byte comparison is completed, so the RCX value is decremented by 1. Now the second value D is compared with B. In this case, both values are not equal, so the 0 flag will not be set here, which means both bytes are not equal here. So in this case, the program will break the repeat comparison loop here due to this second byte comparison, which are not equal here, and exit out of this repeat loop. So you can see how the program has detected that this string is not equal by using this repeat compare string instruction. In this example, we have used bytes by bytes in string comparison instruction. We can use word here to compare two bytes at once. We can also use double word, quad word to compare 4 and 8 bytes at once respectively. So this is the way how we can use repeat and compare string instructions in our assembly program to compare the string values. Let's jump into our Kali Linux machine to do the same program in assembly. Let's first create our assembly source file and name it as compare_strings.asm. Let's first create our data section. In this data section, let's create our first variable string1 and store some character bytes. Let's create another variable string2 and store some character bytes. Let's create our text section. In this text section, let's specify our entry point using global keyword, and in this case our entry point will be underscore start label. Let's write our start label. First, let's clear the direction flag using CLD instruction. Now let's specify the loop count in RCX register. Now let's load the address of our source string into RSI register using LEA instruction. In the same way, let's load the address of our destination string into our RDI register using LEA instruction. Now let's use repeat instruction with the compare string instruction to compare string bytes of our source string 1 with destination string 2 here. Now let's write our exit system call to exit the program safely. Let's save the file. Now let's assemble our source file using YASM. Let's link our object file using LD command and generate our final binary file. Let's load our binary file in GDB. Our binary file is loaded in GDB. Let's disassemble our start label first to see the program disassembly. You can see this is our program disassembly. In this disassembly, first we are clearing the direction flag using CLD instruction. Then we are setting up the loop count in RCX register. Then we are loading the addresses of our source string 1 and destination string 2 addresses into our RSI and RDI registers. Then we have used repeat and compare string instructions here to compare string 1 value with string 2 value. In the last, we have our exit system call. Let's put a breakpoint on our start label first. Now let's run the program. You can see right now the program is paused at our start label. Now the program is going to clear the direction flag using CLD instruction. Let's execute this line using NI command in GDB. Now the program is going to move the loop count value into RCX register. Let's execute this line using NI command in GDB. Now the program is going to load the memory address of string 1 into RSI register. Let's execute this line using NI command in GDB. Now you can see the memory address of string 1 is loaded in RSI register here. Now the program is going to load the memory address of string 2 into RDI register. Let's execute this line using NI command in GDB. Now you can see the memory address of string 2 is loaded in RDI register here. Now the program is going to use a repeat and compare instruction to compare bytes from string 1 to string 2 one by one. Let's execute the first loop with NI command here, which will compare our first byte in string 1 with string 2. Now you can see in RSI and RDI register the first byte is compared and the 0 flag is set here, which means the values are equal. Let's execute the remaining loops which compares all the other string values. You can see all the comparison of bytes of string 1 with string 2 are completed now and the RCX value is 0 now. Let's use C to continue the program execution so that program exits normally. Now let's change the value in string 1 in our assembly program and see the program behavior. Let's save it. Let's assemble it and link it again. Let's load it in GDB. Let's put a breakpoint at our start label. Let's run the program. Right now the program is going to clear the direction flag using CLD instruction. Let's execute this line using ni command. Now the program is going to move 4 in RCX for the loop count. Let's execute this line using ni command. Now the program is going to load the memory address of string 1 into RSI register and string 2 into RDI register using LEA instruction. Let's execute these two lines using ni command. You can see the string 1 and string 2 addresses are loaded in RSI and RDI register. Now the program is going to start comparing bytes in these two strings using RSI and RDI register pointers. Let's execute this line to perform first byte comparison. Now you can see the first byte is compared and the result of comparison is equal because the 0 flag is set right now. Let's use ni command to execute the second byte comparison. Now you can see the second byte is compared and the result of this comparison is equal because the 0 flag is set right now. Let's use ni command to execute the third byte comparison. Now you can see the third byte is compared and the result of this comparison is not equal because the 0 flag is not set right now. So the comparison loop will be terminated now because this one byte is not equal here. Now let's use C to continue our program so that the program uses exit system call to exit normally. So this is how the strings are compared in assembly programming. I hope that by now you have a clear understanding of how we can compare strings in our assembly programming. So that's all for now. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. In this part, I'm going to show you how we can load and store values from our string in assembly programming using loads and stores instruction. This loads means load string and stores means store string. Till now we have moved our string bytes from one location to another location. While moving our strings from one location to another location, the string values are not changing. So what if we want to do something with our source string values in between the string movement and then move it to a destination location? So in this case, we need an assembly instruction loads from which we can first load the source string values somewhere temporarily so that we can perform some logical operations on that string value. Then we can store that changed value using stores assembly instruction to our destination memory location. Let me explain this load and store assembly instruction with a simple example here. Suppose we have a string in memory which we want to move to destination location. So first let's set up our source and destination string memory location pointers RSI and RDI. Then let's use load string byte assembly instruction to load a single byte from the source string using RSI pointer. In this case, this first byte is going to be stored in the RAX register by this load string byte instruction. Now after loading a single byte of our source string into RAX, we need to retrieve this byte from this RAX register using the store string byte instruction in assembly. So this stores B instruction will take this byte from the RAX register and store it to the destination location pointed by this RDI register. So this is how load and store assembly instruction works in assembly programming. We have loaded and stored a single byte in this example. We can use loop instruction with this load and store instruction to load all the bytes one by one in RAX register. Let me show you how we can use load and store to load all these string bytes one by one here. So first we need to clear the direction flag. Then we need to specify loop count in our RCX register. Then let's set up the source and destination string pointers in RSI and RDI registers. Now let's use load SB instruction to load all the bytes one by one in RAX register. After that, we need to retrieve those bytes using stores B instruction to store our byte in destination memory location using RDI register pointer. Now let's visualize how the bytes are going to be loaded in the RAX register one by one, then stored in the destination location. Right now, the first byte will be loaded into this RAX register using this load SB instruction here. After that, this stores B instruction will retrieve this byte from the RAX register and store it to the destination location. After loading and storing the first byte, the RCX value will be decremented by 1. Now the next byte will be loaded into RAX again using this load SB instruction, and further it will be retrieved by this stores B instruction and moved into the destination location. After loading and storing the second byte, the RCX value is decremented by 1. Now the last byte will be loaded in RX and then moved into the destination location. After loading the third byte, the RCX value is 0 now, which means the loop will be terminated here. So this is how the load and store string instruction works in assembly programming. Here in this example, we have loaded byte by byte from the source string. We can load 2 bytes at once using word here. We can load 4 bytes at once using double word here. We can also load 8 bytes at once using quad word here. So you can see how the string values are loaded and stored with the use of loads and stores instruction from source string memory location to destination string memory location in assembly programming. So that's all for now. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. So till then, goodbye. Hello everyone and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can use loads and stores assembly instructions in our assembly programming. So in previous part, I have demonstrated you the concept of how loads and stores assembly instruction works in our assembly program. So in this part, we will do the same thing but practically using an assembly program. So this is my Kali Linux terminal, and in this terminal let's write some code for our program. So let's create our source file. In this case, let's name it loads underscore stores.asm. So this will be our source file for assembly program. So first let's create our data section, and in this data section let's create a variable called string1. So this is our string1 variable, and let's define, let's put some data in this variable. So in this case, let's put some character bytes, in this case ABC. So this is string1, which will be our source string in this case, and let's define our BSS section. After that, in our BSS section, let's create our destination string variable. In this case, the destination string is string2, and let's reserve some bytes. So in this case, I want to reserve 3 bytes because we are going to move this ABC into this string2. Means we are going to move this string1 value into this string2, not value, but we are going to move the value of string1 variable, which is ABC, into this string2 variable. So after that, let's create our text section, and in this text section, let's first define our entry point using global keyword. So the entry point will be our start label, and after that let's write our start label. So in the first step, I already told you in my previous part, in the first step we need to clear the direction flag using CLD instruction. So let me comment it, clear the direction flag. After that, we need to set up the loop count in RCX register. So move, then RCX. So we want to move 3 bytes, means we want to perform 3 times loop. So for that we have to move 3 into RCX, because we will move ABC. ABC is 3 bytes. So we want to loop our we want to loop our load and stores instruction 3 times, so that we can move these 3 bytes in the destination string location. So that is why it is 3. After that, we need to load the so let's load the memory address of string 1 into our RSI register pointer using LEA instruction. So string 1. So string 1 memory address will be loaded in RSI register pointer through this LEA instruction, load effective address instruction. So let me comment it here. So loading string 1 address to RSI register. After that, in the same way, let's load our string 2 memory address into our RDI register. So loading string 2 memory address to RDI register. So we have set up the memory address pointers into RSI and RDI registers. After that, let's create a label for our loop. So loop underscore me. So this is our loop underscore, like this is our label to loop for loads and stores instruction. So first in this label we are going to load the bytes from our string 1 using loads. So loading bytes from string 1 into RAX register. So we are just loading bytes from string 1 into RAX register using loads, and after that we will use stores. Sorry, one mistake is there. Loads B means byte. We are loading bytes, and in stores we will use B. So stores B means we are going to store that byte from RAX into string 2 memory location. So storing bytes from RAX into string 2. Now after that we have to use loop, and we want to loop this loop underscore me label. We want to loop this loop me label. After loading first byte, it will loop, like it will jump here and it will execute again loads and stores to load the other bytes one by one until the RCX value will be 0. After that, let's use our exit system call to exit the program safely. So move, then RAX. So this is our exit system call number. After that, we need to specify the return status value in RDI register, which is 0 here. So return status value for exit. After that, we have to use syscall keyword in order to execute this exit system call. So let's write this file. Let's use yasm to assemble this file. So yasm -f, and we have to mention the format here, which is 64-bit. After that, we have to specify the after that we have to use -G option to include the debugging symbols. So -G, then dwarf2, then we have to specify our source file here, loads_stores.asm. Right now our object file is generated, which is loads_stores.o. Let's use this object file in order to generate our final binary file using ld command. So ld loads_stores.o, object file as an input, and in output let's give the same name, loads_stores. You can see our binary file is generated here, loads_stores. Let's load this file into our GDB. So loads_stores. Now the binary file is loaded in our GDB. Let's first disassemble our start label. You can see this is the disassembly of our start label. You can see it is showing only 4 lines here. Why? Because we have used another label here, loop me. So other parts is in our loop me label. So in order to see these disassembly, these line disassembly, we need to disassemble the loop me label here. So loop_me. You can see this is the loop me assembly instructions here. So this 4 line belongs to these codes. You can see first we have used CLD. You can see here first we have used CLD here, then we are just moving this 3 into RCX. You can see clearly here. After that we are just loading the memory addresses of string 1 and 2 in RSI in RDI, and you can see here it is same here. So in place of string 1, you can see this is the memory address of string 1, which is going to be loaded in RSI register. After that, this is the memory address of string 2, and this memory address will be loaded in RDI register. After that, we are just using loads and stores instruction in our loop me label. You can see this is loads, and in this case you can see this is byte pointer. Byte pointer means that we are dealing with, like, we are loading byte by byte. So this will load, like this will load a single byte from this RSI register, and it will move that byte and it will store that byte into AL register. So don't get confused with this AL, because this AL is the smallest unit of our RAX register. So basically this is our RAX register, but this is single byte unit, which is AL. So the first byte is going to move into this AL register, which is RAX register, and after moving this into RX register, into this AL register, then we are just storing that value from AL. You can see we are just getting the value of AL to RDI register, which is our byte pointer here. So through this RDI we are just sending the value of AL into our destination string location, which is string 2 here. So you can see we are just moving the byte from this RSI to AL, then from this AL to this RDI location, which is our destination memory location, which is string 2 here. After that we have our loop instruction, and this loop instruction will jump at this particular label, which is loop me, at this particular memory address, and it will loop it will perform loop operation till the RCX value will be 0. After performing all the loops, it will just exit it will exit from this program using this exit system call. You can see this is our exit system call in the last. So this is our program disassembly, and let's first put a breakpoint at our start label, and after that let's use display command, display, then let's use display with ws. W means word, S means string. So we want to display the values in word, and we can use GS also in this case, but I am using word here, so W and S, it's simple. So I want to display string 1 value here. This is string 1. You can see don't get confused with this particular error here. It is not an error because program is not running. That is why it is saying that cannot access memory at address 402003. So basically we are using display command to basically track the data movement here, to see the data which is moved from source to destination. So in this case, this is our source string, and I want to also display the destination string also. You can see this is our destination, which is empty here. After that, let's run our program. Right now you can see this is our display output. The program is paused at our start label here. You can see this is our start label, and it is paused at this particular location where it is going to clear the direction flag. You can see this is CLD, and you can see here this is our display output, and in this display output this is string 1, and this is the memory address of string 1, and this is the value of string 1, and this is the string 2, and this is the value of string 2. Right now it is empty, string 2 is empty. So basically let's execute all the instructions one by one, and let's make some analysis. Let's make some good analysis and try to understand the loads and stores instruction here, how the data is moving from source to destination using loads and stores instruction. So let's execute this line which will clear the direction flag CLD. Sorry. Now the first instruction is executed, and right now the program is going to execute our second line, which is move RCX 3. So we are just going to move this 3 into RCX for loop operations. So let's use next instruction. Sorry, and you can see RCX value is 3 right now because we have moved, like the program has moved 3 into RCX. That is why it is 3 here, RCX value. So loop count is set up, and right now we are going to, like, the program is going to load the source string memory address into RSI. So right now you can see this is our RSI register. This is our RSI register, which is 0 here. After executing this line, this memory address will be stored here, linked here in RSI register. So let's use next instruction, and right now you can see sorry, right now you can see this RSI register contains the memory address of our string 1 variable, and this string 1 variable has the value ABC here. So the first, not first, but the string 1 address is set up in our RSI register pointer. Now in the same way, the program is going to load the string 2 memory address into RDI register using LEA instruction. So let's execute it using NI. So you can see RDI is pointing at our string 2 memory location, which is 402004. So this is our string 2, and in RSI this is our string 1. So memory pointers are set up, and after that the program is going to enter into our loop me label. So the program is at this particular location right now. You can see the program is going to use loads instruction to load our first byte from our string 1. You can see this is going to load our first byte from string 1, and it will load that particular value from RSI register pointer into this AL register. So this loads will load the first byte from our string 1 using this RSI pointer register into AL register, which is our RX register. So let's use next instruction, and you can see before executing this loads, you can see this is our RAX register. After executing this line, what is going to happen? The first byte, which is A here, this A will be moved here. This A will be moved here in RAX register. And notice here also, pay attention on these two locations. First location is this string 2, and the second location is our RAX register. So let's execute it and let's see next instruction. And you can see the in RAX we have A, like the first value A is moved here. You can see this A is here. So RAX has A right now using loads instruction, means loads has loaded the value, the first byte, into RAX register. Right now you can see in string 2 we don't have A right now. Why? Because in order to get that A, in order to get that first byte from this RAX register, we need to use stores instruction, STOS. This stores will store that A into our destination memory location, which is string 2 here. So after executing this stores, what is going to happen? This AL value, you can see here, this AL value is going to move into this particular RDI location, RDI register pointer location, which is pointing at this string 2 right now. You can see this is our RDI, which is pointing our string 2. So the value of AL will be moved into this particular location, which is our string 2. So basically this stores will move this A into our string 2 register using stores instruction. So let's execute it using next instruction, and sorry, and right now you can see in string 2 we have our A. So that A, this A, which is stored in RAX, is moved into our string 2 memory location. So the first byte is moved. Right now the program is going to use this loop instruction to jump at this particular label. And before jumping, what is going to happen? This loop will decrement this RCX value by 1. So this 3 will be 2 after executing this loop. So let's use next instruction, and you can see the program has jumped from this loop, like it has jumped from this to this location again, which is load as B. Sorry. So right now you can see R6 value is decremented by 1, which is right now it is 2. It was 3 before, but after executing this loop instruction, it is 2. So one value, like 1 is decremented, one value is decremented, or you can say like 3, it was 3 and right now it is 2. R6 value is 2. So right now the program is going to load the next byte, the second byte, which is B here. You can see RSI is pointing at this B. So this B is moved from this RSI register pointer to AL register again, which is RX here. So this B will be moved into this RX register using this loads. So let's use next instruction, and right now you can see B is moved into RX. So right now we have moved the second byte into our RX register. After that we are going to retrieve this b from Rx into our string 2 memory location using store instruction, store string instruction, which is stores here. So the program is going to store that value from Rx, which is b here, into our string 2 memory location, which is pointed by this RDI register pointer. So let's use next instruction, and you can see here in string 2 this b is moved from this Rx register. So 2 bytes are moved successfully. Right now the program is going to jump at our loop me label again here to perform our next loop. So first it will decrement the value of RCX to 1, from 2 to 1, and then it will jump to this particular memory location, which is loads here. So let's use next instruction, and right now you can see RCX value is decremented by 1, and right now it is 1, and the program is going to use loads. Like the program is going to load the next byte, and the next byte is C here. You can see this is our RSI, and which has this C character byte. So right now it is going to load this C into this RAX register using loads instruction. You can see this is our RSI. So in RSI we have our C. So this C will be moved into AL register using loads. So let's use next instruction, and right now you can see C is moved from this RSI into this RAX register, and after that the program is going to retrieve that C from this RAX into our string 2 memory location using our RDI register pointer. You can see this is stores, and it is going to retrieve from this AL register, which is our RX register, into this particular memory location, which is pointed by this RDI register. So let's use next instruction, and you can see this value is moved into our string 2 variable. So all the 3 bytes are successfully moved. You can see ABC. Right now the program is going to execute this loop instruction. So right now what is going to happen? First, this loop instruction will decrement the value of RCX. You can see RCX is 1 right now. First it will decrement this RCX value, so it will be 0. So when it will be 0, then this loop will this loop will be terminated, because that RCX value will be 0. So 0 means there will be no loop by this loop instruction. So the loop will not going to jump at this particular loop me label again, because the RCX value will be 0 here. So it will jump to the next particular memory location, like next immediate instruction here. So let's use next instruction. You can see RCX value is decremented to 0. 0 means no loop. So it has jumped from this location directly to here. Not jumped, but it has sequentially executed the next line. Like not executed right now, but it has jumped to the next particular line, which is our exit system call, this particular area. So this is our exit system call. So right now it is going to exit our program safely using C command. We can continue. So exited normally, this program exited normally, and you can see how we have moved 3 bytes from source string location to our destination string location using our RSI and RDI pointers, register pointers, and we have used load and stores instruction here, means loads byte and store byte. So this is how loads and stores instruction works. This concept is very simple, very straightforward. Nothing is complex here. I think if you practice 1 to 2 times, you will get to know how this load and store instruction works. So if you have any questions regarding this, like if you are getting any kind of confusion in this program, let me know. I will surely help you. So till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. In this part, I will show you how we can encrypt any string in assembly programming. Suppose we have a source string in memory and we want to encrypt this string and store it to a destination location in memory. First, we need to clear the direction flag. Then we need to set up the loop count for this string in RCX register. Then we have to set up the source and destination memory locations to our RSI and RDI register pointers. Now let's load the first byte of this source string into RAX register using load SB instruction. Now the first byte is loaded in RAX. Let's encrypt our first byte, which is stored in this RAX register using XOR logical operation. Let's XOR this first byte with a key which is 5 here. Now the XORed value is stored in RAX. Let's retrieve this XORed encrypted value from RAX to our destination string memory location using stores B assembly instruction. Now the first byte of our source string is encrypted and stored in our destination string location. Now the RCX register value is decremented by 1. Now the second byte will be loaded into RAX register using load SB instruction. Now let's encrypt this second byte using our key value. Now the XORed value is stored in RAX. Let's retrieve this XORed encrypted value from RAX to our destination string memory location using stores B assembly instruction. Now the second byte of our source string is encrypted and stored in our destination string location. Now the RCX register value is decremented by 1. Now the third byte will be loaded into RAX register using load SB instruction. Now let's encrypt this third byte using our key value. Now the XORed encrypted value is stored in RAX register. Let's retrieve this XORed encrypted value from RAX to our destination string memory location using stores B assembly instruction. Now the last byte of our source string is encrypted and stored in our destination string location. Now the RCX register value is decremented to 0, which means the loop is complete now. So you can see how we have used loads and stores assembly instruction to encrypt our source string and store it to our destination string memory location. So this is how we can encrypt any string data to our assembly program. So if you have any confusion regarding this concept, let me know in the comment section. I will surely help you. We will do a practical demonstration of this concept in the next video. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can encrypt our string in assembly programming. So in previous part, we have covered all the conceptual part in which I have demonstrated you how the strings can be encrypted in our assembly program using loads and stores instruction. So we will do the same thing in this particular video, but practically. So let's first create our assembly source file in our Kali Linux terminal. So vim, and let's use a name called encrypt encrypt.asm, and first let's create our data section. sorry So in this data section, first let's create our source string, which is string1 variable here, and let's store some character bytes here, which is A, B and C. So we are going to encrypt this string 1 values, which is ABC here. After that, let's create our BSS section, and in this BSS section, let's create our destination string variable, which is string 2 here, and let's let's reserve some bytes. So in this case 3 bytes, because we are going to encrypt those 3 bytes from string 1, and we will encrypt that ABC byte from string 1 to this string 2. We will store the encrypted value in string 2. That is why we have taken 3 here. After that, let's create our text section, and in this text section, first let's specify the entry point using global keyword. So in this case, the entry point will be on our start label. After that, let's write our start label. So in the first step, I already told you, in the first step we have to clear the direction flag using CLD instruction. So CLD, so let me comment here, clear the direction flag. Now in the second step, we have to specify the loop count here. So the loop count will be 3 here, because we are going to encrypt 3 bytes in our string 1. You can see here we are going to encrypt these 3 bytes. So the loop count will be 3 here. So we have to specify the loop count in our RCX register. So RCX, then 3. Let's move forward that. Okay, so let me comment here, loop count. So we have specified the loop count in our RCX register. After that, we need to set up the source and destination. We have to set up the source and destination string pointers in RSI and RDI registers. So for that, we are going to use LEA, load effective address instruction. So first we are loading the effective address of string 1 into RSI register pointer. So RSI, and we are going to load the memory address of string 1 here into RSI register pointer. So let me comment here, loading the address of string 1 in RSI. Let me adjust the window little bit. Okay, so loading the address of string 1 in RSI register pointer. Now the first pointer is set. We have to set up the like the source pointer is set in RSI, and we have to set up the destination string pointer, which is string 2 here, into RDI register. So RDI, then string 2. Sorry. Loading the address of string sorry, string 2 in RDI. Now string memory pointers are set up in RSI and RDI, source and destination string pointers. After that, we have to use loop, like we have to create a loop here. So for that, first we need to create label here. So loop underscore me. So this will be our loop label. And after that, first we have to load the first byte from our source string, which is string 1 here, this. So we have to store all the bytes one by one 3 times. So to load the bytes in RX register, like we are going to load these bytes one by one in RAX register in order to encrypt. So for that, we have to use loads B instruction here, which will load each byte one by one from string 1, from source string 1. So it will load the first byte. So after loading first byte, let me comment here, load each byte one by one in RX register. So we will load each byte one by one in RX register using load SB instruction here. After loading the first byte, like not first but each byte, we are going to perform, like we are going to do XOR with that particular byte which we are getting from string 1 in RX. So XOR, and we are going to do the XOR with this value, like not value but key. In this case the key is 5 here, so we are just performing XOR operation, logical operation in between RX and 0x5. So in RX we have our first byte stored here using load SB, and that value will be XOR'd with this 0x5 here. So basically we are just encrypting here. So XORing RX value with 0x5. So now the output here, the output, like the XOR'd value will be stored in RX register. Keep in mind, after XORing, like after performing the XOR operation, the result will be stored in RX. So the first byte will be XOR'd and the result will be stored in RX. And this is the key, remember, 0x5. So this, like the value of RX will be XOR'd with 5 and the result will be stored in RX. It's very simple. Now after XORing, like after encrypting, we are just encrypting here. So after encrypting and storing the value in RX, after this we need to store that value, that encrypted value, into our destination string location, which is string 2 here. So we are going to store that encrypted value into string 2. And how we can do that? We can do that by using stosb, stosb. So we are going to store that encrypted value, that first byte value, into our destination location using RDI register. It's very simple. And let me comment here, storing the encrypted byte, in string 2, in string 2. Very simple. And after that we are going to use loop instruction in order to loop the other bytes, other remaining bytes, which is 3 here. So loop, we want to loop, like we want to jump at this particular location again to perform all the remaining byte encryption. So loop space loop me. Sorry. After that let's write our exit system call to exit the program normally. For that, first we need to move the system call number, which is 60 here. We need to move the system call number in RX register, which is 60 here. So this 60 is syscall number for exit. After that we need to move the return status value into RDI register. So return status value for exit syscall. After that we have to use our syscall keyword in order to execute this exit system call. Sorry. Let's save this file. Let's assemble our file using YASM. Let's specify the format here, so ELF 64-bit, and let's use -G option to include the debugging symbols for our program. So -G, then dwarf2. then we have to specify our source file here, which is encrypt.asm. Now our object file is generated here. You can see encrypt.o. Let's use this object file in order to generate our final binary file using ld command. So ld, so as an input we have to specify the object file here, which is encrypt.o, and in output we have to specify a name here. So let's use a name called encrypt. Right now you can see that our binary file is generated, and let's load this binary file in our GDB. So gdb-q, then encrypt. So our binary file is loaded in our GDB. Let's first disassemble our start. You can see this is our start start label code. You can see this is our first line, which is CLD instruction here. Then we are just moving 3 into RCX, which is our loop count. Then we are just loading the string 1 and string 2, it means source string and destination string variable memory addresses into RSI and RDI. Very simple. So this is our start label code, assembly code, and after that we have our loop me label assembly code. In this loop me we have our loads and stores, then we have our exit. So let's let me show you the disassembly of this loop me also. So disassemble loop me, and you can see this is the disassembled code of our loop me label here. So you can see clearly in this loop me the first instruction is loads b, means we are just loading bytes from our source string, which is this one by one. So loads, and we are just loading the bytes from our source string pointer, which is RSI here. You can see byte pointer means single byte. We are loading single bytes from our source string pointer, which is RSI in this case, because we have loaded the source string memory address into RSI. That is why this RSI is used. So it will load the bytes from RSI source string pointer to AL register. AL register means RAX register, and then we are encrypting, or you can say we are XORing that particular value from RAX. Like we are XORing this value which we have loaded in our RAX register with this 5. You can see XOR RAX and 5. So in this line we are just XORing, like we are just encrypting our data from source string 1. So we are encrypting the first byte here in XOR and storing that byte in RAX. You can see this line. So this line disassembly is this. After that we are just storing that encrypted value from RAX register. You can see this is our RAX register. So this is AL, means this is the smallest unit of our RAX register. So this is our AL register, which is the smallest unit of RAX. Don't get confused here. This is RAX. So we are just loading the encrypted value from this AL to our destination location using this RDI register pointer, which is pointing our destination string memory location. So we are just storing our encrypted byte into our destination location using stores B instruction. You can see here this stores B. After that we are using loop to perform loop operation, to perform loop until all the bytes of our source string gets encrypted and stored in our destination location. So it will loop like 3 times to encrypt all the bytes one by one, and it will store the the bytes into destination location, destination string location using this RDI. After that, we have our exit system call here in the last this part. So this is very simple example, simple program. So let me first put a breakpoint at our start label, and then let's not run, but let's use display command to display our string values, so that we can see how the bytes are encrypted from source to destination. So string 1, this is a mistake. I have to use address of operator here. So this is string 1 and string 2. So let's run our program, and you can see the program has paused at this particular location, which is our start label here, at this particular location, which is this CLD. So program is paused at this particular location, and right now you can see, so we have 3 display. Okay, so first display has an error, so we have to remove first display. Let me remove this using delete command. So delete display 1. I want to delete this display 1. So let's execute this first line, which is CLD. It means we are just clearing the direction flag here in the first line, in the first instruction. So you can see, let me show you here important parts. So this is string 1. You can see this is our string 1, and this is the output of our display command, which I have used in previous commands. So this is string 1, and this is the memory address of string 1, and in this string 1 ABC is stored. 3 bytes are stored. And this is string 2. In string 2, we don't have anything here. This is empty. So we will encrypt these 3 bytes one by one, and we will store those bytes, those encrypted bytes, into this string 2. So let's use ni next instruction to execute this first line, which is CLD. We are just clearing the direction flag, and this is the first step, remember, in my previous video. So hit enter, and the first line is executed, the CLD is executed. Right now the program is going to move the loop count into RCX register. So this 3 will be moved into RCX register. Right now you can see RCX is 0. So when we execute this line, the RCX value will be 3 here. This RCX value will be 3. So let's use next instruction, and right now you can see RCX value is 3. After that, we are going to execute this line, and in this line you can see we are going to load the source string memory address into RSI register pointer. We are just setting up the source and destination string pointers, string memory pointers, into RSI and RDI. So let's use next instruction, and right now you can see this is our RSI. In RSI right now it is 0. So when we execute this part, this line, this will load the effective address of string 1, means source string 1 address, into RSI register pointer. So hit enter and you can see RSI register pointer is pointing at this particular memory location, which is the location of our string 1 memory address, which is ABC here. So this is the hexadecimal representation of this ABC, right? After that, we are going to set up the destination string pointer, the destination memory string pointer, into RDI register pointer, like the same way which we have done here. So let's use next instruction, and right now RDI is pointing at this particular memory address, which is our destination string which is string 2 here. This is our destination location. So this 2004 is the address of our string 2. So source and destination pointers are set up. After that, we are going to start our data movement using loads. So we are going to perform, like we are going to load our first byte using load instruction. So loads, and we are going to load the first byte from this RSI register pointer. So we will load, like we are going to load the first byte which is pointed by this RSI register. So the first byte is this A. Right now the RSI is pointing this A, the first byte of our source string. So we are going to load this A into RAX register, you can see byte pointer. So this value which is pointed by RSI will be loaded into AL register, which is RAX here. So let's use next instruction, and right now you can see RX value is loaded with A. The first byte is loaded into RX register and right now the program is going to perform XOR operation between RAX and 5. So RX is A, which is 0x4, this is the hex value. So this RX will be XORed with 5. This RX value is XORed with 5, and the result will be, like after performing this XOR operation, logical operation, the result will be stored in RX register. So let's execute next instruction, and you can see after XORing, this is the result. So this is the encrypted value. So the first byte is encrypted, and this is the result of first byte encryption, which is D here, So the first byte is encrypted and stored in RAX. Now after that, we are going to store that encrypted byte, that encrypted first byte from this RX register into our destination location, which is pointed by this RDA register. Right now you can see this is our RDA and it is pointing at this particular memory address, which is the memory address of our string 2. So we are going to store that encrypted value from RX to this RDI register pointer location, which is pointing at string 2. So let's execute it and focus here, focus on this part. So this first byte will be encrypted and stored here after this. So this encrypted RX value will be stored at this particular memory location. You can see 2004, you can see here RDI is pointing at 2004, which is this string 2 memory location. So let's execute this line, and you can see that RX value, that encrypted value from RX is moved into our string 2 memory location. So the first byte is encrypted. Right now the program is going to execute this line, which is loop. So what is going to happen? This loop will be executed and it will first decrease this value. It will first decrease the RCX value by 1. So this 3 will be 2 after executing this loop, and then it will jump at this particular memory location, which is the loop me label here. So let's use ni, and right now you can see RCX value is 2. It was 3 before. So now the now the next byte is going to be loaded. You can see the program is going to use loads instruction to load the next byte, which is pointed by this RSI register pointer. Right now you can see RSI register pointer is pointing at this particular memory location, which is pointing at B, the second byte of our source string. You can see this is our source string and it is pointing B right now. You can see this B. So this memory address is pointing at B, and this B will be loaded in our RAX register. Right now RAX register is D, like RAX register has D. So after executing this load, what is going to happen? This RAX value will be changed from D to B here, because this B will be moved in this RAX value using loads. You can see clearly here, this is going to move from this RSI register pointer, which is pointing at B, into this AL register, which is RAX. So let's execute next instruction, and right now you can see RAX register has B. So we have loaded the second byte from our source string into this RAX register, and right now we are going to perform XOR operation to, like, we are performing the XOR operation between RAX value and 5. So this B, this RAX value will be XORed with 0x5 and the result will be stored in RAX register. So let's execute this using NI, and after XORing, the result is stored in our RAX register. This is the encrypted value of our second byte. This is the encrypted value of our second byte, which is stored in our RAX register. Now let's store this encrypted value, this second byte encrypted value, into our destination location, into our destination string 2 location, using stores B instruction. You can see right now the program is going to perform, like the program is going to execute this stores B instruction. So stores B, like stores, and then it is moving the value of RAX into RDI pointer location. Right now RDI is pointing at this particular memory location, which is the location of string 2. So let's store this G into our string 2 memory location using stores B instruction. So let's use next instruction and right now you can see this G is moved here. You can see this is string 2 and our second encrypted byte is moved into string 2 memory location. So we have successfully encrypted 2 bytes, and right now the program is going to execute this loop instruction, and after executing this loop, the first part, like the first step, is to decrement the value of RCX here. After decrementing this value, it will jump at this particular memory location and perform its next loop. So let's execute using next instruction, and right now RCX value is 1. So 1 is decremented from that 2. So RCX is decremented, and right now we are going to load the next value from our source string pointer. So you can see this RSI is pointing at the third byte. This RSI is pointing at our third byte from sources, like from our source string, which is C here. So we are going to load this C into our RAX register. Right now RAX has G. So after using this load instruction, this C will be moved into this RAX register. So let's use next instruction. Right now you can see C is moved in RAX register, and right now after moving in after moving in RAX register, this C, let's encrypt it. Let's perform encryption on this C using XOR operation here. So the program is going to perform XOR operation here with this C, which is stored in our RX register, and we are performing the XOR between RX and 05. So let's XOR it to encrypt our third byte of our source string. So next instruction. Now you can see the encrypted byte is stored in RX register, which is F here. So the third byte is encrypted, and the result of that encryption is F, which is stored in our RX register. So after this, let's use stores. The program is going to use a stores instruction to store this encrypted value from RAX to RDI pointer location. The RDI is pointing at this particular memory location, which is the memory location of our string 2. So this F will be stored from this RX to this string 2 memory location using RDI pointer. So let's execute it. You can see clearly this is stores, and we are just loading the RX value. You can see EL. We are loading RX value from this location to this pointer location, byte pointer location, which is pointed by this RDI, which is the location of our destination string. So let's use next instruction, and right now you can see the third byte is loaded, like not loaded but moved successfully here. So this ABC, these 3 bytes are encrypted and stored in our destination string location, which is string 2 here. So we have successfully encrypted all the bytes one by one using loads and store loads and stores assembly instructions, and we have used XOR logical operation in between these 2 instructions to encrypt these 3 bytes one by one. After that, you can see the program is going to perform this loop instruction operation, assembly operation. So what is going to happen? First, this loop will be executed, and when it executes this loop, the first thing it is going to do is it will decrement this RCX value. So when it will decrement, like when it decrements this value, it will be 0. Right now you can see it is 1. When this loop is executed, this will be 0. So when this loop sees this is 0, RCX is 0, then it is not going to jump here. First it will decrease this value, it will be 0, then it will see the value. In that situation it will be 0, and in that condition the loop is not going to work, like this loop is not going to jump at this particular memory location, loop me. So it will exit from this loop, and it will continue to execute our exit system call from here. So let's use next instruction. Right now you can see RCX value is 0. So 0 means no loop. So right now it is jumped at our, not jumped, but it has executed, like it is going to execute our next instruction, which is our exit system call. So these 3 lines are our exit system call. So let's use C to continue our program. So right now it is like the program exited normally. So sorry, and this was a very simple basic example of how we can encrypt our string values in our assembly programming. This is very basic concept, so try to practice it, and if you are facing any kind of confusion regarding this concept, let me know in the comment section. I will surely help you. So till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. In this part, I will show you how we can decrypt any encrypted string in assembly programming. So let's see how we can decrypt any encrypted string in assembly. Please remember that in order to decrypt the encrypted data, we need to have the same key which was used for encryption. In this case, we have used 5 as a key to encrypt this data. So we will use 5 here as a key to decrypt this data. So we have an encrypted source string in memory and we want to decrypt this encrypted string and store it to a destination location in memory. So first we need to clear the direction flag. Then we need to set up the loop count for this string in RCX register. Then we have to set up the source and destination memory locations to our RSI and IDA register pointers. Now let's load the first byte of this source string into RAX register using load SB assembly instruction. Now the first byte is loaded in RAX. Let's decrypt our first encrypted byte, which is stored in this RAX register using XOR logical operation. Let's XOR this first byte with a key which is 5 here. Now the XORed value is stored in RAX. Let's retrieve this XOR decrypted value from RAX to our destination string memory location using stores B assembly instruction. Now the first byte of our source string is decrypted and stored in our destination string location. Now the RCX register value is decremented by 1. Now the second byte will be loaded into RAX register using load SB instruction. Now let's decrypt this second byte using our key value. Now the XORed value is stored in RAX. Let's retrieve this XOR decrypted value from the RAX to our destination string memory location using stores B assembly instruction. Now the second byte of our source string is decrypted and stored in our destination string location. Now the RCX register value is decremented by 1. Now the third byte will be loaded into RAX register using load SB instruction. Now let's decrypt this third byte using our key value. Now the XORed decrypted value is stored in RAX register. Let's retrieve this XOR decrypted value from RAX to our destination string memory location using stores B assembly instruction. Now the last byte of our source string is decrypted and stored in our destination string location. Now the RCX register value is decremented to 0 now, which means the loop is complete now. So you can see how we have used loads and stores with our XOR assembly instruction to decrypt our source encrypted string and stored it to our destination string memory location. So this is how we can decrypt any encrypted string data with a correct key in our assembly program. So if you have any confusion regarding this concept, let me know in the comment section. I will surely help you. We will do a practical demonstration of this concept in the next video. So hello everyone and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can decrypt any encrypted string in our assembly programming. So let's first create our assembly source file in order to do this practical. So vim space and let's name our file as decrypt.asm. So first let's create our data section, and in this data section let's create our let's define our string 1 variable, means source string variable, which is string 1 here, and let's store the encrypted value here. So the encrypted value is D, G and F. So this is the encrypted value and we have to decrypt this string 1 value using assembly programming using a key. So in this case we already know the key. In this case the key will be 5, number 5 here. So we will decrypt this encrypted value dgf with 5, like with 5 as a key to get the actual data. So this is our encrypted string, string 1. This is our source string, which is encrypted. After that, let's create our BSS section. In this BSS section, let's define our destination string variable, which is string 2 here. So let's reserve some bytes. So in this case we need 3 bytes, because we are going to decrypt our source string data, and we will store that decrypted value into string 2 here. So this is string 2, which has 3 bytes of space here. After that, let's create our text section, and in this text section let's define our entry point using global keyword here, and the entry point is start label. And after that, let's write our start label here. Now in the first step, I already told you in my previous part, the first step is to clear the direction flag, which is CLD here. So clear the direction flag. After that, we need to mention the loop count here. In this case, we need 3 bytes, like we need to loop 3 times here. You can see dgf3. So we have to mention the loop count in RCX register. Let me move here. So RCX, and we have to move 3 into RCX to specify the loop count. So loop count. So loop count will be 3 here. After that, let's load the memory address of our source string 1 into RSI register pointer. So LEA, then RSI, then we have to mention the source string memory address here. So this string 1 memory address will be loaded into RSI register pointer. So we have set up the source string memory pointer in RSI register here using LEA instruction. So let me comment it here. So setting up source string memory let me comment short. Set up the source pointer in RSI. So we are setting up the source pointer in RSI, source string pointer in RSI. After that, let's load the destination string memory address into RDI register using LEA instruction. So as LEA space RDI, then string 2. So we are just storing the memory addresses of our string 1 and string 2 variables into RSI and RDI register pointers, so that they will point at these memory addresses, string 1 and string 2, so that we can move the data. So set up the destination pointer in RDI. Now after that, we need to create a label loop me, and in this loop me, first let's load each byte from these pointers. from these register pointers using RSI and RDI. So we will load all the bytes from this source string pointer RSI and destination string point RDI using load instruction. So loads B means load byte, load string byte. So we are loading byte by byte, one by one, using this loop me label. So load SB means it will load single byte from our source string using RSI register pointer. So loading loading a single byte from RSI to where, to RX register. Okay, after that we need to perform, now we have loaded the value in RX register from the source string. Now what we have to do, we have to decrypt that particular single byte from XOR operation. So XOR, and we need to perform XOR between RX, because our first byte is stored in RX with 0x5 value. So this 5 is our key here, which we have used to encrypt that particular data of string 1. So 0x5. So we will perform XOR between RX and 0x5 here, between the key. So decrypt the decrypt each byte, not each byte, but decrypt the value in RX. So we are decrypting here, and the result will be stored in RX register. So after that we want to load that decrypted value from this RX register into our destination location using RDI pointer. So stores B, then finish. Stores B means it will load the RX value into string 2. Okay, so it will load the RX decrypted value into our destination string 2 location, which is this destination string, is this string, which is string 2 here. So after that we need to perform, like we need to use loop instruction here to loop until all the bytes are decrypted here using loads and stores B instruction. So loop, and I want to loop this loop underscore me label. So it will loop again and goes for the second byte decryption. Then it will perform the loop until the RCX value will be 0 here. So this is loop. Now after that, let's exit our program after completion of the loop. So for exit, let's first specify the system call number here, which is 60 for exit. So syscall number for exit. After that we need to move the return status value into RDI register. So return status value for exit. After that we have to use our syscall keyword in order to execute this exit system call. Now our program is completed. Sorry, our program is completed and we have saved it. Let's open another Kali Linux terminal here, and in this terminal let's first assemble this file using yasm. So yasm space then -f means we need to mention the file format here, which is 64-bit here, so ELF64. After that we have to use -g to include the debugging symbols in our program. So -g space then dwarf2, then space, then we have to mention our source file, which is decrypt.asm here. So our object file is generated here. You can see decrypt.o. This is our object file. Let's use this object file to generate our final binary file. So ld space then decrypt.o, then in output we will name it decrypt only, and you can see our decrypt file is ready to be loaded in GDB. So let's load our file in GDB. So gdb-q then decrypt. Now file is loaded. Let's first disassemble our start label. This is our start label. Nothing is changed from nothing is changed here. You can see from our source only the string 1 and string 2 variables are replaced by memory locations. So let me explain you. This is the first line. You can see, let me adjust this window little bit so that we can view the text clearly. Okay, so you can see this is our first line, which is CLD, in which we are clearing the direction flag in the first line. Now in the second line, you can see we are moving the loop count into our RCX register. You can see here, this is our second line. After that, we are loading the source string memory address. This is the source string memory address, and our source string is this string 1. You can see here, this is string 1. So this is our source string, and this is the memory address of this this source string 1. And this memory address is loaded in this RSI register pointer. After that, like the same way, we are just loading our string 2 memory address into our RDI register. After that, after these two lines, we have our loop me label here. So let me first disassemble this loop me to see the disassembly of this loop me label. So you can see this is the disassembly of loop me label, and you can see in this disassembly we are first using load SB instruction to load a single byte from the RSI register pointer, which is pointing to the source string memory address. So you can see here loads. Program has used loads here. So it is loading the value, the first byte from this RSI register pointer into this AL register. AL means REX register. So it is loading the first byte, means each byte one by one, into REX register using loads instruction. Now after that, after loading into this AL register, like after loading the encrypted value of our source string into AL register, we are performing XOR between that loaded value, means that loaded value from RAX, with this key value, which is 0x5. So we are just decrypting our source string byte with this XOR instruction. So XOR, and we are XORing between RAX and 0x5. So through this line we are decrypting our bytes one by one. So the decrypted value will be stored in our RAX register. You can see clearly here, this is XOR. So we are decrypting our bytes using XOR operation with the key 5 here. So after decrypting, the value is stored in our RX register. Then what we have to do, we have to load this value from RX using stores instruction. You can see this is stores. So this stores will load the decrypted value which is stored in RX into our RDI register pointer, which is pointing at string 2 memory location. So indirectly we can say that this stores will store the decrypted value from RX into our string 2 variable location. You can see this is our RX, which is AL, and this value will be stored in our destination memory location, which is pointed by this RDI, which is string 2. Now after that the program is using this loop instruction to perform loop operation, like to jump here and perform all the remaining bytes encryption, like all the remaining bytes decryption. You can see loop, then it will jump at this particular location, which is the address of loop me, this address, and it will loop until all the bytes will be decrypted. Now after that we have our exit system call. You can see clearly here, this is our exit system call. So this is just a dry run to show you how this disassembly looks like. So this is just a very basic explanation. Now after that, let's put a breakpoint at our start and let's use a display command to display the string values, to display the string 1 and string 2 values here, so that we can see how the data is decrypted from source to destination string. So not this, but address of string 1. You can see this is the encrypted value, which is DGF here. This is our string 1, and this is the memory address of string 1, and this is the value, which is the encrypted value DGF. Like the same way we need to display the destination string 2 value here, which is empty right now. So all the decrypted value will be stored here. So let's run our program using run command, and right now you can see the program is paused at our start label here, which is showing here, and the program is going to clear the direction flag using CLD instruction. So this is the first line, and this is the first line. You can see CLD. This is program is at this particular location. So let's execute this line using ni command. Now after that, in the second step, we have to mention the loop count in RCX register here. You can see move this 3 into RCX. So we are just mentioning the loop count in RCX register. So you can see right now RCX value is 0 here. After executing this move instruction, what is going to happen? This 3 will be stored in our RCX register here. So let's execute it. Next instruction. Right now you can see RCX value is 3. After that, we are going to set up the source and destination string pointers, string memory location pointers using LEA instruction. So this is LEA, and you can see in this line the program is going to load the memory address of our source string. So this is the source string 1 memory address. You can cross check it. You can see this is 0x402000, and you can see this is our string 1. This is the memory address of our string 1. You can see this is 402000, which is exactly the same. So this memory address will be moved, not moved, but loaded in RSI register pointer. Right now you can see RSI register pointer is 0. So after executing this line, what is going to happen? This memory address will be loaded in RSI register pointer. So let's execute it, and right now you can see RSI register pointer is loaded with this particular source string 1 memory address. This is string 1 memory address, and which is pointing at DGF here, means which is pointing at the first encrypted byte here, which is D here. So this is the hex value of DGF actually, and this is the clear text. So the source string pointer is set up. Now we have to set up the destination string 2 memory address into our RDI register pointer. You can see in this particular line the program is going to load our destination string 2 memory address into RDI register pointer. So let's use next instruction, and you can see right now RDI is holding the memory address of our string 2. You can see this is string 2 and this is the memory address of our string 2, which is 2004. You can see 2004. So source and destination memory addresses are loaded in our RSI and RDI register pointers. Now in the next step, we are going to load the bytes from our source string memory addresses into our RAX register. So in this particular line, what is going to happen, the program is going to load the first byte from this RSI register pointer into RAX register, which is AL here. AL is the smallest unit of RAX register. So the program is going to load the first byte from RSI register pointer to AL register, and right now you can see RSI is pointing at this particular D byte, like the RSI register pointer is pointing at the first byte of our source string 1. So this is D, it is pointing at D right now. So this D will be loaded in RAX register after executing this line. So let's use next instruction, and right now you can see this D is moved and loaded in RAX register. Right now you can see RAX is D here. Now after loading that value, that first byte in RAX, we are going to decrypt our RAX value with this key, which is 5 here. So this D will be XORed with RAX, not RAX, but this D, or you can say this RAX value is XORed with this 0x5. So it will be decrypted by this way, by this XOR operation. So the decrypted value will be stored in RAX register here. So let's decrypt it using next instruction. So the first byte will be decrypted and it will be stored in RAX right now. So next instruction, and right now you can see the first byte is decrypted, and you can see this is A right now. So A is decrypted value is stored in our RAX register. The first value is decrypted and it is stored in our RAX register. So now what we need to do, we need to store this value into our destination string 2 memory location using stores B assembly instruction. So right now the program is going to store that RAX value, that decrypted value, into our destination, means destination string 2 memory location using this RDI pointer. You can see this is loading RAX value from here to, not loading but moving, storing, not moving, storing. This is storing this RX value to this RDI register pointer location, which is pointing at this string 2 memory location right now. So let's use next instruction and focus on this part here. You can see this is our source string here, this is our source string, and this is our destination string 2. So after executing this stores, what is going to happen, this first byte will be decremented decrypted and stored in our string 2 memory location and the decrypted value is this A, which is stored in RX right now, and this A is loaded from this AL register, which is RX, into this particular memory location, which is string 2. So this is very simple. Let's execute it. You can see that RX value, that A value is loaded in this string 2, like not loaded but stored in this string 2 memory location. So the first byte is decrypted and loaded, not loaded but stored in our string 2 memory location. So right now the program is going to execute this loop instruction. So what is going to happen, first this loop will decrement the RCX value here. So it will decrement this value by 1. So this 3 will be 2 after executing this loop instruction. So after decrementing this RCX value, the program is going to jump at this loop me label again to perform the next loop. So let's use next instruction, and right now you can see this RCX value is 2, and right now the program has jumped at our loop me label again to load our second byte from our source string memory location using this RSI register pointer. So the program is going to load our second byte from this RSI register pointer into our AL register. So AL register is our RX register right now, you can see. So this G, this second byte, this G will be loaded in RX register using this loads B instruction here. So from RSI register pointer to RX, it's very simple. So let's use next instruction, and right now that G is loaded in our RX register, and right now we are going to perform XOR operation between 5 and the value of our RX, which is G right now. So this G will be XORed with this 5, and by using this XOR operation we are decrypting the second value of our source string. So let's decrypt it using next instruction, and right now the value is decrypted, and you can see we have got our second byte which is decrypted here, which is B here. You can see the second byte is decrypted and it is B. Now it is stored in our RX register. So what is going to happen? The program is going to store that B from RX into our destination memory location, which is string 2 here, using this RDI register pointer, which is pointing at our string 2, means destination string memory location. So this B will be stored at our destination memory location using stores B instruction. You can see clearly it is loading from this RX register to this RDA register pointer. So let's use next instruction, and right now you can see that the second byte, you can see A and B, this second B, you can see clearly B, second byte is decrypted successfully. Now the program is going to execute this loop instruction, which will first decrement the RCX value. It will first decrement this RCX value, then it will jump at this particular memory address, which is the address of our loop me label here. Let's execute it using next instruction, and you can see RCX value is decremented by 1. It was 2 before, right now it is 1, and right now the program has jumped at loop me label here, and right now the program is going to load the last byte from our source string 1. This is our string 1, and the last byte is F. You can see clearly here, this is F. So the last byte is going to be loaded in our RX register using loads B instruction here. So it will load from this particular RSI register pointer to this AL register. AL means this RX register. Right now RX has B. After executing this loads, you will see this F will be loaded in our RX register. So let's use next instruction, and you can see F is loaded in our RX register. Right now the program is going to perform XOR operation to decrypt this value with our key. So this F, now the value of RX will be XORed with this 5, and the result will be stored in our RX register. So let's XOR it and see the decrypted value, and you can see the third byte is decrypted right now, and it is stored in our RX register, which is C. Now we have got the third decrypted value in our RX register. Right now the program is going to store this decrypted value from this RX to our destination memory location, which is string 2 here, using this RDA register pointer, which is pointing at string 2 right now. So this stores B instruction will, like this stores B instruction is going to load the value of RAX into our RDA register pointer location, which is pointing at string 2 right now. So focus on this part, focus on this part and this part, because this C is going to move here in this destination string 2 memory location using stores B instruction. So let's use next instruction, and right now you can see this C is stored at this particular memory location in string 2. So you can see this DGF, this encrypted value is decrypted in our string 2 memory location. After that, you can see right now the program is at this particular location, and in this particular line you can see the program is going to execute this loop. So what is going to happen here, the program will first decrease, decrement the value of RCX by 1. So after decrementing the value of RCX, it will be 0. It will be 0. That will mean that means that it is not going to jump at this loop me label here, because the value will be 0 here. So there will be no loop, and the program will jump at this particular line to execute our exit system call. So let's use next instruction, and you can see R6 value is 0, and the program is going to execute our exit system call. You can see clearly this is our exit system call. Move this 60 into RX, then move return status value into RDA, then syscall. So let's use C to continue our program. You can see the program exited normally. So this is how we can decrypt any encrypted string in our assembly programming using correct key. So if you are facing any kind of trouble in this particular concept or in this particular program, let me know in the comment section. I will surely help you. So I will see you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. In this part, I'm going to explain to you what a shellcode is. Basically, shellcode is a piece of machine code which has a specific purpose, like it can print hello world, it can spawn a local shell, it can create a new account on the system, etc. This shellcode doesn't need any assembling or linking to execute. This shellcode is used in other programs to execute. Now this shellcode is used by exploit programs generally to get the system shell. In this module, we will learn how to create this shellcode and how to test it. We will use this small C program to test our shellcode in this whole module. Let me explain this program briefly. This line declares an array named code of type unsigned character and initializes it with our shellcode. This line prints the shellcode length in bytes. This line declares a function pointer named return that points to a function taking no arguments and returning an integer. It then assigns return to point to the memory address where the code array is located, casting code to a function pointer type. This line calls the function pointed by return, effectively executing the shellcode stored in the code array. When this program is executed, it treats the shellcode as executable code and jumps to its location in memory and executing it. In this program, we just need to paste our shellcode in this variable to test it. In this module, we will learn how to create good shellcodes which can be used for security testing of the systems. So that's all for now. If you have any confusion regarding this topic, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. So in this part I'm going to show you the lab machine which we are going to use in this whole shell coding tutorials. So basically I am using this Ubuntu machine in this whole shell coding tutorial. So let me show you the version of this Ubuntu machine. lsb then release -a. So this is the version which I'm using in this shell coding tutorial, particularly in this module, in this whole module of shell coding. So this is the version of this Ubuntu machine, which is 18.04, and you should also install this Ubuntu machine, this particular version, to follow with me or to follow along with me. I have included the virtual machine disk file in the resources section. You can download, and like if you don't want to install this machine by yourself, you can import that virtual machine from the resources section and install it into your virtual box so that you can follow along with me. So that's all for now. This video was just about how, like which operating system I'm going to use for this shell coding tutorial. So I will meet you in the next part. Till then, goodbye. Hello everyone and welcome to the next part of this tutorial. So in this part we are going to create our first shell code. So before creating our shell code, I want to show you the shell code creation steps in this part. What are the steps in which we are going to create any shell code? So these are the basic steps which we need to follow in order to create any shell code. So let's begin. Now in the first step of shell code creation, first we need to write assembly program for our shell code. So this is the first step. In this first step we need to write assembly program for our shell code. So in this case, as an example, I have written exit shell code here. This is our exit shell code. You can see this is our text section, this is our start label, like this is our entry point, and this is our start label. And in this start label you can see we are just moving the system call number into this RX, which is exit system call number here, and after that we are moving the return status value into RDI, and then we have our syscall. So this is our exit system call. So this is exit shell code. So if we want to write exit system call, sorry, not exit system call but exit shell code, then we need to first write assembly program for our shell code. So in this case we have written exit shell code, like exit program in assembly. So the first step is we have to write assembly program for our shell code. Whatever shell code we want to create, we need to write first assembly program for that particular program. Now after this first step, we have like written assembly program and we have just assembled it. After that, what we need to do in step 2, we have to we have to extract the shell code from this assembled object file using object dump. So we have to extract the shell code. You can see this is our shell code using object dump program. So using object dump, we have to extract the shell code from our object file which we have created from our assembly program. So this is step 2. Now we have extracted our shell code. You can see this is our shell code. Now after this step, the next step will be to check if there are null bytes in our shellcode. We have to perform a check in the step 3. So we need to check if there are null bytes in our shellcode or not. So we have to, if there are null bytes, what we have to do, we have to modify the assembly code. If there are null bytes, then what we need to do, we need to modify this assembly code. We have to modify this assembly instruction so that there will be no null bytes in our shellcode. You can see here in step 3, modify the assembly code such that there will be no null bytes in shellcode. There will be no null bytes in our shellcode. You can see here there are null bytes, because nulls will break the shellcode execution. You know, if there is null bytes in our shellcode, then this shellcode is not going to work. This shellcode is not going to execute in memory because of these null bytes. So in step 3, we have to check if there are null bytes or not. If there is a null byte, then we have to modify our assembly source instructions such that there will be no nulls. So let's move on to our next step. And you can see right now we have modified our assembly source instruction. You can see we have just modified few lines. You can see in first line we have used XOR operation here, XOR RAX and RAX. What it means? It means it will zero out RAX, means it will like the RX register will be 0 here using this XOR. After putting 0 in RX using XOR, what we are doing here, we are just moving this 16 to AL. So we have just modified, in place of RAX we have used AL here, the 8-bit unit of RAX. So we have used just AL here, AL register, which is just 8-bit. And after that, in the last modification, you can see in place of move 0 into RDI, we have used XOR RDI and RDI, means we are just moving 0 into RDI. So this is just an alternative way to use the same thing in a different way. So in place of move 0 into RDI, you can see here, in place of move 0 into RDI, ultimately we are moving 0 into RDI. So we can also move 0 in RDI using XOR. Perform XOR between RDI and RDI. So it will be 0 ultimately. So we have modified our assembly source, and after this modification, little modification, you can see there are like all the null bytes are gone. You can see there is no null bytes in our shellcode after extracting it. Like after this modification, we have to just assemble this file and generate our object file, and from that object file we have to extract the shellcode, and we have to again check if there are null bytes or not. Okay, and you can see right now there is no null bytes. So no nulls, it means that we can test our shellcode in the next step. So step 3 is completed. Now in step 4, means in the final step, you can see we can test the shellcode in C program. Now we can test our final shellcode in our C program. This is the final step. So these are the 4 basic steps by which we can create any shellcode. So that's all for this video, because I don't want to create a longer video for this. We will do all these steps in the next video, step by step. So if you have any confusion regarding this video, this concept, let me know in the comment section. I will surely help you. So I will continue from here in the next video. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part we are going to create our first shell code, which is exit shell code. And in order to create our exit shell code, we will follow all the steps one by one, which I have explained in my previous part. So let's follow the first step in which we have to write our assembly program for our shell codes. And you can see this is our assembly program. In this assembly program we have used, you can see this is our text section, then we have our entry point, which is our start label, and in this start label we are using exit system call here. So we are going to create exit shell code, so for that we need to use exit system call here in our assembly program. So you can see we are moving 60 into REX register. This 60 is the system call number for exit, and then we are moving 0 into RDI, which is the return status value, and then we are using the syscall keyword in order to execute this system call, this exit system call. So let's follow the first step. So let's write our assembly program in our lab machine. So this is my lab machine. Sorry. So let's first create our assembly object file. Not object file, but let's write our source file. So let's name it exit.asm, and let's write our text section, and in this text section let's mention our entry point using global keyword, and then let's write our start label. So in this start label, what we have to do, we have to write our exit system call, because we are going to create exit shell code. So move, then we have to move the system call number in our RX register. In this case system call number is 60, so 60 is moved into RX, which is the syscall number for exit. After that we are going to move the return status value into RDI register for exit, and in the last, this is our syscall keyword, which is going to execute this exit system call. So this is our exit system call. Let's write and quit, and let's generate our object file from this source assembly program. So not program, but source file. So let's use YASM. Then we have to mention the file format, in this case 64-bit, and then we have to mention our source file here, which is exit.asm. Hit enter, and right now you can see our object file is generated successfully. Now our first step is completed. Let me show you. This step is completed. Now we are going to follow the step 2. So in step 2 our object file is generated. Like in step 1 our object file is generated. Now what we need to do, we need to extract this shell code from assembled object file using object dump. So we have to use object dump utility in order to extract the shell code from the assembled assembly program. So let's perform step 2. So let's use object dump, objdump, object dump, then -d. -d means we are decompiling, or you can say disassemble. So we have to mention the object file here, which is exit.o, and after that we can use the assembly syntax here, which is intel here. So -m and then intel, and hit enter. You can see we have used object dump to dump the disassembly of our object file. You can see this is the disassembly of our object file, and right now you can see this is our shell code. You can see 48C7 C0 3C, then these are the zeros, like null bytes, then we have these bytes. So these are basically shell code. Like this is our shell code for exit, which we have which we get from our object file, which is this exit.o. So you can see these are the instructions: move, then this 16 to rax. This is the second line in which we are just mentioning the return status value into RDI. Then we have our syscall keyword. So this is our exit system call, and this is our shell code. So what we need to do, we need to extract these bytes, this shell code from this particular object file. So how we can do that? We can do that using this script, this simple bash script, which will extract all these bytes one by one easily using grep command. So this is just using grep command to grep all the bytes, all these shell code bytes from this object dump output. So let me use this extract shell_shellcode.sh, and then let's mention the input here, which is exit.o. We have to mention the object file here, which is exit.o, to extract all the shell codes from this object file. So hit enter, and you can see we have this program has extracted, not program but this script has extracted all the shell codes from this object file easily. So we have finished, like we have completed the step 2, in which we have extracted all the shell code from our object file. You can see exit.o. So we have extracted all the shell code from our object file. So we have completed step 2. We have extracted the shell code. Now let's move to our let's jump into our step 3. Now in step 3, you can see modify the assembly code such that there will be no null bytes. So we have to check if there are null bytes in our assembly, not assembly but in our shell code or not. So let's see. Right now you can see in this shell code which we have extracted from our object file, assembly object file, you can see there are null bytes. You can see after fourth byte, this fifth byte is null, sixth byte is also null, and there are 3 null bytes here. And if we follow here, you can see there are other null bytes also. So there are null bytes in our shell code. So we need to modify our assembly source file so that we can remove these null bytes. So how we can do that? We can again modify our assembly source file. So assembly source file is our exit.asm. Let's modify it. So in order to modify it, let me show you my presentation so that you can relate it. So we need to modify like this. You can see we have modified those 3 instructions with XOR. In the first line we have used this XOR RAX and RX, which is putting 0 in our RAX register in the first line. So let's do that. So in the first line we have to perform XOR operation between RAX and RAX. It means like this XOR is putting 0 in RAX register. After that, in place of RAX we have to use AL register here, which means the same thing. We are going to move this 66 system call number into AL register. So in place of RX we have used AL, which means the same thing. We are ultimately moving this 16 to RX register, but in the lower section of this RX. So AL here, AL is 8-bit register here. So after that, in the last part we are using move 0 into RDI, which can be modified here easily to move 0 into RDI. So we can modify this with XOR RDI and RDI, which is exactly the same thing. Let me comment it here. Move 0 into RDI. So this is exactly the same. If we perform XOR between RDI and RDI, we will send, like, we will move 0 into RDI ultimately. So in place of move 0 in RDI, we have used XOR operation between RDI and RDI. So these two lines are the same, like the purpose is same, to move 0 into RDI. So we have used XOR to replace all the null bytes. So we have done our modification. Let me delete this line so that you won't get confused. So let's write and quit, and let's use our YASM again to assemble this file. So format is ALF 64-bit, then exit.asm, hit enter. Now our object file is modified and generated again. Let's use our extract shellcode.sh script to extract our shellcode from this exit.o object file. So before that, let me show you object dump output so that you can relate the output from the previous part. So object dump -d, and then our object file here, which is exit.o, and then we can mention, like, we can specify the we can specify the assembly syntax, which is Intel here, and hit enter. And you can see, you can relate here the output. You can see this was the first output, and right now it is here. Like right now we have removed all the null bytes. You can see these are the null bytes. So in previous output you can see all these null bytes, and in right now you can see we have removed all the null bytes. You can see there are no null bytes here. In this whole shell code there are no null bytes because we have modified some instructions in our assembly code. So you can see this is our XOR RX and RX, and then we are using move to move this 16 to AL, and then in the last we are using XOR operation between RDI and RDI. So by modifying these instructions we have removed all the zeros, or you can say all the null bytes from our shell code. So right now we can finally extract all these shell codes and we can test it in our final C program. So let's extract it using extract shellcode script, bash script, and then let's use our object file, which is exit.o, and right now you can see this is our final shellcode, which has no null bytes. So let's copy it and let me show you all these steps here. So we have completed step 3. In step 3 right now we don't have any null bytes. So in the final step what we have to do, we have to test the shell code in our C program. So let's follow the final step. So let's open another terminal here so that we can relate some stuff from our previous outputs. Okay, now let's maximize the font size so that you can see clearly. Okay, so let's jump into our directory, in the same directory, shellcoding. So let's clear the screen and let's use our C program in order to test our shell code, in order to test our exit shell code. So let's use vim and then shellcode test.c. This is our testing program, shellcode testing program, and in this shellcode testing program we have to copy this shell code from here, and we have to paste our shellcode into this code code variable. So control shift and V. So we have pasted it here, and then let's let's write and quit, and then let's use our GCC compiler to compile this shellcode, like to compile this shellcode testing C program. So it's GCC space, then we have to use this option to remove all the protection, stack area protection. Means I don't want to I don't want to put any security on stack area, so that we can execute our shellcode easily. So no stack protector, and then we have to mention, like we have to use another option which will remove the stack execution protection, -z, then space, then exec, and then stack. This way we can execute anything, like we have the right to execute anything on the stack area. So after that we have to mention our source file here, and then after we have to mention our output here. So let me adjust a little bit, -o, then exit. Right now our exit binary file is successfully generated, and let's test it. So let's test our shellcode. Hit enter, and you can see our shellcode is executed successfully. You can see shellcode length is 10. If you count the shellcode length, you can see this is first, second, third, fourth, fifth, sixth, seventh, 8th, 9th, and 10th, all the 10 bytes. So we have successfully executed our shellcode, like we have tested our shellcode in our C program. So these are the these are the steps, these are the 4 steps which we have followed in this video in order to create our exit shellcode. So if you have any confusion regarding this concept, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part we are going to perform some memory analysis of our shellcode, which we have created in our previous part, which was exit shellcode. And this is the shellcode. You can see here, this is our C program in which we have tested our shellcode. So in this part we are going to perform some GDB memory analysis, in which we will see where is our shellcode, where this shellcode is loaded and executed in memory. So let's see. So I have opened this C program to correlate all the things, all the source code in our GDB. So in other terminal, let's open our exit shellcode in our GDB. So you can see right now we have our exit program here, and we have to load this exit program into our GDB. So let's use gdb-q, then let's load this exit into our GDB. Now let's first put a breakpoint at our main function, and then let's disassemble main also. And in this case, this is the disassembly of our main function. So in this whole disassembly, we are interested at this particular line. We are interested at this line, or you can say from this line. You can see after calling printf, like after when the program is printing the number of bytes of our shell code, you can see this is call to printf. So it is just printing. You can see this part, this line. In this line, the program is just printing the number of bytes of our shell code. After that, it is going to load our shell code in memory and it will execute it using this return function. So we have to start memory analysis, like we have to make some memory analysis from this particular line here. So we have to keep in mind that we have to focus on this area. So let's put a breakpoint, not breakpoint, we have already done that. I already put a breakpoint at main. So what we need to do, we need to just run our program, and we have to run step by step until we reach at this particular location. So let's use run and hit enter. Right now the program is running and it has paused at our start label, not start label, sorry, at our main function, you can see. So right now the program is going to make some space in our stack. You can see the program is going to subtract some bytes from the stack pointer. You can see this is 10 means 16 byte. So the program is going to make 16 bytes of space here, and 16 byte means, and this is 8 byte. This is our stack area. You can see this is our stack area. So 16 byte will be, this is 8 byte and this is 8 byte. So the program is going to make 16 bytes of space here. So these parts. So let's use next instruction, and right now you can see that space is created. In this space you can see this is the number of arguments from our program, which is 1 here, and after that we have a blank space, not blank space but empty space on our stack. So this is 16 byte which is created using this subtract. So let's use next instruction until we reach at this point. So next instruction, hit enter, it will automatically move forward in the next part. Hit enter, hit enter, enter, then this is our printf call. Hit enter, and then one more step and we will be at this place. So after this, let's use next instruction, and right now we are at this place. So now we have to understand what is going on inside the memory. So you can see the program is going to use LEA instruction, which means it is going to load effective address of some location. So you can see it is going to load this particular memory location, which is the memory location of our code, which is the memory location of our shell code. Code means shell code. So this is the memory location of our shell code. You can see 5010, this is the memory location. So the program is going to load that shellcode memory location into our RAX register. Right now you can see RAX register has the value 15. So let's use next instruction, and right now you can see in RAX, you can see this memory location is loaded, and at this memory location our shellcode is stored. You can see this is our shellcode. If you see clearly 4831C0, you can see 4831C0. So this is our shellcode. So right now our this shellcode memory location is stored in our RAX register. So after that the program is going to move this RAX value into this particular memory location on the stack, you can see clearly this is RBP minus 0x8. So RBP minus 0x8 means this particular location, this particular area on stack. So at this particular area on stack, our shell code is going to be stored, means our memory location of our shell code will be stored at this stack area using this move command. So move RX value into this stack area, which is RBP minus 0x4. So let's use next instruction and let's see. Right now you can see that at this area the memory location of our shell code is stored here. You can see 5010, you can see 5010. So this is our shell code and this is the actual shell code bytes. So the shell code is the memory location of our shell code is stored on our stack. Now after this, the program is going to move that particular memory location into RDX register. You can see move this part, like this particular area, into RDX, means the program is going to move this memory location into RDX register using this move instruction. So let's use next instruction. And if you check RDX, you can see this is our RDX. This RDX contains our shellcode memory location. After that, the program is going to move 0 into EAX. Let's use next instruction. And in EAX, you can see this is our RAX. So 0 is there in our RX. Now after this, after all of this, the program is going to call RDX. The program is going to call RDX, and right now RDX is pointing at this particular memory address, which is our shellcode, where our shellcode is stored. So after this call, what is going to happen? This will jump, like this will jump at this particular memory address where our shellcode is stored. So let's step into, not next instruction, remember this part. This is going to be a call. You can see here, this is going to be a call, not move or something else. So we have to use step into. We have to use step into command here to step into that function, or you can say step into that call. So step into, hit enter, and right now you can see the program has entered into our code segment. You can see this is our code, shellcode area, like shellcode memory area. You can see code. So it has jumped in our code area, and in this shellcode area we have our shellcode stored. Shellcode instructions are stored. You can see this is the first line of our shellcode, in which we are using XOR operation between RAX and RAX. So right now RAX is 0. So if we use next instruction here, then RX will be 0. It was 0 before, right now it is 0. After that, we are moving this 60, this hexadecimal value, which is the system call number for our exit system call, in AL register. AL means RX register here. So this 0 will be replaced with this 0x3c, which is 60 in hexadecimal. So let's use next instruction. Right now you can see this 0x3c is moved here. After that, the program is going to perform XOR operation between RDI. So that RDI contains 0, which is the return status value for our exit system call. So if we check our RDI value, you can see it is 1 right now. So after executing this XOR, this RDI value will be 0, which is the return status value for our exit system call. Hit enter. Right now RDI is 0. After that, we have our syscall keyword, which will execute our exit system call. So let's use next instruction, and you can see it has executed our shellcode and exited normally. You can see program has exited normally. So you can see how this shell code is loaded in our memory and how we can clearly see all the instructions one by one, how we can execute all the instructions line by line in our GDB. So that's all for now. If you have any confusion regarding this concept, let me know in the comment section. I will surely help you. So we will perform all these steps in our upcoming shell codes which we will develop. So that's all for now. I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part, I'm going to show you how we can write our hello world shell code. So let's see what are the basic techniques by which we can write our hello world shell code. So you can see this is just a basic assembly code in which we are just printing hello world. You can see this is our data section. In this data section we have defined our string hello world inside this string message. After that, in our text section we have our write syscall. You can see here we have our write syscall in our start label. You can see, and this is the system call number for write syscall, which is 1 here, which is going into this RAX register. After that we have our file descriptor, which is going inside RDI, and after that we have our hello world string memory address, which is going inside RSI. After that we have our number of bytes, total number of bytes, which is 12 here for this hello world string, and it is going inside RDX. So this is our write system call. It's very easy and simple program. So there is a problem here. We cannot use this assembly to create our shell code for hello world. So what is the problem? The problem is we cannot use hard coded addresses of our hello world string inside our text section. This is the problem. So we have to find a way such that we can load the memory address of our hello world string dynamically in our text section. So we don't have to use this data section. We have to use our text section. Inside this text section we have to use a technique. We have to find a way such that we can store, like we can load the memory address of our hello world string dynamically when the program loads in memory. When our shell code loads in memory to execute, it will load this string memory address dynamically in our RSI register. So we have this problem here, like we have this single problem here which we have to solve it. So let's see how we can solve this problem. Rest part is very simple. Rest part is same which we have did earlier in our exit shell code. The only problem is this: we have to find a way in which we can load our hello world string message memory address dynamically in our text section. We don't have to use this data section. So let's see how we can do that. It's very easy. No complexity here. So you can see, don't get confused to see all these. Just focus one by one. It will be very simple for you to understand. So you can see the title here, jump call pop technique. We are going to use jump, call and pop technique. So we will use these 3 instructions in our assembly to solve that problem, to solve that address loading problem dynamically. So we use these 3 instructions, jump, call, pop, which uses stack memory. So through these technique, it uses stack memory, means we will load our hello world string memory address from the stack memory into our text section, into our shell code when it loads inside the memory dynamically. So these instructions will uses stack memory to load the addresses of our address of our hello world string in our text section using pop instruction. So basically we are going to use pop instruction here basically, and pop is the only instruction which is helping us here to load our address dynamically from the stack. And other instructions are also very important here, which are jump, call and pop. These are the three most important instructions for this shell code. So let me explain you let me explain you one by one all this concept, jump, call and pop technique. You can see, focus on from here, focus on this part. So first we have our text section, very easy. This is our text section. In this text section, now we have our global keyword in which we are defining our entry point, which is our start label. Now after that we have our start label in which we are going to write our program, assembly program. So after that, after this start, you can see we are using jump here. We are using jump instruction here. So what is going on, what is going to happen here? This jump instruction is going to jump at this particular label, which is 1 here. So let's find out where is 1 here. You can see this arrow here. This is 1. So the program is going to jump at this particular memory location, which is 1 here, means 1 label. So it will jump here. This is the first step. First we will jump at our label 1 here. After jumping, we are after this jump we are using call instruction here to call shellcode label here. So don't focus on shellcode right now. Don't focus where is shellcode. Just focus on this call only here. Okay. So after that, this is our call instruction, right? So in the next step, what is going to happen? Now before calling anything, before jumping to anything, what this call will do? This call will store the memory address of the next instruction. You can see this is the next line in which we are defining our hello world string inside our string message variable here. So we have written this line intentionally here after this call, because what this call is going to do, first it will store the memory address of this line where our hello world string is stored. So this call will store the memory address onto the stack. This is the second step. This is the second step in which this call is going to store the next line memory address. At this line we have stored our hello world, remember this part. So this memory address is going to be stored on the stack memory area on the top of the stack. You can see here, this is our stack memory. So step 2 is completed. We have used jump, then we have used our call. Right now we are half of this call. So this call will first store the next memory address, next line memory address into the stack, which means our hello world string memory address is stored in our stack memory. Now in the next step, what is going to happen? In step 3, this is our step 3, this call is going to jump at shellcode label, and follow this line. You can see this arrow. This is our shellcode. So it will jump here or on the shellcode label, and in this shellcode you can see the first line instruction is pop RSI. The first line instruction is pop RSI, means you can see jump, call, pop. We have used jump and call. Right now we are going to use pop, the third part. So this is our pop instruction, pop RSI. So what this means, let me show you through this diagram. You can see this pop RSI. This is the fourth step. What is going to happen? This pop RSI means just pop the top value of the stack memory area into RSI register. So right now what is going to happen, string message address means hello world message memory address will be stored from the stack, from the top of the stack to RSI register using this pop instruction. So it will but it will pick up the address of our hello world string into this RSI register from this pop instruction. So we are loading the memory address dynamically from the stack memory into this RSI register. After that, after loading the memory address of our hello world string in RSI, the rest part is same. You can see this is our system call number for write, which is going inside RAX. Then we have our file descriptor in RDI. Then we have our number of bytes which we want to print into RDX. Then we have our syscall. So we have solved our problem using jump, call, pop technique, in which we have loaded our hello world string memory address dynamically in the runtime inside our RSI register. And if you see carefully, we are storing our hello world string memory address inside this RSI. So finally we did this, like finally we have loaded our memory address of hello world inside RSI register using dynamic method. So this is jump, call and pop technique. Very simple technique. Nothing is complex here. Just follow, like if you follow these numbers you will get to know this is very simple. So this was jump, call, pop technique, in which we will print, like we will create our hello world shellcode, which when executed will print hello world onto the screen. So we will use this technique in the next video. Practically I will show you how we can create our hello world shellcode using this jump, call, pop technique. So if you have any question regarding this concept, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. So hello everyone and welcome to the next part of this tutorial. So in previous part I have demonstrated you how this jump, call and pop technique works in order to create our hello world shellcode. So let's follow these steps in order to create our hello world shellcode in our system, in our lab machine. So let's minimize it, and this is our Ubuntu machine. And first let's create I think there's a problem, let me solve it. All right, so let's first create our assembly file, not this, but let me show you this part. Okay, so we have our shellcode here. You can see here we have to write these instructions, like we have to write these assembly instructions one by one. So let's write the same thing in our source file. So vim, then let's name it hello world.asm. So in the first line let's create our text section. In this text section let's first specify the entry point using global keyword. Then after let's write our start label. Now in the first step we have to use jump instruction, jump, and I want to jump at one label. This is our label name, 1. So in one label, let me write 1 here. So 1. So this is our one label. In one label, we are going to use call here. So call, and I want to call shellcode. Now we have to define our shellcode, but we will define it after writing our after defining our hello world string variable. So in this case, string, not string, what was the name, string message. Okay, so we have to write this line here, you can see. So string message, you can use any other name, but in my case I'm using string underscore message, then db, then we have to write our hello world here, string, then 0xa to terminate the to break the line. So we have written, we have defined our hello world string here in the next line, and right now we have to write our shellcode label here, because when this call will jump to shellcode, we should have our shellcode here. So here we will write our shellcode label. So shellcode. Now in this shellcode, what we need to do, we need to write our write system call here. So to write our system call, first we need to use pop here, because I already told you in previous part. Let me show you again. We have to use pop instruction, pop RSI, which will pop the top value of stack inside RSI. The top value will be the hello world string memory address. So let's do that. So pop RSI. So this is completed. After that, what we need to do, we need to write the rest part, the remaining arguments for the write syscall. So the first argument was to move the system call number into RAX, so which is 1 here. After that, we have to move the file descriptor number inside RDI, which is 1 here. After that, we have to move the number of bytes which we want to print inside RDX register. So in this case, it is 12 bytes. This hello world plus this part is 12 bytes. And after that, we have to use our syscall keyword. Then after this system call, this write system call, we need to write our exit system call to exit the program normally. Otherwise, it may get segmentation fault, means the program will crash. So that we should write our exit system call here. So for that, it's very simple. Move 60 into RAX, then move 0 into RDI, then we have to write our syscall keyword in order to execute this exit system call. Now our shell code is completed here, you can see. Let's check again. In the first step, we are jumping at one label, which is here. So the program will jump here. After jumping here, it will execute this call. So when the call is executed, the first part of this call will, the first task of this call is to store the next line memory address into the stack. So this hello world string memory address will be stored on the top of the stack. After storing this value, this call will jump at this shellcode label which is here, and after jumping here it is going to pop the top value of the stack into RSI. So the top value of the stack will be this hello world string memory address which is going inside this RSI. After that we have our like other input parameters, or you can say other arguments for our write syscall, which is here the write system call number, then we have our file descriptor, then we have our number of bytes which we want to print into RDX, then we have our syscall, then after we have our exit system call which is going to exit this program normally. So this is our shellcode for hello world. So let's save this file and let's use YASM to assemble this file. So -f elf 64-bit, and then we have to mention our source file. Right now our object file is generated. You can see hello_world.o. This is our object file. So what we can do, we can disassemble our object file to see if there are null bytes in our shellcode or not. So let's see. So we will use object dump, then -d to disassemble our hello world.o, and then let's mention the assembly syntax here, which is Intel here. And right now you can see this is the disassembly of our shellcode. So you can see we have to track down all the null bytes here. So we have to remove all the null bytes anyhow. So you can see we have null bytes in the third line here in move, where we are moving our system call number into RAX. So in this part there are 3 null bytes. Like the same way in this particular line where we are moving the file descriptor value into RDI, this line also has 3 null bytes. Then in the same way we have other 3 null bytes in this line where we are moving 12, means we are moving the number of bytes which we want to print into RDX register. After that we have our syscall. So we have like these null bytes here which are using, like in these line we are using move instruction here. So somehow we have to like replace these instructions with something else, so that these null bytes will be removed. After that we have another null bytes here. You can see in our exit system call, you can see this is our exit system call. So we have already removed the null bytes in our exit system call, like exit shellcode. So it's very easy for us to do the same thing here to remove these null bytes. Now after that, after this exit system call, we have other code segments, like we have other assembly code, but in these assembly codes there are no null bytes. You can see no null bytes is there. Only null bytes are here in our write syscall, in these 3 instructions, and in our exit system call here. So let's modify our assembly code in order to remove these null bytes. So let's open our hello world.asm again and let's modify our code. So you can see what we can do here. We can perform XOR between RAX and RAX here, which will put 0 in RAX, and after that we can move 1 in AL register. AL is the 8-bit register of RAX. So it will like this will be the same thing. So we are moving 1 into this AL register. After that, the second move, which is move 1 into RDI, for this what we can do First, we can perform XOR between RDI and RDI, so that RDI will be 0. After that, what we can do here, we can, in place of move, we can use add here to add 1 into RDI. So nothing is like we have just we are just doing simple modifications. The working of these, like the actual working of these instructions will be the same. So we are adding 1 to RDI, means we are just moving 1 into RDI. This is like, the meaning is same here. We are just altering the instructions so that we can remove our null bytes. After that, we have the last part here in our write syscall, which is move 12 into RDX. So what we can do here, we can use again XOR RDX, then RDX, and here in place of move, what we can do, we can use add here. So add 12 in RDX. So this will add, like this will move 12 into RDX. So it will be, the instruction will be the same. Like the task, the target is to move, like to store 12 into RDX, and we are doing this using this add instruction. So it's simple. So we have modified all these instructions one by one, and if we check it, let's write and quit, and let's assemble it again, and let's use our object dump to see the changes. And right now, if you see carefully, this is our write syscall. You can see pop RSI, then till here syscall. So we have used XOR, like between RX and RX, then we are moving 1 into AL. You can see all the null bytes are removed from here, from this write syscall. You can see there were null bytes in our write syscall before. Right now, all these null bytes are gone from here. You can see. Now after that, we have our null bytes in our exit system call. So let's remove these null bytes by modifying these instructions, these assembly instructions one by one. So let's open our assembly file again. So vim, then hello world.asm. Now let's modify this exit system call. Not modify, but let's alter some instructions a little bit so that the null bytes will be gone. So let's first perform XOR between RX and RX, and after performing XOR, in place of RX we can move 16 to AL. So this will remove all the null bytes in this line, and after that we can perform XOR between RDI and RDI to put 0 into RDI. So we don't need to use this move 0 into RDI. So XOR RDI and RDI means we are giving 0 to this RDI register ultimately using this XOR. So problem is solved. Let's write and quit, and let's assemble it again using YASM, and let's see the object dump output, if these null bytes are gone or not. You can see right now, you can see all the null bytes are gone. You can see this is our exit system call and null bytes are gone. So we have removed all the null bytes, and after this, let me use our script which extract all the shellcode from this object file. So let's use extract shellcode. Then we have to mention the object file here, which is hello world and hello world.o. And right now you can see this is our shellcode. So let's copy it and let's open our shellcode testing C program. So vim shellcode test.c, and let's paste our shellcode into this area. Let's overwrite and let's compile this shellcode test program in order to test our shellcode. So gcc -f no stack protector. We are just removing the stack protection, and after that we are removing the stack execution. Like we are applying, or you can say we are telling the GCC that please remove the write protection on the stack memory area, so that we can execute anything on the stack by using this Z command, Z option here. So exec stack. Then after we have to mention our source file, which is shellcode test.c, and we have to mention the output file here. So -o, and let's name it hello world. Hit enter. So okay, there is a mistake in this option. So f no, I misspelled. So this is f no stack protector. So right now our hello world file is generated here, which is binary file. So let's test it, hello world, and you can see that our hello world shellcode is successfully executing for us. You can see hello world is printing, and the length of our shellcode is 51 bytes. So our shellcode is printing successfully on the screen, means our shellcode is working. So we have developed our shellcode successfully. So right now let's open our GDB in order to perform some memory analysis, in order to see our shellcode inside memory, how it is working. So let's clear the screen first, and let's open our hello world in our GDB. So this hello world is loaded in our GDB. So let's first put a breakpoint at our main, and let's run our program. So the program is running, and let me put this this Ubuntu machine in the full screen mode, so that we can see all the registers. So switch, and right now let me adjust the terminal area so that you can see all the parts. So you can see we are able to see all the registers here. So right now the program is paused at our start label, and right now we have to check our but we have to make some analysis on our shellcode instructions in this particular binary. So what we have to do, we have to use next instruction in order to follow all the execution of this binary. So in this case, you can see right now the program is going to create 16 bytes of space on this stack memory area. You can see this memory area. So this is 16 byte, 8 plus 8, 16. So this is 16, which is in hex format. 10 is 16. So this will create 16 bytes of space on the stack area, on this area. So let's use next instruction, and right now you can see that it has created 16 bytes of space, and in this space this one is our argument, single argument, which we have given. So it's clear, like all the parts are clear right now here. Now it is going to load our shellcode into RDA register using LEA instruction. So let's use next instruction, and you can see that right now this RDA is loaded with our shellcode memory address. You can see 5020. This is the memory address of our shellcode. Now after that it is going to call the string length function to calculate the string length of our shellcode. So let's use next instruction. After that it is going to move the value of ex into esi. So right now the value of ex is 0x33. So let's use next instruction to execute this, and right now you can see RSI has 0x33. After that it is going to load the it is going to load the effective address of this particular area, which is the relative address from this RIP instruction. So let's use next instruction to load it, and after that we have our move instruction. So we have to just follow all these instructions one by one till we will encounter our shellcode call. So let's use next instruction. This is the printf call. Let's use next instruction. Right now you can see here that our shellcode address, memory address, is going to be loaded in RX register. You can see here after printf. So let's use next instruction. You can see RX is loaded with our shellcode memory address. After that the memory address from our the memory address of our shellcode, which is stored in our RX register, is going to be stored on the stack area. You can see this is a stack area, and this stack area you can see RBP minus 0x8. This area is belong here. You can see this part. So RBP minus 0x8 means this particular area. So at this area our shellcode is going to be stored, like our shellcode location, memory location is going to be stored. So let's use next instruction. You can see this is the memory address of our shellcode, which is stored here on the stack. After that it is going to move this particular memory address into RDX register. You can see RDX register is 0 now. So let's use next instruction. Right now you can see RDX has the memory address of our shellcode. So after this you can see 0 is going to be moved into EX. Let's use next instruction to execute it. Right now the program is going to execute our shellcode finally using this call instruction here. So call RDX, and you can see right now in RDX, if you see carefully, RDX has our shellcode memory address. So the program is going to execute our shellcode right now using this call instruction. So let's step into this call using SI. And right now you can see this is our shellcode. This is our right shellcode. You can see in the first part, let me open another terminal to show you the proof so that you can cross verify all the parts one by one. I'm sorry for getting getting the video lengthy. I don't want it to get lengthy, but the concept itself is very complex, little bit complex, not very complex. So stay with me few more minutes. So let's cat our, not this way, let's cd into temp and then temp. Here our shellcode is there. So let's cat, not cat, but let's vim shellcode test, not shellcode test, but our assembly file, which is hello world.asm. So this is our assembly file, and you can see here that you can see clearly here. Let me adjust the screen little bit. You can see here clearly. First we are going to jump at our one label here. Let me increase the screen. Okay, so you can see here, first we are jumping at this particular one label, and you can see jump this one label, which is the memory address of our one label. So this is the first line of our shell code, right? Shell code. After that, we are going to jump at this particular memory location. So let's use next instruction. You can see it has jumped from this location to this location. So it has jumped at this location 1. After that, it is going to call, like it is going to execute this call instruction. You can see right now, call. So this is going to execute this call instruction, and what is going to happen right now, before calling this, like before jumping at this particular location, what is going to do, like what this call is going to do, what I already what I have told you here. You can see here, before going to execute this call, what this call is going to do, it will store the next line memory address on the stack memory area, which is our hello world string memory address. So let's cross verify if this is happening really inside memory or not. So it will be very interesting concept here. You can see this call, and after this call, this is our hello world string. This is our hello world string. So what is going to happen, let's use next instruction and let's check the stack area, because according to our concept, like according to our technique, what is going to happen, this stack memory will store this particular hello world string memory address. So let's see, let's check the stack after executing this call. So let's use next instruction, and right now you can see what is happened here, like it has printed hello world. Okay, so I think we have I have to use step into maybe, but anyhow you can see that it has executed hello world here. You can see it has printed hello world. So we have followed till here, and after that I have to use step into, maybe I have to use a step into to step into this call, so that we can follow up the string message location on the stack. But it's not like it has executed all the instructions at once. So it has executed, basically it has jumped at shell code, I think, and it has executed all these parts. And you can see program exited normally, means it has just jumped from here to this part and executed all the parts. So that's all for now. You can follow, like you can step into this call and try to see all the stack memory area yourself, to see, like I have already shown you all the parts, like all the shell code of our hello world, which is the proof that our shell code is executing inside this memory. So that's all for now. If you are facing any kind of trouble in this, like in creating our hello world shell code, I will definitely help you into this. So try to practice it, and try to print in place of hello world, try to print other strings as well. And sorry for the lengthy video. My what we can say, my intention was to help you understand each and every part of this practical. That is why the video is the video is going very big in size. I'm sorry for this. So please follow all the parts, like all the different parts, and do your practicals. If you are facing any kind of trouble, I will surely help you. So till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part we are going to perform some in-depth memory analysis of our hello world shellcode in our GDB. So let's do this. So let's load our hello world in our GDB using GDB command. You can see hello world is loaded, and in my right side you can see this is our source file. This is the program source file. So I have opened this file here because we want to correlate, like we want to see where we are in our program when we make some analysis in our GDB. So in GDB, let's first put a breakpoint at our main, and then let's disassemble main, and let's see the disassembly. You can see this is the disassembly, and in this disassembly the area of interest for us is this line. You can see in this line we are, like, the program is calling this RDX. So in this RDX our shellcode is stored. So we have to focus on this part, like we have to start memory analysis from this line. So this line is actually this location, this return call here, this return function. So at this line we have to make some memory analysis. So let's run our program and let's see how the program is executing our shellcode. So let's run, and now the program is paused at the start of our main function, and right now it is going to create some space on our stack. You can using this subtract instruction. You can see 0x10. So it is going to create 16 bytes of vacant space here in this stack using this subtract instruction. So let's use next instruction, and you can see 16 bytes are created, and in this 16 bytes this is our number of arguments which we have given for this program. So what we can do, we can use next instruction multiple times so that we can reach here, so that we can reach at this particular line, so that we can speed up our process. So let's use next instruction until we found the call instruction, call RDX. You can see right now this is our call RDX. So we have to reach here. So let's hit enter, and right now you can see that our shell code, you can see this location. This is the location on our stack. You can see RBP -0x8. So at this particular memory location our shell code is stored. You can see this is our shell code. This is the memory address of our shell code, and this is our shell code. So basically the memory address which is stored on our shell code on our stack memory area is going to be moved into this RDX register. So basically right now you can see our RDX is 0 at this particular moment. our RDX is 0. So the program, like the program is going to store the memory location of our shell code into our RDX register. So let's hit enter, and right now you can see this RDX register is loaded with our shellcode memory location, which is this memory location. After that, the program is going to move 0 into EAX. Let's execute it using next instruction. After that, this is the line which is very important for us here, because in RDX, like in this particular memory location, our shellcode is stored. So let's use step into to follow this call. So it is going to jump at our shellcode. So let's use step into SI in our GDB. Now pay attention from this step. So SI step into this call. So right now let's close this source file because we don't need this anymore. And what we need our assembly source code here. So in this case, hello word, then ASM. So we need our assembly file here to cross verify our instructions in memory. So right now this is our shell code, you can see, and you can see right now this is exactly the same. You can see this is the first line of our shell code here, and you can see clearly right now here in our source code, you can see jump to this one. This is the first line, and you can see this is our first line. So this is jump, and this is our one memory address. This is our one label memory address here. So the program is like in our shell code, we are going to jump at our one label memory address. So you can see jump is taken, status is jump is taken, because we are going to jump at this particular memory location, which is the location of this one label. So let's use next instruction, and the program has jumped here. The program has jumped at this one. Right now at this one, you can see this is one. Program has jumped here, and right now it is going to execute this call instruction. So you can see this is our call instruction, and this is going to call, means this is going to call this particular shellcode label, which is this location. So it is going to jump at this shellcode, but before jumping at shellcode, what is the most important concept here? The most important concept here is, let me show you again. Before jumping on this shellcode, the program is going to store the memory address of our hello world, which is the next line instruction in our shellcode. So this hello world string memory address will be stored on the top of the stack before this call instruction. Means like this call instruction perform two steps. In the first step, it is going to store this next line memory address onto the stack, and in the second step it is going to jump at this shellcode. So let's see if it is happening in our memory or not. So what we can do, you can see right now on the stack, on the top of the stack, and these are the different data. You can see random data. So what we can do, we can use step into, because this is call, so we have to use step into to see the changes. So let's see if our hello world string memory address is stored on our stack or not. Basically, specifically at this place at the top of the stack. So let's hit enter, and right now you can see hello world string is stored on our stack. Means the memory address of our hello world string is stored on the top of the stack. and this is happening. What we have learned in our previous part is happening exactly in memory. So this hello world is stored on the top of the stack, and right now we are going to perform, like we are going to execute pop RSI. So what this pop RSI will do, it will load the top value of our stack, which is the memory address of our hello word string, into RSI register. So let's minimize it, and you can see this is the instruction pop RSI. So this memory address will be loaded in RSI register. So right now this is our RSI. You can see on this RSI, this is the different memory address at which this string is stored, which is shellcode length, something like this is shellcode length. So in the next step, this RSI should contain this hello world memory address. So let's use next instruction, and you can see this is our RSI. So hello world memory address is stored on this RSI. Now in the next part, like in the next line, what we are going to do, we are going to perform XOR between RAX. You can see this is our shellcode, which is exactly the same here. So let's use next instruction. So Rx is 0 right now. Now the program is going to execute our next instruction, which is move 1 into AL. You can see this one will be moved into AL, which is Rx here. Let's use next instruction. You can see all these instructions are the same. You can see XOR RDI, the next value is XOR, like the next instruction is XOR RDI RDI. This is XOR RDI RDI. So what is going to happen? This RDI, where is RDI? This RDI will be 0. So let's use next instruction. Then the program is going to add 1 into this RDI. And right now RDI is 0. So let's use next instruction, and you can see RDI is 1 here. After that we are performing XOR between RDX. So let's use next instruction. Then we are adding 12 into RDX. So right now RDX is 0. So let's use next instruction. Right now you can see RDX is 12, and after that this is our syscall keyword. The program is at this location in our shell code. So let's use next instruction. Now after that we have our exit system call shellcode. You can see this is our exit system call, where we are performing XOR operation between RX. You can see XOR RX and RX. After that we are moving this 60 into AL, which is the system call for our exit system call here. You can see clearly. After that we are performing XOR with RDI, so that RDI value will be 0, which is the return status value for our exit system call. So let's use C to continue our program, so that program exits normally and print hello world. Hit enter. You can see the program exited normally. So basically we have seen in this particular memory analysis that all the hello world shellcode is executing inside our memory. So this is how we can perform basic memory analysis of our shellcode execution. So if you are facing any kind of trouble, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part I'm going to show you how we can create hello world shellcode using stack memory. So let's see how we can do this. So you can see in this slide, this is our shellcode, and in this shellcode you can see I have taken only a write system call part here. This is our write system call assembly instructions. You can see in the first line, just focus on this part. we are just moving the system call number for write into this RX register using move instruction. Like the same way we are moving the file descriptor into this RDI, and then this is our hello world string memory location, which is going to move into this RSI register. After that we have our number of, like, total number of bytes which we want to print, which we have to mention in RDX register here using move instruction. So now our task here is to load this hello world string dynamically into this RSI register. So let's see how we can do that. So we have to load this hello world dynamically into our RSI register. This is our task here, and we will do this using our stack memory area. So let's see how we can do this, how we can load this hello world string into our RSI register using stack memory. Now in the first step we will work on this particular line. Rest part will be the same. You can see these two lines will be the same and these two lines will be the same. So we have to move on this RSI part. So let's jump, and you can see in the first step what we have to do. This is our stack memory. In the first step we have to push this hello world. We have to push this hello world bytes into our stack memory area using push instruction. So the trick is, like, the main trick here is, we are not going to push the whole string here. We need to push the last 4 bytes. We need to push the last 4 bytes of this hello world in hexadecimal format, like in hex encoded format, in reverse order. Keep in mind, we should take these 4 bytes in reverse order and encode it with hex, like hexadecimal value. So this is the hexadecimal encoded value for this last 4 bytes of our hello world. So we will push this hex value of our hello world into stack, and right now you can see the last 4 bytes are pushed on the stack. Now after this, after pushing these 4 bytes first, we are going to move the rest part. We are going to move the rest part which is left after moving these 4 bytes. The rest part will be moved into RBX register. So we are using RBX register here to move the rest part of our hello world string into RBX. So you can see this is the hex value of this particular string, and after moving this the rest value into RBX, what we need to do, we need to push this RBX register. We need to push this RBX register onto the stack, so that the remaining part, like the remaining hello world string, will be pushed on the stack. You can see the remaining part is here. So right now our hello world string is pushed onto the stack. Right now we have our hello world string completely on our stack. So after this push, like after pushing RBX, which has the hello world string, like which has these hello world bytes, what we need to do in the last step, we are going to move the RSP content. We are going to move the RSP value into RSI register. And right now if you see carefully on our stack, on our stack pointer, we have our hello world stored. You can see this hello world is stored. So this hello world will be moved inside this RSI. So this hello world means the location of this hello world on the stack will be moved into the RSI register. So the memory location of the stack will be moved into this RSI register where our hello world string is stored. So you can see this is a simple trick in which we have used push operation here, in which we have pushed our hello world string onto the stack, and then we are loading that pushed value from the stack into our RSI register finally. So this is very simple concept to understand here. So we will do the practical part of this concept in the next video. So if you have any confusion regarding this topic, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part we are going to create our hello world shellcode using stack memory area, like stack memory technique. You can say technique, you can say a stack memory, using stack memory. So let's start writing our shellcode. So let's minimize it and let's jump into our lab machine, Ubuntu lab machine. So let's first create our assembly file. So vim, then hello world.asm, and in this assembly file let's create our text section first, then let's specify our entry point using global keyword, and then after let's start writing our start label here. So first let's write our exit system call here first. So move, then first we have to move the system call number for write, which is 1 here, into Rx. Then we have to move the file descriptor value into RDI. Then after we have to move the hello world string in RSI register. Like we have to move the hello world string memory location into RSI register. Then after we have to move the total number of bytes which we want to print into our RDX register, which will be 12 here generally. So after that we will use our syscall keyword. Then we will write our exit system call to exit this shellcode normally. So for that, first we need to move the system call number, which is 60 here for exit system call, into Rx. Then we have to move the return status value into RDI. Then after we have to use our syscall keyword in order to execute this exit system call. So our code is completed, and right now we have to work on this particular line, in this particular line. So in this line we have to use our method here, which we have seen in our previous part. So we have to implement this method. So first we need to push the last 4 bytes in hexadecimal format in reverse order. So first, in the first step, what we need to do here, we need to convert this hello world in reverse order, and after that, after converting it in the reverse order, we have to encode this hello world string into hexadecimal format. So let's do it using Python. It's very simple. So in our another terminal, let's open up our Python shell, and in this Python shell let's name our let's create a string. In this string let's write our hello world. So hello world. So This is our string, a hello world, and if we want to reverse this string, what we need to do? We need to do this in Python and -1. It's very simple. You can see this hello world is printed in reverse order here using this particular technique in Python. So after that, like we have reversed, I want to encode this reverse string into hex format, and right now you can see we have got our hexadecimal format in reverse order of this hello world. So right now what we need to do, we need to perform our first, like we need to write our first line in which we are going to push the first 4 bytes in hex format. So you can see here, let's copy the first 4 bytes here. So this is the first byte, this is the second byte, this is the third byte, and this is the fourth byte. So we need to copy these 4 bytes here, and let's use push and then 0x, then paste it. So we have pushed the last 4 bytes. After that, what we have to do, let me show you again our slide. We have pushed the last 4 bytes in this case, which is this part. So we have pushed. After pushing, we need to move the rest part into RBX register. Okay, so let's do this. So let's copy the rest part here. So from here till here, after 72, let's copy it and let's use move, and I want to move the rest part in RBX. So 0x, then paste it, and let me adjust the comments a little bit. So moving the rest part of hello world. Okay, so we have moved the rest part, and after that what we need to do, we need to push this RBX, we need to push this rest part into the stack or onto the stack, whatever it will be. So we are going to push this RBX onto the stack using this push command. So push RBX. So what is going to happen here? Push the rest part on stack. So this will put the rest part on our stack. So let me show you the concept here. So this way, like we have used these 2 commands, like not 2 commands but these 3 commands here, not commands but instructions. So we have used these 3 instructions in which we have completely pushed our hello world string onto the stack. Now after that, after these 3 lines, right now we can load the memory location of this hello world string into RSI register using this move instruction here. So move RSP means stack pointer. So wherever the stack pointer is pointing right now, it is pointing at our hello world. So that particular memory address of our stack pointer will be moved into this RSI register using move RSP into RSI. So through this way we are moving the memory address of our hello world string into RSI finally. So our task is completed here. So let's move it. So move RSP like this. So move the address which is pointing on our hello world string into RSI register using this RSP pointer. So we have completed all these 4 instructions here in order to load our hello world string dynamically when our shellcode runs in memory. So after that, all these things are completed right now. And what is needed here? Let's first execute, like let's first assemble and link it, and let's test it if it is working or not correctly. Then after, we will modify, like we will remove all the nulls. So let's first write and quit, and let's first assemble it ysm using ysm. So -f format, which is 64-bit here, and then let's specify our source file, then hit enter. Right now our object file is generated. So let's generate final binary file using ld command. So ld, then let's specify the object file in output. Let's use the same name, hello world. So our hello world is generated successfully, like hello world binary is generated successfully. Let's test it if our hello world is printing on the screen or not. So you can see hello world is printing successfully. It means that it will work. So right now what we need to do, we need to not dump, but we need to use object dump -d to disassemble our object file. So hello world.o, and then let's specify the assembly syntax here using m to Intel. So right now you can see that we have some null bytes. You can see in the first line we have 3 null bytes, in the second line we have null bytes, then here you can see these are the null bytes. So you can see this move has null bytes, this move 1 into rx has null bytes, then we are moving this one into RDA, it has also null bytes. And after that, so let's first edit these 2 lines to remove these null bytes first. So let's use vim to open our assembly file, source file, hello world.sm. So let's modify this. So in order to modify this, let's use XOR. So XOR RAX and RAX, and after XORing RAX, let's move this one into AL. So this way the first three null bytes will be removed. So let me show you. Write and quit, and let's again assemble it, and let's open it in our object dump to see the effect. You can see the first 3 null bytes is removed. You can see by using this XOR operation, XOR, and then we have replaced RX with AL register here. See, so we have removed first 3 null bytes. After that there are more null bytes, so in this line, so we have to modify this line like the same way, move 1 into RDA. So let's do the same thing with RDA. So let's open our source file, and let's use XOR. So XOR RDI, then RDI, and then in place of move we can use add here. So we are just adding 1 to RDI after performing XOR operation. So let's write and quit, and let's assemble it again, and let's see the result in object dump. So right now you can see these 3 null bytes are removed. You can see these 3 null bytes are removed completely right now. So there are no null bytes here in these lines. So in the down part you can see there are null bytes, still we have our null bytes. So these null bytes are at this line. You can see move this 12 into RDX. So this is the line where we are mentioning the number of bytes which we want to print on the screen inside the RDX register. So let's modify this part to remove these 3 nulls. So let's open up our source file, and let's go down, and we have to modify this particular line. this particular line in which we are mentioning the number of bytes which is going to be printed in RDX. So what we can do here, we can use here XOR RDX, then RDX, and then in place of move we can use add here. So we are adding 12 to RDX after performing XOR, after performing XOR between RDX and RDX. So 12 will be added to RDX, and let's write and quit, and let's check it again after assembling it using object dump. And right now you can see these 3 null bytes are gone from here, you can see. So we have removed all these nulls. Right now there are nulls in our exit system call. Here you can see this is our exit system call, and in this exit system call we have 6 null bytes. So let's remove these null bytes also using the same technique. So let's use XOR RAX and RAX, and then let's use AL register here to move 16 to AL. Then after that let's use XOR RDI, then RDI, and then okay, we don't need this line because XOR RDI means ultimately we are zero, we are sending 0 to RDI using XOR. So it's completed. Let's write and quit, and let's assemble it again using YSM, and then let's dump all the shellcode using object dump. So right now you can see all the null bytes are gone, all the null bytes are removed from our shellcode. So let's extract our shellcode from this object file using our extract shellcode bash script. Let's specify our object file here, and you can see this is our shellcode. Let's copy it, and let's clear the screen first, and let's open our shellcode testing C program, and let's paste our shellcode into this code variable. Let's write our file, write and quit, and let's use GCC to compile our C file. So f no stack protector, which removes all the stack protection, and then we will use -z option here to disable the stack execution protection from the binary. So exe stack, and then we have to mention our source file, and then we have to mention our output file using hello. Let's use hello only, so -o then hello. Then right now you can see we have our hello. So this is the previous hello world. So let me remove it so don't get confused. So hello world is different here. So right now we have our hello. So let's execute it and let's see if it is working or not. You can see it is working correctly. It is printing hello world, and the shellcode length is 50 bytes. So we have implemented, we have successfully created our shellcode using stack method, using stack memory, using this push move instruction. All we have used only these, we have used this trick in which there are 4 instructions involved, which is push and move, then push and move. So use these use this trick in your lab machine, which I have given you, in my resources section and practice it. So if you have any confusion regarding this particular topic, let me know in the comment section. I will surely help you. So in the next part we will perform GDB analysis on this particular shell code in memory. So I will meet you in the next part. Till then, goodbye. Hello everyone, and welcome to the next part of this tutorial. So in this part we are going to perform memory analysis in our GDB of our hello world shell code, which we have developed in our previous part. So let's open up our shell code in GDB using this GDB command. So this hello world shell code is loaded in our GDB, and first let's disassemble our main function to see the disassembly. So you can see this is our disassembly. So this is the source of this disassembly. So this is our program. So this program's disassembled code is here. You can see this is the disassembly. So in this disassembly you can see this line. You can see this is our printf. This is a call to our printf where we are printing the shellcode length, in bytes. So this will print the shellcode length in bytes. After printing that shellcode length, it is going to perform, like it is going to execute these two lines. So let's make some analysis after this printf. And let's see where is our shellcode going, and we will follow all these steps. We will follow our shellcode where it is going, and we will see how the shellcode is loading inside the memory, and we will perform some good analysis, some good memory analysis of our shellcode. So let's first put a breakpoint at our main, and you can see clearly here after this printf call, these are the instructions where our shellcode is loading in different memory locations. And after that, in the last part, you can see there is a call. You can see this call, like there are only 3 calls here. You can see in this whole main function we have only 3 calls here. The first call is string length. You can see here, in which our shellcode length is calculated here using this string length. Then we have our printf call, and in the last we have our rdx call. So this call, like for us, this call is very important here, because in this call, this rdx has our shellcode, which is going to be executed by this call instruction. So this call will jump into this, this call will going to jump at this particular location, which is pointed by this rdx, and it will start executing our shellcode. So we have to focus on this particular call here. So let's run our program, and let's see how this call, like how our shellcode is going to work in this call. So let's run it, and right now the program is paused at our start, like not start but at the main function, you can see. So let's use next instruction till we reach that call rdx. Let's hit enter, hit enter multiple times so that we can reach that call rdx. You can see we are here right now, and in the next line the program is going to execute this call rdx. So let's see, hit enter one more time to reach this line, and right now the program is going to call this rdx, and we are at this particular line here. So let's step into si, means step into this call, so that we can see how, where is our shellcode right now. and how this shellcode is going to be executed. So step into, and right now you can see this RDX has the memory address of our shellcode, and this is our shellcode. So right now you can see these are the instructions of our shellcode. You can see clearly. First we are performing XOR between RX. Let me open up my let's open our shellcode file. Let's shellcode source file, which is our assembly source file. So let's vim and then hello world.asm, and you can see clearly here, you can see it clearly here, always on top. Okay, so you can see first in the first line, you can see this is our shellcode. In the first line we are performing XOR RX. You can see XOR RX. After that we have our move. You can see this is our move 1 into AL. Then we have XOR RDI. You can see all these parts are the shellcode, our hello world shellcode. So let's use next instruction. You can see all these parts are executed, and right now you can see in this line the shellcode is going to push the last 4 bytes. You can see this is the last 4 bytes of our hello world string. So let's use next instruction and let's see if that, like how that 4 byte is loaded in on our stack right now. So let's see using ni, and you can see right now the last 4 bytes are pushed on the stack right now. You can see RLD, then this /n. So these 4 bytes are pushed onto the stack using this push, and after that we are moving the rest bytes, the rest string part into RBX register. So let's use next instruction, and you can see in RBX register, you can see here the rest part, hello space WO, these are the rest part of our hello world string, which is moved into RBX. And then finally we are moving this RBX into the stack using this push RBX command. You can see push RBX. So let's use next instruction, and you can see on the stack right now, you can see on the stack we have our hello world. We have last 4 bytes which is aligned in this part to become hello world complete. So this is our hello world which is stored on our stack right now. So right now the program, like our shellcode, is going to move the RSP pointer, like the RSP address, into RSI register to point at our hello world. So let's use next instruction, and you can see RSI right now, this RSI has our hello world address, which is the address here, which is the address of our stack. You can see this 98, this 98 is the address of our top of the stack right now, and on the top of the stack we have our hello world. So we have successfully passed the memory address of our hello world string into the RSI register successfully. So after that we have other shellcode instructions. You can see XOR RDX right now, XOR RDX, then we are adding this 12 into RDX, which is the total number of bytes which we want to print, and then we have our syscall here. After that we have our exit system call here. You can see XOR RX. So let's use next instruction, then let's use again next instruction. So this, you can see this is our exit system call, these 3 lines. You can see XOR RX, then we have 16 to AL. You can see this 16 to AL. So this is our exit system call, which is exactly the same which we have written in our shellcode. So let's use C to continue our program. So program exited normally. So you can see how easy this is to make some analysis on our shell code execution. So you can see all these instructions of your shell code easily using this method in your GDB to perform all the shell code loading in your memory, like to see the shell code working in memory. So that's all for now, and if you are facing any kind of trouble regarding this topic, let me know in the comment section. I will surely help you. So I will meet you in the next part. Till then, goodbye.